So let's just get on into it. First off, welcome. Thank you for joining me today on this. Looks like I haven't been outside today. Looks like overcast Saturday. For those of you who don't know me, my name is Adam Betinsky. I'm a junior here at UCF studying computer science. I've TA'd for this CS1 twice with Dr. Ahmed. Absolutely love it. About to do it a third time this semester. It's nice to see some familiar names, also some new people as well. Nice to meet you all. I'm looking forward to this. Thank you all for joining again. Normally, AJ, the workshop director, would be here to introduce himself and a quick overview about the club, but he was not able to make it today. I think he will make it tomorrow. By the way, this what we've done in the past with this when I did it last time. Well, first off, before I even get into that, thank you Night Hacks, even though nobody is here from Night Hacks, for letting me do this again. I know they typically don't do it for the spring semester, but I know a lot of you last semester were asking for it, and I really enjoy doing this. So I thought, you know what the hell, might as well do it again. So thank you for that opportunity again. Now, as we're getting into this, just like last time, what we did was it'll be across three separate sessions across 3 days. Um, with that, tomorrow should be at the same time, and the third one should be on Tuesday from I think it's from one to no, what the hell am I saying? It's from 10 a.m. to 1 p.m. If you can't make it to all the sessions, no worries. They will all be recorded and uploaded to YouTube. I'm recording right now. By the way, you guys can see my screen, correct? Okay, awesome. While we're doing this, if you have any questions or anything, feel free to either throw it in the chat or unmute. If you want to interrupt me, feel free if something doesn't make sense. For those who watch my live videos, I'm basically going to treat it the exact same way. So if you have a question or anything, don't hesitate to ask. This is why you're all here. Any questions, comments, concerns before we get started? My microphone just died? No, it didn't. Okay. This is my first time using this microphone on something like this. So, how's the audio? Glad to hear it. My pleasure, Judy. Very happy to do this again. All right. Any quick questions? I guess I should have the chat open. That'd probably be helpful. Any quick questions or comments, concerns before we get started? All right. So, let's get into day one. So, first off, I think the good thing to always start with, we did this last time, is to start over. By the way, for those who just joined, I should mention the background slides are the same from last time. If you watched the last work time I did this, but the questions are new. It is all new questions we'll be going over. So anyway, so a good starting point with this that we always say. Well, let me jump ahead. So here's the overview of each day. You know, Basically, we're going to just go through the whole course. It's not going to be a full on review of all the topics, but it should basically, we'll do a quick brief, like, here's what you really need to know for each topic. And then we'll go over some questions for it. Unlike last time, I asked AJ to change it so that instead of two questions randomly, we will definitely be it will always be three questions for each topic. One of them will be a conceptual question, and two of them will be coding unless that topic doesn't have it, like AVL trees. There's no coding, for example. But for pretty much all of them, it will be three questions, one conceptual, two coding. That way, you can get a good mix of everything and see just how what curveball is going to be thrown out on the exam. I Day three is probably going to be a little shorter. Last time these sessions were allocated for 3 hours, but they ended up going to 4 hours almost every day because I was trying to take my time with everything. So if you need to leave at some point, feel free. I don't care. It's you're adults. You can do whatever you want. But again, everything will be recorded. And apologies in advance if this does go over. But I want to be as thorough as possible with you all. So here's all the topics for each day. It's like day one's mainly a lot of the data structures. Day two and three, well, day two is more of the algorithms, I would say, some data structures, and then day three is kind of just other stuff. Base givers, somewhat the easier stuff, I would say. So, of course, I'm very happy to host this again. Thank you again, Night Hacks, for allowing me to do this once again. Hopefully, I don't get laryngitis this time. All right, so let's quickly go over first off, before I forget, because now I'm going to forget this, make sure you register for the exam, please. If you haven't done that already, please go do it right now. It takes 30 seconds. Um, I think if you need to register, it's on Guha's website. If you just search Arup Guha, it would help if I type the whole thing. You type Arup Guha. Yeah, there you go. Go to his homepage. And then I think if you scroll down, yeah, foundation exam links here. If you click that and then register for spring 26 foundation exam here, it will take you to the registration page. It'll make you log in with UCF. Now, see, it's going to say I'm not eligible because I've already taken this before. But make sure you do this because you cannot take the exam without it. And I'm pretty sure that it closes on Wednesday. Don't quote me on that, though. I'm not sure when this closes. But literally takes 30 seconds. So, anyway, the exam is on Saturday, this upcoming Saturday, a week from today. I don't know what time it's at. I'm guessing, I think usually it's at 10 a.m., but don't quote me on that. You will get an email from Guha explaining everything, probably in a few days or so, sometime this week. The only exception to that is if you're at you have SAS accommodations, you will be taking it on Friday at SAS. If you haven't already, make sure to reach out to them because they need to add you to their system and whatnot. It's a bit confusing. The exam itself is 2 hours split into 4 sections. Part A, B, C, and D. I don't really know the science behind it, how they did this. But basically, it's a 2-hour exam, so if you use your time efficiently, that's 30 minutes a section. Each section has 3 questions, where one of the questions is worth 5 points and is supposed to be quote-unquote easier, and the other 2 questions are worth 10 points, which is supposed to be a little harder, all for a total of 100 points. My biggest thing I always tell students is that even if you don't know how to do a question, put something down, even if you know it's wrong, even if you think it's the stupidest thing ever, put something down because you never know what partial credit you're going to get. I cannot tell you how many times I've seen students not put anything down and then tell me later, yeah, that's what I was going to put, but I didn't for some reason. And I was like, well, you should have put it because, then you would have gotten 2 or 3 points. And, every point counts in this exam. The passing line always changes every semester. So always put something down. Please do not forget that. Now, the other thing I tell students is that when you get the exam, don't just jump straight into the first question. Take 5 minutes of your time and quickly glance over all the questions and categorize them into 3 categories. Now, I'll write this down so you can forget. I'll say category 1. Actually, let's do category A. I think that sounds better. Category A. If you see a question that's like, okay, I can do this right away, I'll say, quote, I can do this. If you see a question and you're like, okay, I can do this question no problem in 5 to 10 minutes, great. Mark that in category A. Category B, instead, if you don't think you do this question easily, but you think you can do it, this is basically like, I can do this, but you may struggle on it or take longer. I'm just writing this down fully, so because I know people like to look at what I write afterwards. Hopefully, y'all can read my handwriting. So, category B is you can do it, but you might take longer or struggle on it. So, if you see a question like that, put in category B, and then category C is okay, I don't know how to do this, or you're gonna struggle. You really don't think you'll do it right. I guess that's the same thing I just said twice. So basically, mark the questions in these 3 categories. Quickly glance over them all, whether it's based on topic, length, or just personal opinion. After you do that, you can write this on the exam if you want. You can write whatever you want on the exam. Well, don't write gibberish, of course, but you know what I mean. Once you do this, first go through the questions in category A. Get most of your points done. If you can do all those questions in category A, you should be set for a good score at least with those questions. If you're confident about them, then go through the ones in category B. See what time you have left, and then go through it, see what you can get done. Then, if you still have time after doing those questions, try to go for category C and get done what you can. By the way, you get all 4 parts at once. You do not have to do them in order. You can do them in any order you'd like. So try this approach. I think it's helpful. The other thing I will say is that if you can, if I don't know if you'll have time, but if you do, look over your work. The biggest thing, and I will emphasize this in pretty much every question, please draw everything out. It is so helpful to do examples and draw things out. I cannot emphasize that enough. Especially, what was I going to say? When you get a question, you shouldn't just jump straight into it. Take 2 or 3 minutes to make sure you understand what it's asking you. Think in your head in English, like, okay, it's asking me to do blah. Like, for example, it's asking me to flip a linked list around. I'm just making that up. So what does that mean? Well, am I going to have to make nodes? Am I going to have to move pointers around? Am I going to have to, move? Well, I guess those are really only two things. Well, am I going to have to change values inside a linked list? Keep those thoughts in your head. And as you're doing that, if you need to, literally write on paper like a checklist. I did that on the exam for a couple times, and it really helped me. Make a step-by-step plan of what you're going to do in English. And then as you're doing that, afterwards, just use that plan you made to make the code or solve the question if it's conceptual and check it off as you go. It really makes a difference. I cannot emphasize that enough. Aside from that, as you're studying, first I would say focus, there's those websites where you can filter it by topic. First, focus on the questions or the topics that you think you struggle with the most. After you do that, try doing topics on questions on the topics that you feel better on. After you do that, I would say take a couple, 2 or 3 mock exams, like full exams, and don't just do it on your computer. I actually say, and I did this, print out the exam just like you're doing it in real life, like when you're going to next Saturday. Go to a quiet place, get a pencil out, and by the way, for those that don't know, there is a formula sheet you get. I don't think it's the most helpful thing in the world, but you have it. Print out the formula sheet, get a pencil, an eraser, and time yourself. It's 2 hours. Try going through it. See if you don't finish on time, don't just end the exam. See how much longer you take, but then learn from that. Okay, here's where I took long enough. How can I be more efficient with this? And then see afterwards how you can go from there in your studying and do 2 or 3 exams. Old exams are really your best bet, in my opinion. Don't do one from like 1999. That's probably too old. The Guha's website, he has that archive of old exams from his class. That's a pretty good resource as well. But old foundation exams are probably your best option. The formula sheet is also, the formula sheet is also on Guha's website. I think we can look real quick. Yeah, formula sheet right here. Here it is. It's pretty much, you might have seen this in your midterm if you took the class last semester. Oh, thank you for putting in the chat. It's basically the same. It's just function prototypes, really. Not the most helpful thing in the world, in my opinion. Probably the most helpful thing are the summation formulas. But if something's not here and you need it, they'll typically give it to you on a question. And then the outline and FAQs are there as well. Pretty much everything about the foundation exam you need is on this website. So, any questions about any of that mumbo jumbo I just said before we actually get into doing stuff? Also, does anyone need me to send those slides again so they can follow along? I'll just put them in anyway. Feel free to send this to a note app or whatever you like to take your notes on. There you go. The version with the solutions will be posted later. I'm just posting the blank versions for now. I don't want to give everything away. All right, so any other questions before we get into it? Does everything make sense about how the foundation exam works? Again, feel free to unmute if you don't feel like chatting. It's always nice to hear other voices. Ooh, I like the thumbs up. That's cool. All right, so let's get on into it. Let's do this thing. So today, day one, it's going to be, what was that, 5 topics. Infix to postfix is stacks to me. I mean, I know it's technically different things, but basically 5 topics. I'm counting it as 5. So we'll see how long this takes. I'm going to go through every question step by step. On some questions, I'll give you guys a chance to try it on your own first, mainly the conceptual questions. But we'll see how we do. All right, day one. Let's do this thing. Starting off with everyone's favorite dynamic memory allocation, good old DMA. Dynamically allocating memory, it's in the heap space. It's basically the point of it is it's a way for the user to properly allocate to use variables and mainly arrays and stuff, but other variables and stuff without having to worry about runtime issues or variable length arrays. And the biggest way to do those, of course, is to use DMA as malloc, calloc, and realloc. Or, well, malloc and calloc is for initializing, and realloc is for resizing an array. So let's, or any DMA really, I shouldn't have said an array, it could just be a single integer pointer. So of course, let's just pretend you want to allocate a single integer pointer. Well, you could do malloc or calloc. Let's do malloc, that's the usual. You write int, of course, and then you put the star for a pointer. By the way, this is in C. Everything on this exam is in C. And then you give it a name. You give it whatever the heck you want. So let's just call it PTR for simplicity. And then I'm going to call malloc. And to do that, you would literally write malloc. Now, a lot of people have asked me, do you need the typecasting over here? The answer is no. You can put it if you want. I just think it's kind of extraneous. You don't really need it. I don't put it because, at the end of the day, whatever you write over here gets casted to this over here. But you can put it if you want. It's not wrong. But then if you wanted to make a single integer, of course, you'd be malloc size of int times, well, you don't even need to do that for a single one. You could say times 1, same thing. But the semicolon. And what that does is now you have two boxes. You have PTR, and then you have a box over here without a name. What do you mean if you write the type up here, Christian? I didn't do it on my foundation exam, and I didn't get penalized for it. It's not that big of a deal. There's much more other things they're looking for than stuff like that. You might be asked to use calloc or realloc. It's possible. In the midterm this past semester, there were questions on calloc and realloc. I know most of the time malloc's the go-to, but you need to know how to use those as well. But anyway, so we have a pointer box, and then over here we have a box without a name. This is our dynamically allocated memory here. Let's say it has a memory address of 510. Then that means inside the pointer, it's storing 510 and literally pointing to this, and that's how you access it. That's a malloc call. Does that make sense? I'll take your silence as a yes. Okay. So then a calloc, is very similar. It's just the parameter is slightly different. Malloc takes one parameter, as you can see. You kind of smush everything together. Calloc, the first part's the same. So now let's say we wanted to make an array of 5 characters. Why did I just write int? You do char star, let's call it str, because we can pretend it's a string. Now, if you want to do a calloc, you first have to you still write calloc, but then you first put the size. So let's say we want 5 of them. So you put 5. And then you would put size of char. And that's a calloc call. And now that would basically make an array of size 5 without a name, where the pointer is pointing to the first element. So we have an str box over here. Let's say the starting memory address is 870. That's going to go inside of here and point to there, and then you can access the rest of the elements in the array. Now, I will say, people have asked me before, and if you're doing a char and a malloc call, do you have to write size of char since it's 1 byte? Technically, no, but I would. I think it's more formal and more professional, and I think they'll really understand then you know what you're doing. But anyway, does this make sense how calloc call works versus a malloc call? Any questions on this? Oh, yeah, that's the other thing I forgot about. When you use a malloc call, everything is initialized to garbage. When you use a calloc call, everything is initialized to 0. Now, I don't know how that fully works if you're doing a char. I guess everything's initialized to the ASCII value of 0, which I forget what that is. But just keep that in mind in the back of your head. And then if these don't work, of course, it returns null. Otherwise, it returns the pointer that you made. You will probably get penalized if you don't put size of yes, because you have to specify what you want the size of, if you want to make 100 integers, you have to tell it, okay, I want 100 times the size of an integer. Because otherwise it's ambiguous. Well, if you just write 100, do you mean character? Do you mean integer? Do you mean float, double? You have to write that, yes. Does that make sense? Awesome. So now realloc, the last thing. No, they will, well, it depends. It might just, I'm making this up. Say you have a question where it's like, I'm making an array of employee names where each employee's member ID is initialized to 0. Well, then okay, Calloc would make it a little easier than malloc. And you could still do malloc and then manually initialize everything to 0 after, but then that's a separate loop. So they might not specifically state that, but if there is a situation where okay, hey, everything in this person's thing or data type or whatever needs to be initialized to 0, then it might be ring a bell in your head. Hey, Calloc might make this a little easier for me. Does that make sense? No problem. So now the last big thing is realloc, of course. So let's say we had this array over here, right here, and we needed to increase its size. I guess you could technically decrease its size too, but that sounds kind of silly. Let's say you wanted to increase its size to 15. Well, realloc then makes everything garbage again. But what it does, so let's say we have someone give me a 4-letter word. Let's do, I don't know. I don't know why I'm overcomplicating a 4-letter word so much. Okay, exam. I like exam. So let's say we have exam with the string terminator, of course. Never forget the string terminator with characters. You always got to allocate that extra spot for it. Don't forget that. A lot of people always forget that. So now let's say we wanted to have more space. So now realloc, if you want to do that, you call realloc. So you would first write realloc, and then you put the original pointer name. So in this case, it was str. And then on the right, you put the size, just like a malloc. So now let's say we need 15 characters. So you'd say 15 times size of char. Does that make sense? Now, is this correct? Or am I missing something? What do you guys think? Is this semantically correct? You okay? Well, two things. I'm not worrying about the Terminator. Fine, I can do that. I guess. Okay, sure. We pretend we're adding a 15 character word. Now we have an extra space for the Terminator. Sure. Yes. The thing I noticed people miss this in the class. That's why I'm mentioning it. You have to reassign it to a pointer. Now, usually the standard is you just put it to the same pointer like this. Because what this does is it reallocates everything, but it saves the result to a pointer. So you might as well save it to the original pointer. Now, what you could do in case it fails is basically call this something else. So you could say char, I'm just going to call it x, and then be like, okay, hey, if x is equal to null, then free everything. Because if you free everything, or if it is null, then you could free everything without losing or access to the memory. But usually you don't have to worry about the null check for this. The point I was just trying to get across is reassign it to the original pointer. Does that make sense? So then what this would do is, of course, make an array much bigger. I don't know if I'm going to get 16. I'm not really counting. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8. No, I was way off. Well, that was too small. Well, there we go. So now you would have your bigger array, and then it would copy everything over from the original. So you'd have exam, and then like this. Now, of course, in this example, you need to move the terminator, but I'm just trying to get the point across of how realloc works. So that realloc is used for expanding memory, basically, on something, dynamically allocated memory. Does this all make sense? Any questions on this? No. On this one, if you put char star pointer again, you would overwrite the original pointer. When you're referencing a variable that you already have, you just write the name. That's just how it is in C. Does that make sense? No problem. Any other questions on this? I haven't honestly seen that many tricky scenarios with realloc on the FE. It's mainly more malloc-calloc that I've seen, and freeing. Freeing's the big one as well. Speaking of which, let's talk about freeing. Every malloc-calloc realloc, any alloc as they call it, has to have a free. You got to make sure to free all your dynamically allocated memory, or you'll have a memory leak and probably lose points. You know, it's not good for the computer, but this is a paper exam, so that doesn't really matter. So basically, anytime you allocate something, make sure at some point later on, before the program terminates, you write free and then pass in whatever the thing is you dynamically allocated. Now make sure, I've seen people do a couple things. I've seen people do this. If I wrote free n, what is wrong with this? Based on this code. That's freeing a statically allocated variable. You can't do that. That's going to cause you a compile time error. No, it has memory technically. You know, it's a static variables in the memory, but you can't free statically allocated memory because it's already going to be destroyed when the program terminates. That's the whole point of freeing dynamically allocated memory, because otherwise it won't be destroyed. But at some point you have to destroy it or you're going to get the memory leak. But does that make sense, the versus freeing static versus dynamic? Take that as a yes. So then the other thing I see people do, don't free the same thing twice. That's called a double free. Doesn't work out that way. You can't do that. That's almost like saying, you know, I drank a cup of coffee and then I'm going to drink from the empty cup. You can't do that. It doesn't work. So does that all make sense? Oh yeah, and the other thing, of course, is don't use something after you free it. That doesn't work as well, because once you free it, it's gone forever. You're never getting it back. So, any questions on this? You don't have to put that. No, I don't put it. I don't think it's necessary, but you can if you want to. There's no point associated with that. I just think, you know, save your space, save your energy. One less thing to write. Why do it? But you don't have to put the type caster, because again, remember, anything like whatever you write over here, it's a void pointer and it gets casted to what's on the left side. So, all right, moving on. You know, common mistakes. Make sure always that you have a mismatch of data types or pointer types. My favorite saying, as I like to say, when you're allocating something, whatever's on the left side should be, like to say, quote unquote, one step higher than what's on the right. So you see here, everything's being saved into a double pointer. Well, then the thing that's being passed into malloc on the right side should be a single pointer, not a double pointer. It's one step down. Does that make sense? So you're going one step down over here. This is wrong. This should be, that should only be one star, it'd be an int star. This example is just showing you it's wrong. But see what I mean? You're going one step down like that. It's always like a quick self check in my head. I love these self checks. Like, okay, hey, I did that right. You know, things like that. So always, you know, whatever's on the left should be one step higher than whatever's on the right. Does that make sense? Now, of course, whoa, there's just an explosion of thumbs on the screen. That's funny. Um, the other things, of course, you know, make sure you always got to initialize things, especially the biggest thing I see. If you need a counter or something, and students don't initialize that, I see that all the time. Please make sure you initialize your counter variables. You got to do that or it's wrong. It just won't work. But of course, you know, same thing with strings. You can't copy anything into something that's not initialized. Of course, with DMA, the left side has to be a pointer. It won't work otherwise because this is an address on the right side. And then, of course, this is a kind of an extreme example, but when you're using a 2D array, make sure you allocate the rows and the columns before you start assigning stuff, because otherwise, again, just won't work. That's pretty much everything I just said. Any questions on this? Those are common mistakes. All right, so let's get in. I think next is an actual question. And up, there's some more stuff. Actually, a lot more stuff here. I forgot what these slides looked like. No, you have a question. What's up? Go ahead. Don't be sorry. Which statement that was allocated? Oh, this here. So this is the creation right here of basically the outside pointer. In a 2D array with DMA, you have the double pointer out here that points to some amount of pointers. These are like your rows. And then each one of those pointers points to a set number of columns. Let's just say it's 3, and those are the normal version of that data type. That's 4, actually. But so basically, the creation, this statement up here is doing this guy here. But then what the user didn't do in this case was do this and this. You can't do the last two you can't put anything in the last two if you don't initialize them. Does that make sense? Does that answer your question? Well, okay. It makes the space for the array. It just doesn't put anything in the array. Does that make sense? You have to manually assign it after you allocate everything. Perfect. I'm glad that answered your question. That's a good question. No problem. All right. So problem tips. Of course, leave no pointer without memory unless you're doing it statically. Don't allocate a memory to something that's not a pointer. Here's that one step down thing I was talking about again. Pay extra attention to 2D arrays. Don't forget the terminator for a string. You always got to allocate one extra space. Pay attention to function return types. That's always a good thing. If a function's return type is an integer double pointer, for example, well, then one of the first things you should probably do is make an integer double pointer and be sure to free it at the end. Or not free, return it at the end. Excuse me, return it at the end. And then, of course, the other thing I forgot about is when you're freeing, make sure you always work from the inside out, because if you work from the outside in, you're going to get a memory leak and you basically lose access to everything. Always get yourself inside the mess, start freeing from the inside and work your way out. I don't know, a stupid analogy of that is if you have a meatball, get yourself into the center of the meatball, start eating from the inside and work your way to the outside. I don't know. I just came up with that on the fly. That was probably the stupidest thing ever. But does that make sense? That was just kind of from the slides, other stuff you should know. How is memory stored? Pointers are 4 bytes for integers. 8, well, you're not really asked this stuff. The thing you really need to know is an integer is 4 pointers, or 4 bytes, excuse me. An integer is 4 bytes. A char is 1 byte. A double, I'm pretty sure, is 8 bytes. Or float, excuse me. A float is 8 bytes. Pretty much all you need to know in that kind of sense. And then static stuff goes on the stack space. You can keep that, S goes with S. And any dynamic memory goes on the heap space. Now, I'm pretty sure that's not like a heap data structure kind of thing. I'm sure that's 2 separate things. I'm pretty sure. But you just kind of need to know that. That did appear this was the exam I took. That was a weird question. But just kind of other things you need to know in your head. The biggest thing, of course, is can you solve the questions? Do you know how to dynamically allocate a structure array of different lengths? Can you allocate a single pointer? Can you allocate, X, Y, and Z? If you can do that, you should be pretty much set. But this is just other stuff to know if you can. 2D arrays, we'll go over a question like that probably, but you allocate the double pointer, then the array of, it's basically just like in that example I drew up there, and then work your way from the inside out. Does that make sense? And again, these slides will be posted later if this is too fast for you. For this kind of stuff here, I'm going to go a little faster just for time. I'll spend more time on the questions. So, any other questions before we get into this, though? All right, so let's do it. We have 3 questions. Again, 1 conceptual, 2 coding. These are all very good questions. I like these, especially the last one's a good one. But let's start off with our conceptual question. Here we go. Consider the following code that attempts to allocate a new array with the same number of rows as ARR, which is a parameter of this function, as you can see, but triple the columns. Copy the values from ARR into the new array in the same slots, free the dynamically allocated memory pointed to by ARR, and return a pointer to the new dynamically allocated array, new ARR. Okay, whoa, that's a lot, isn't it? So this is why I always say, take a second, read it 2 or 3 times, read it as many times as you need to. And then the other thing I always say, let's draw an example. So ARR is a parameter being passed in, and for ease, let's say it has initially 2 rows and actually let's do 3 rows and 2 columns. So the way this would work, since this is a double pointer, that should ring a bell in your head, that's dynamically allocated. ARR is a double pointer that's pointing to basically an array of 3 dynamically allocated pointers, where each one of those pointers points to 2 integers. Let's just make up some values, 5 and 3, 8 and 7, and then 6 and 7. I had to throw that in there somewhere. I'm sorry, I couldn't resist that. But that's what ARR is. It's being passed into the array. And then the number of rows, this R variable up here, is being passed in. And the number of columns is being passed in as well. Now, the point of this, let's read the question again. The point of this function is to basically remake this whole mess, but have triple the columns, basically. So instead, there would be 6 columns per row instead of 2. Does that make sense to everybody? Then it would copy everything over here into the way it is now, and just except with the bigger array. So, I'll draw this in blue. It's too dark. Orange. So then the function would make 4 more empty spots in each row, and then leave everything else the same. Now, mind you, it would actually copy the stuff over to a new array, but I'm just leaving it as is for simplicity's sake. And at the end of the day, it would free all the old stuff here in red and return the new stuff. Imagine this whole thing is in orange. It would return the orange array. Does that all make sense? The point of the function. Do you understand what the question's asking you? Okay. So now the question is, let's see what we're being asked to do. The key errors in the code are at points A and B noted in the comments. Question part A. What is the fix for the line of code for part A? There's no it's one simple, so no need to write out any code. So let's take a look at this. Can someone tell me, based on what this question is asking and what we're given, what's wrong with question A? Or point A, excuse me. Correct. The times 3 is not supposed to be there. We want to triple the number of columns. We're not tripling the rows. We're not asked to do that. There should be the same amount of rows. We need to leave that alone. So basically the answer to this is just remove. Now, do I just remove the 3 or do I remove the star 3? You have to do the star 3, exactly. If you don't remove the star, that's a syntax error and that's wrong. I don't think you might get partial credit for that then. Oh, never mind, it's all or nothing. I'm looking at the grading criteria. So you have to put the star 3, or otherwise you won't get the point for that. That there is 1 point. And again, this is a 5-point question. Each section, we're kind of jumping around the sections today, but it's a 5-point question. It's supposed to be easier. So, also, I did see we had a question. Let me go back to that real quick. There's no pattern for the exams, and these are not Guha's questions exclusively. A few of the CS faculty come and write the exam together. They get a section. Usually I think Guha does a section, Ahmed does a section, Dr. Ali does a section, etc. And then they all come back together. But then Guha told me, since he has quote unquote the authority over the exam, he can overwrite one of their questions if he doesn't like them. But so there's really no set pattern per se of what topics could be there or not. It's random. There's some things like you'll always get a DMA question of some kind. You'll usually get, a sorting or tree question. You'll almost always get some kind of recursion question, even if it's not in the recursive section, things like that. Does that make sense, Katrina? No, that is not wrong, Christian, because this is correct here. Because remember, the double pointer's out here, and it's allocating what's are quote unquote the rows, which should be pointers. It's one step down. Remember, whatever's over here needs to be one step higher than the data type you're allocating on the right side. Does that make sense? Okay, awesome. Now let's move on. Part B. Why is the line of code for point B incorrect conceptually? Let's get the drawing. What's wrong with that? Yes, we didn't allocate the space for. Well, no, ARR is not changing. We're not changing ARR. That's staying alone. New ARR is basically the bigger copy we're making. Yes, Nikki is correct. Is that how you pronounce your name? Nikki? Apologies if I said that wrong. But yes, that is correct. Basically, the problem with this is it's pointing, this is basically assigning a pointer to the original array and not copying the value. You see, the problem is you're missing the column on the left side. Remember, new ARR is a 2D array, and we should be allocating that inside after we allocate the columns. We're kind of jumping ahead here. You need to have the rows and the columns there because new ARR is a 2D array. Does that make sense? Any questions or confusion on that? Okay. So basically, need, I'm just going to say columns and assignment. Doesn't have to be perfect. As long as you get the general point across, you'll get the right answer, or you get the point. So then, now part C is how do we fix this? Someone tell me what's the general idea on how we'd fix part B to do this correctly. If I'm going through the rows already, what do we need to do? Exactly, a second loop to go through the columns. So what would that look like? Well, for int, I'm going to call it C equals 0. C is less than, what would C be less than? Calls, exactly, because that's the number of columns. But is it calls? Oh, no, wait, yes, it is calls. Never mind, I'm stupid. Forgot what I just said. It's calls because we're just copying everything over. We don't have to worry about the extra stuff because we're not copying anything in there. And then I plus plus. And then what would the assignment statement look like for each original value? Oh, it's C++. Thank you. Shout out to the language C++. So then what would this look like? Well, it would just, instead of doing the rows, you do the row and the column on the left side. So new array at row column equals the original array at the same thing, the row and the column, because both of them are 2D arrays. And there you go. That's it. That will fix the code. So now it does everything as intended. It will make all this. Whoops, I was going to change it orange, but whatever. It will basically satisfy the function. Does that all make sense? What's the question? What do you mean if it asked it to be spaced out one by one? You mean like if there's a gap between each value? The thing is, if you did that, I think you'd have to, allocate a lot more space, and then that'd be a little complicated. I don't really what you'd have to do is just go. I think in just your loop, instead of going one by one in the columns, you would just go you increment by 2 every time. So maybe it wouldn't be that hard. You just have to do some pointer arithmetic there. That's probably something they won't ask you, but I could see it though. It's possible, but not likely. Does that make sense? All right. So, any other questions, comments, concerns about this? No problem. Give me 1 second here. All right. Here is the formal solution and the grading criteria. You can take a look at this later if you want. So now let's move on to the second question. The coding question. Oh boy, let's do it. Also, I will before I forget, if you're given a structure name, a variable name, or something, you have to reuse it. If you don't reuse it, it's wrong. You have to reuse what's given to you, if necessary. If something's not necessary, then don't write it. But if you are given something that you need, you have to use the same name and declaration of it. So if they don't use a type def structure, but you don't write the word struct, it's technically wrong. Does that make sense? You have to keep everything the same. All right. So let's do this. Suppose we have an array to store all of the holiday presents we've purchased for this year. Now that the holidays are over and all the presents have been given out, we need to delete our list. Our array is a dynamically allocated array of structures that contains the name of each present and price. The name of the present is a dynamically allocated string to support the different lengths of strings, and I'm highlighting that for a reason. That is dynamically allocated. Write a function called delete present list that will take in the present array and free in all the memory space that the array previously took up. Your function should take 2 parameters, which are given to you, the array called present list and an integer num representing the number of presents in that list, and return a null pointer at the end representing the now deleted list. Note the array passed to the function may be null as well, so you need to handle that case as well. Okay, that was a lot. So let's take a quick breather here and look at this. Let's look at the structure we're given. Here's our present structure. We know present name is dynamically allocated. It's supposed to represent a string. Now, is price dynamically allocated? No, correct. So we should not touch that at all because when we're freeing things, you don't free things that are statically allocated. There's no point in don't touch it. It's going to be wrong. So leave the price alone. But the present name is. So we'll have to deal with that at some point. Now let's draw out a quick example here. I'll do, um, let's say we have, this is a 1D array, by the way. I should have pointed that out, which you can tell since we're being passed in a single pointer. So let's say we have an array of 3 presents. Yeah, let's do 2, make it easier. For each present has a price. I'm just going to make up a number, 5610, and then 4767. Yes, that was intentional again. I'm sorry. And then each one has a name. So let's say the first one is called, I don't know, Ahmed Action Figure. That has a name in an array. There's an array in there. I'm just not drawing it out for simplicity. And then the other one is called, how about Nitro? So each present in the list, inflation in the coding questions is crazy. Each present in the list has a name, where this is dynamically allocated. There's all the indices and whatnot. I'm just not drawing it out for time's sake. But that technically in here there's a pointer that's a char pointing to these. I should have made the boxes bigger, but imagine they're in the box. So that's how each one looks like. Does that make sense? Like what the array itself looks like. This is why I really think drawing it out really helps you to understand the question. Now let's look at this. Let's what do we have to do? Well, we need to free everything that's dynamically allocated, which we said is the names and the entire array itself. We're not touching the price. So if we have to go through something more than once, what do we need? A loop, exactly. Now, should we jump into the loop right away, or is there something else we need to take into account first? Yes, we need to take care of the null case first. If you loop into something that's null, you're going to get a problem. Always deal with your null case first. So, how would I check, first off, if the array itself is null, doesn't exist? Exactly. You got it right. Good job. If present, and see how I'm reusing the names, if present list is equal to null, well, then we were told no matter what, return null. So in this case, we're going to return null. Cool. We took care of that case. Done. Any questions on what we just did? By the way, these are squiggly brackets. I just cannot write them for my life. If the question didn't mention it, don't worry about it. Usually it'll tell you, almost always it'll tell you this is either null or you can assume it's allocated. I mean, it wouldn't hurt, but usually you don't need it. So now, okay, now as we said, we got to go through everything, each present. So we need a loop. You could do a while or for. I think for is easier. For int I equals 0. I is less than what? Oh, I forgot. This is freeing. Yeah, I'm sorry. Yeah, when you're freeing, you should put a null case. Yes, I apologize. I don't know why I thought we were allocating for a second. Yes, when you're freeing, put a null case. It's good practice. But yes, I is going to be less than num because that's what we were told represents how many presents there are. Equals plus. Now, as I go through this, what am I going to say? What are we freeing at each index in the array? The present name, the price, or both? The name. Good, because that's the only dynamically allocated thing. They say free. Now, how would I write this? And again, if you don't want to type it out, feel free to just say it. Either is fine. Yeah, I can zoom out. Sorry. Okay, so this is a good question. Is it you're all very close, but is it dot or arrow? Why is it dot? That's not necessarily not because we dereferenced it, and not if it's a linked list. Good guesses though. Not because it's an array either. Yes, Russell got it. You use the arrow when you're dereferencing a structure pointer, not a regular pointer. If it's a structure pointer, if this was like, I'm making this up real quick, if this was like an employee or something, then you would use the arrow. But because this is just a plain old char, you use the dot because you're just accessing the member of a structure. Does that make sense? If that was employee, you would still do dot and then the arrow. But basically, if it's a structure pointer, then you use the arrow. So, as most of you said, though, it would be present list at I dot the present name. Cool. Okay, all the present names are gone. Now what do we have to do? And that this whole chunk right there, by the way, was 4 points of this question. We free the rest of the list. Exactly. Free the outside. We're working from the inside out. We did the inside, now we do the outside. So how would I write that based on what's given to us? I want to make sure you guys understand. Exactly. Free present list. That's it. Literally all it is. Free present list. And here's a quick question. Why am I not writing free struct present list? Why am I writing just free present list? Because it's not typed F, so don't you have to write struct every time? It's part of the struct. Just curious, this is kind of a side question. Just curious if you guys know this. Any other ideas? Good guess, Deborah. The reason these are all good ideas, but the reason you don't have to write struct in this case is because present list is a parameter. You don't have to rewrite something that's a parameter like that. You just write the name of it. Does that make sense? I'll come back to the employee thing in a second. But does that make sense why I'm not writing struct in this function? If you did, it's technically wrong. Any questions on that? Wow, we're already an hour in. Jeez. It's probably going to go a little over. I apologize. Y'all can still hear me okay, right? Just want to make sure this microphone's working. Okay. All right. So, what's the last thing we have to do? Are we done? Or do we need to return something? Well, first, what's the return type? We need to return null because we were told that in the question. So return null. And that's it. There you go. Not too bad if you draw it out like that, in my opinion. Now, let me look at your questions. Yeah, that's also true, Fernando. You don't need to redeclare a variable type every time you do an operation with it. That's also true, exactly. Same thing. Now, the other question was... So, with the employee question, do you mean like this was... the structure was an employee or this was an employee up here? If it's not a member of the struct, don't use the dot. The dot's only used for accessing the member of the struct. So, okay, so if this was an employee, temples, we made a temple. Oh, I think I get what you're saying. So basically, if you're saying if you have an employee pointer, like an employee structure that has a name, and then I'm just making this up, it has a name and like I don't know, an ID, and then you want to access the name. Are you asking if it would be dot or arrow? This would still be dot because you're accessing the member of the structure. Now, if this was a pointer, it would still be a dot. But then if this name was like, I'm going to make this up, like if this struct employee was a struct, I don't know, struct super, struct super name, then, and this would be a pointer, it'd have to be, then you would basically say, okay, employee, whatever. Well, let's just say we have an employee declared called X, so we'd have struct employee X. If you wanted to access the name, it would be X dot. Wait a second. That feels wrong. I'm used to that in an array, in a sense. So let's say we had, 5 of them. Then would be, X at I arrow name. Does that make sense? Does that answer your question? No problem. Okay, any other questions about this question? Say that 10 times fast. When we're freeing Elena, the whole freeing present list, it's gone, so we can't return it anyway. and you can only return one thing from a function. So, and when we're being told to return null, so you you return null. That's what you have to do. Any other questions on this? I hope my teaching style is coming across to you all well. I hope this is making sense. No worries. All right, so let's do the other question. Oh, well, here's the solution. So really, if you could do this, that's basically half the question. If you forget the null check and you did all of this, that's 70%. That's pretty good. If you can average that, if you average like a 70 on every question, I would think you could pass the exam. Look, people make mistakes. You can't be perfect. I made mistakes in the exam. Just do the best you can. So, we good to move on? Sure, I can do that moving forward, Christian. That's actually good because I was getting hungry and want to go get a snack. So here's the next question. I'll give you guys a minute to read it, and I will be right back. All right. Are we ready? I is just the name. You can name that whatever you wanted, Katrina. You can name it row. You can name it um, cheese. You can name it literally whatever you want. I is just what's most commonly used because it's small, and I don't know who decided I, but it's just the most common thing. But if you did I could represent the columns in like a 2D array, for example. It just depends on the semantics of the question. But you most of the time it's almost always the left, yes. Yeah, oh, index. That makes sense. I'm stupid. I never thought of that. I can't believe that. That makes a lot of sense. Um, well, position wise, again, it could be anything. It's not always the position. It could be named something else. Am I answering your question? I feel like I'm answering your question.
Wait, I think it'll be easier if I unmute. Is that okay?
Yeah, go for it.
Wait, can you go back to the previous question?
Yeah, sure.
Okay, so when you do so you see the for loop and then
Mm.
right under the code, the line after it.
What about it?
Okay, so when it says free present list and then bracket I, usually the
Mm-hmm.
bracket I is like after like is before the dot and not like after like present name, right? Whenever you're doing that,
I get
that's
what
what I
you're saying.
meant. Yeah.
Yes, yes. But
Okay.
then, of course, if present name was an array itself and you had to access it, there could be another one over here. But
Oh, like
yes,
bracket J or something. Okay.
correct. Yes. Okay, that makes sense. Yes. Does that make sense?
Yeah, it does. Thank you.
Okay, sorry about that. All right, so we're ready for this question. This one's a good one. I like this one. All right. So we have a structure representing a type def structure representing a basic checking account at some bank. Complete the following user-defined function, merge accounts, which is over there. The function will combine two accounts that were already declared with the proper information, so you don't have to worry about that stuff if it's null or anything. So like say they usually tell you. So like we wouldn't need to do a null check here. It will combine the two accounts into one account. Please note that both structs account 1 and account 2 were both dynamically, by the way, these are being passed in, dynamically allocated into the heap space. You will need to properly allocate a new struct in the heap space that will store will represent both their accounts combined. That means the following is going to happen. The names will be merged with account 1 name followed by account 2. Both names will be separated with the word and. For an example, let's say account 1's name is Sonic and account 2's name is Amy. That means the new account name would be Sonic and Amy. Make sure there's enough space to hold the updated name with the word and including the two spaces. And they're not telling you this, but also the terminator. The amounts will be summed together. The ID of the merged account should be the original ID of account 2, and no changes should be made to the original accounts whatsoever. You're just copying information. The function returns the heap address of the new structure. So basically, it returns the new account that's merged together. Does it make sense what we're being asked to do? Any questions? All right. So, if we want to do this, what do you think is the first step? He kind of outlines it for you here. But what do you think is the first step if you want to make this merged account? We need to allocate a new account. Exactly. So let's do that. So we have to use the same structure name. It's account underscore T for some reason. I don't know why they like underscore T. I feel like that's a thing Ahmed does. This might be an Ahmed question. Account, oops, account T. It's going to be a pointer because we're dynamically allocating. And let's call it, I'm just going to call it new. You can call it whatever you want. Now, how would I write this on the right side? I want to allocate a single account. Let's see if someone else responds before I start writing it. Yes, you guys got it. It would be Malik. You could do Calic, technically, but Malik's easier in this case. Malik, and it'd be size of account underscore T. And again, quick self-check. I'm going one step down, so I did that right. Make sense? All right, cool. So now we have, up here, we have a giant, I'm making it big for space. We have the new account. This is new. It's ready to go. Well, okay, technically new is over here pointing to this. But you get the idea. So what do we need to do now? Well, let's look at this. The account itself has a name, an amount, and an ID. So what do you think is going to be easier to deal with first? Which attributes? Yeah, the amount and the ID are the easier things. So let's take care of those right away. So if I wanted to do, let's do the ID first. Well, we're told the ID should just be the original ID of account 2. So now using the structure definition, how would I write this? How would I assign the new account's ID to be the same ID as account 2? I'll get back to the calc at the end. Do we need to make space for it? That's a good question. Do we need to make space for it? No, because it's static. There's no star next to it. Now, I see a lot of you are putting dot. Is it dot or arrow? Are we dereferencing a structure pointer? And if we are, what does that mean? Yeah, yes. New is a structure pointer. If there wasn't a pointer, then it would be dot. But new is a structure pointer, so you have to use the arrow. So it would be new underscore, or why did I say underscore? Arrow ID equals, well, we want to count two's ID, which is called ACCT2. ACCT2 arrow ID. And that's that. Does that make sense? Do you understand why it's arrow versus a dot in that scenario? Okay. So now let's do the amount. We are told the amount should be the sums of the original accounts to get added up together. Sure. So it is arrow. New is a structure. It's a instance of a structure, and it's a pointer. New is a structure pointer. Anytime you access a structure pointer, you have to derefer. You have to use the arrow. That's just how it is. You don't use dot in that scenario. What do you mean creating the function, Fernando? Because that's what we're doing right now. I see what you're saying. No, we're already told in the function that they were all already dynamically allocated in the heap space. You're good. So we don't need to do that. We don't need to make them. We don't need to do a null check or anything. So if new was a yes, this question here. Well, it is technically present listed I is a structure pointer, but then once you're inside of it, this is not a structure pointer, so it's dot. Yes, that's correct. Basically, anytime you see a structure pointer, think arrow. You're almost always using arrow. Does that make sense? So if new was not a pointer, then you would do dot. Does that make sense? Okay. So now someone wrote it out. Perfect. To get the two sums, we would be doing new arrow amount and keeping everything the same based on the structure equals to account one arrow amount plus, oh, whoops, I didn't write the whole thing, plus account two arrow amount. Okay, great. That's done. You know what? I'm going to check them off. We did that. We did that. Okay. Now, this is where we got to be careful. Now we have to do the name. So let's be very careful with this. We need to take the two names together, add the word and the terminator. So the way I think is easiest to do this is to draw it out. Let's use the example given to us. So Sonic, that is 1, 2, 3, 4, 5 characters. Amy is 1, 2, 3. And then and is also 3 characters. And then, of course, the Terminator itself. Don't forget the Terminator. That's 1 character. So in this example, how many characters would I have to allocate for? Yes, we have to do the spaces. I was going to get there in a minute. Yes, we have to do base down here. There's 2 spaces, so we have to account for that as well. So I'll represent those with underscores. So we have 2 more spaces, 2 more things. So how do you think I could generalize this basically? How could I determine what the length is going to be of the overall name in this new account? Because we have to generalize it. It's not Sonic and Amy is just one-time thing. I don't even really know anybody named Sonic except Sonic the Hedgehog. Let me zoom out. Based on what we were given, how can we generalize this? We cannot just do a generalized array. You have to, it has to be exact. It has to be exact. That's the whole point of it because it's dynamically allocated. Yes, exactly. You can call string length on the first account's name, string length on the second account's name, and you can see, okay, and is 3, and then these guys are 3 more things. So you just do those 2 string lengths plus 6. And that's the right amount of space every time. Does that make sense? Okay, so let's do that. Let's do that math and save it because it's going to be very helpful. So I'm just going to call it. Oops. I'm going to call it. Why I want red. Keep it consistent. Int len is equal to. Well, as we said, it'd be string length of account 1 arrow. I think it's called name. Yep, name plus. Oh, we gotta close that. Account. What the hell am I doing? Sorry. String length of account 2 arrow name plus 6. Everyone understand why I just did that one line? The 6 is coming from the null terminator, the 2 spaces, and the word and. Does that make sense? Sonic in this example is this, and Amy in this example is that. Does that make sense? It's 6 every time because we were told you need 2 spaces and the word and then you have to remember the terminator. You can't forget the terminator. So now, can we start copying everything over, or is there something else we have to do? We have to allocate the name, exactly. So we can do that by saying new arrow name equals malloc, because we're dynamically allocating. Now it would be, we called it len times size of char. Does that make sense what I just did in that one line? You could do the math inside the malloc, yes, but I think it's easier to do it separately in something like this. You have to be really careful with parentheses then. Does it make sense what we just did? No, we don't have to make a pointer to the because remember, new is an instance of an account, and then remember, every account has a pointer for a name already inside of it. Yes, you could flip these around. There's no problem with that. Order of operations, 5 times 3 is the same as 3 times 5. It doesn't matter. Does that make sense, though, with the malloc, Christian? Why we don't have to make a pointer? What do you mean we can make a space inside of a structure that's empty? It's not empty. We just allocated that space. We just did that. That's what we just did in this line. Now we have the space for it. You're good. Okay, so now we have that. So now, okay, what goes first? Well, we were told it's account 1 name, then the space, then the and, then the other space, and then account 2's name. So let's take this very carefully. Can I just do a string copy of everything at once? No, you can't. So let's do the first part. Let's do account 1's name. How would I do that? Well, I just said it's string copy. It would be strcpy. Oh, by the way, I should point out, you don't have to include header libraries. You can assume they're included in this. Any question? To be strcpy. Now, Does the destination come first or the source? The destination. Good. So we would say new arrow name, and then we would put account one name because that's what has to go first. Now we have to do the two spaces, a space and in a space. How would I write this? What function am I going to call? That's really what I'm getting at here. Yes. Okay. I wasn't sure if you guys knew about string concatenate. Yes, you have to use string concatenate. If you did string copy again, it would overwrite what we just had. String concatenate, strcat, basically appends it to the end. So that's exactly what we need to call. Exactly. So we would do strcat. Now, again, it's new name. And then we need to hard code, as we were told, quote, a space, pretend there's a space there, and then pretend there's another space. That's why I'm leaving space in between the quotes. Just like that. Make sense? So now we have the first person's name, the space, and in the other space. Now we just have to get the second person's name. So literally, it's this again, except there's two little changes. Oops, I'm going to copy that. This becomes a string cat again, because we can't copy. And then this, instead of account one, goes to account two. Does it make sense, everything we did here for the names, based on what we were told to do? Jeez, I did not mean to do that. Any questions about that? Okay, so are we done? So I can now check this off. We didn't touch the original accounts, but are we done? We have to return new, exactly. Return. I know I went out of bounds here. You'll have more space on actual paper. Return new. And there we go. We did it. Yay. So string, let me show a quick example of what that does. So if we had the word cat, now that's going to be confusing. If we had the word dog, string copy, if I was copying something to whatever is using the word dog, it would erase it and replace it, say with the word fry. But then string concatenate, if you wanted to add something on, so then if we went back to original dog example, string concatenate, when you call that, it would basically then, let's say we wanted to add on the phrase be good, so then it would add on the end be good, like that. And then the terminator would be moved to the end. Does that make sense? The difference between copy and concatenate? Yes, no, maybe so. Okay. So there we go. We did it. And here it is more typed up. They did it in a different order. This question, the order doesn't really matter as long as you do this first and this last. You can flip this around as we did. Not going to make a difference. So, any questions on this question? The dot is when you're accessing a member of a structure that's not a pointer. Think arrow for pointer, dot for the other scenario. No problem. It's hard to say for sure, Elena. Some questions they explicitly stated, some they don't. I would probably, I honestly don't know. It could be like a half a point, a point. I'm not really sure because I don't grade these. Yeah, it is kind of like merging a linked list, sort of, in a sense. That's a little easier, though, in my opinion, merging a linked list. Well, it depends on the type of merging the linked list. So, any other questions? All right, so that does it on DMA. Sorry we're going slow, but I think it's good for you all. So, linked list, section 2. All right, so what is a linked list? Well, it's like an array, except the size is variable. It can change if needed, and it's not contiguous in memory, which is basically what an array is. An array is contiguous in memory, and the size can't change. The drawbacks is that the runtime is typically worse unless you have pointers to the front and the back. Binary search is basically impossible in it unless you sort it, which is very difficult to do. Inserting to the head is always constant. Inserting to a tail is linear runtime unless you have a pointer to the back. Searching, no matter what's going to be constant because you got to go through everything. And sorting is difficult, as I just said. I'm going to go through this pretty fast because I want to just get to the questions again. Types of linked lists, singly, it's like a line at the cafeteria. You're behind somebody, that's like you can point to. A double linked list is basically you can see the person ahead of you and behind you. And then a circular linked list is once you get to it's like a singly linked list, except at the end, you can see the beginning person as well. Imagine a circle. It's like literally like a circle. Traversal, you always got to go to the head. Usually, it's good practice. A while loop is your best friend here, not a for loop, because you don't know how long you're going to have to run through the linked list. Especially also since you got to check. Usually, you have to check if the loop is equal to null, because usually going to the tail like that. Then you perform the operation, and then you can usually then manually increment your pointer. You're a traversal pointer. So again, linked list ones, there's traversals, there's tracing, and there's coding. Pretty self-explanatory in my opinion. Common mistakes, you pretty much always have to do a null check with a linked list. Make sure you do that. And don't free a node you're on before traversing, because if you do that, then you're going to lose access to whoever that was pointing to, i.e. the rest of the list. You got to work your way from the back of the list to the front when freeing. So here's the question. Any quick questions on any of that stuff I just said? All right. So let's do a tracing one. I'm going to give you guys a couple minutes to try this one on your own. I want to see if you guys get the answer. There we go. There's all the space you need. Give it a try, and then we'll go through it in maybe like 3 to 5 minutes. All right, are we ready? Christian, a doubly linked list, each node has a pointer to the node in front of it and behind it. Unless you're at the front of the tail, then that's not possible. One of those. But every other node has a pointer to the front and the back. Or the one in front of it and the one behind it, excuse me. All right, when you guys finish, tell me what you got in the chat. Plus plus I makes no difference in I plus plus in a for loop. It's the same thing. I know technically it's not, but in a for loop, it will be the same thing. If it was separate, then it'd be very different, yes. But in this case, it's not. Okay. Got one answer. See if we can't get a couple more. Got a second answer. It's okay, Jesse. See if we can't get one more answer. Seems like the majority of you did get the right answer. It is 75684. So let's go through it. It's okay, Elena. It's okay. You're still practicing. This is why we're here. Let's go through it. So suppose we have a singly linked list, aka the easy one, implemented with the structure below and a function that takes the head of a list and an integer. Okay, great. There's a function. They always call it mystery for some reason. That drives me crazy. If we call head equals mysterious, so basically the result of this function, by passing in 3 on the following list with 3 with the following list, show the list after the function is finished. Okay, so let's draw this out. We have a list 6, 8, is it 745? 475. 4, 7, 5. Move this out so it's better. And then the head is pointing to 6. And we know that k is some integer. K equals 3. So let's just take this slowly and go through it. So, is k equal to null? Or, I'm sorry, is k equal to 0? No. Or is the head equal to no? No. So this base case here, or I guess we don't call it that, this base case is false. So we skip it. So now we're doing a loop. I is equal to 0. I is less than k. So that means we're doing this k times, which in this case is 3. Plus plus I, same thing as I plus plus in this scenario. So here we go. Now we got to be careful. We're making another node pointer and pointing it, we're calling it cur and having it point to the head. That, in this case, that is 6. Then, while current next does not equal to null, current equals current next. So we're just incrementing it through. So really, let's go through this. Is current next equal to null? No. Move it forward. Is current next equal to null? No. Move it forward. Is current next equal to null? No. Move it forward. No. Yes. Now we stop. Now that we're here. Current next equals the head. So what that means is 5 now points to 6. Then current equals current next. So where's current going to be pointing to now? What number? 6, exactly. So now current points to 6. Then, now we're at head equals head next. So now, head is going to be pointing at 8. And then current next equals null. So now 6 isn't pointing to anything. So if you want to make this a little more cleaner, that just made the list into this, that one iteration. Does that make sense? So what just happened here? Well, if you wanted to, you could just do the other iterations, but if you also get the pattern, you might have to do it a couple more times, but once you see the pattern, you should be able to you could pretty much easily finish the question right away. Can someone tell me conceptually what just happened here? Exactly. The head goes to the tail. So if you keep that in mind and we did this 2 more times, well then the second iteration, 8 is going to go to the end. And then the third iteration, 4 is going to go to the end. I'm just doing the shortcut for time's sake. And then there you go. After you do the loop, you return the head, and that's it, which is how you get the answer of 7, 5, 6, 8, 4. Does that make sense? And again, you could grind through it 2 more times, but for time's sake, I'm doing it the shortcut way. Any questions on this? All right. Let's do a coding question. This one, oh, there's the answer. You can look at that later. This is a good one. All right. The structure of a node of a doubly linked list, so it has a next and a previous pointer, is shown below. Oh, I'm sorry. You guys got to read it first. Take a second. I forgot that was requested. My apologies. All right. We're going to write a function that takes in the pointer of the head of a doubly linked list called the head and a pointer to a node in that list called me, removes that node from the list, and then returns a pointer to the head node of the resulting doubly linked list. You may assume that both head and me are not null and that me is somewhere in the list, basically. So we got to be careful here. If you think about it, let's draw an example list. Let's do 7, 8, 3, 6, 2, 4. And each of these nodes point between each other. So if you think about it, how many scenarios are there, do you think? Like scenarios of like deleting. Yes, there's 3 situations. Exactly. You're either going to delete you're going to delete the head, the tail, or somewhere in between. So we really just got to take care of each of those um, scenarios. So, and the last 2 are kind of intertwined with each other, but let's take care of the easy case first. If we're deleting the head, what do we have to do? So in this case, the head is 7. This is head. If the head is 7, conceptually, what would we have to do? Exactly. We just move the head pointer up 1, and then we would free the node. That's it. So if I wanted to do that, how would I write that? Exactly. If me is equal to the head, well, then we just move it up. Now, do I want to free me yet? Should I free me at this scenario? we already have a temp pointer pointing to the head and me, so we don't have to worry about that. That's given to us in the function. Yeah, we don't want to free yet because there could be other scenarios. We just got to be careful with the pointers. So now we got to be careful here. So me, in this case, we're pretending in the example we just did, we said this was also me. This is me. So if we want, now we have to deal with the pointers. So then how would I update the pointer there? Like, what do I have to update basically? We don't want to free me yet, because if we free me, we're going to lose access to these 2 pointers here, and we need to update those first. We need to free at the end. Because basically, if we don't update the pointers right away, you're going to have garbage pointing to 8 and then 8's previous pointing to garbage. That's not going to work out well. You don't want to necessarily set them to null, because remember, this is going to be a generalized case. Is what if now let's pretend instead what if me was 3, and forget the head. What if this was a generalized case? What would we do here? Not head previous equals null. Okay, we have some. Yes, you got one of them. Me's previous next. Well, first, can we just check it? Or can we just do that? Or do we have to check it first? You always got to check it. So let's take care of me's next pointer first. So let's say, okay, hey, if me's next pointer, if me arrow next, if that exists, then we got to update it. So then if I wanted to update the next pointer, how would I update that? Well, this is actually not next. This is actually kind of trippy. If you think about it, when I just wrote, if we're checking if a next exists, are we going to be, yeah, me is 3 in that example. If we're going to update, if we're checking if the next exists, do you think we're going to update me's, like a previous pointer or a next pointer? A previous, exactly. And yes, you got it. If you think about it, we need to have, in this example, 6. If we're checking if this link exists, well, then we need to check if we have to have the node after it point to the one previous of me. So basically, we need to break this link here and make this. Does that make sense? So if we want to do that, then we can do me next prev equals to me prev. Does that make sense what I just did there and why that is? Yes. So if you think about it, Ryan, this is what we had before. Now, if we're checking if there's stuff after me, then that means we need to bridge the link for the stuff afterwards to be able to access the stuff beforehand. And the way to do that is, well, okay, if this stuff over here exists, then we need to have the node after me, so in this case 6, points its previous point to whatever comes before me. In this case is 8. So we need to update this pointer I'm erasing to point from 6 to 8 instead of from 6 to 3. Does that make sense? Does it make sense, Ryan? And then, yes, as you guys are thinking, we have to do the exact same thing for the opposite scenario. So we need another if statement. Because if you think about it, this might not be right. immediately obvious, but if we do the two separate if statements like this will take care of the head and the tail scenarios as well, all in one. If me prev is not equal to null, then me prev next equals me next. So in the scenario, then what that would do is we see that me has a previous. It would break this link between 8 and 3, and now 8 would point straight to 6, essentially bypassing 3, which is exactly what we want to do because we're deleting it. Now, the only other thing is, let me just show you how this would work on the head scenario. So if we're deleting the head, if me was the head, I'll make this in green just for a second. If me is green now, the green me, we would increment the head, and then we're like, okay, me has a next that exists, so then it would break up me's next prev 8 is going to point to me's previous, which in this case is null, which is exactly what we want. I just erased the wrong thing. Sorry. This is going to point now to null, which is exactly what we want, because the previous would go to null. Then we check the other way. Well, me's previous doesn't exist, so this would be skipped. And then as you can picture it, the opposite would happen if me was the tail instead. Does this all make sense, what I just explained? I know it's a little confusing, this one. Questions, comments, anything? Okay, glad it makes sense. So now, okay, so you see why, though, you do the separate if statements instead of like doing one for each scenario? It's more generalized and it's a lot easier that way to not mess something up. Correct. It's a way to do two in one instead of doing it all individually. Correct. If you did it individually, it's possible to mess it up. You could do it that way, yes, but it's going to be a lot more complicated that way. You got to be really careful if you do it that way. So then, what's the last steps? Free me. That's part one. That's easy. Free me. And then what's step two? Or is there even a step two? Are we told to return anything? Yeah, we got to return the head because the head might change. Return head. So that's it. But yes, if you wanted to, you could say like, okay, hey, if me is equal to head, that's an easy way to check. But if you wanted to check if you're in the middle, you'd have to check, if me next is not equal to null and me previous is not equal to null, you'd have to do that. And then the way to know if you're at the tail will be if me next is not equal to null and me previous, or I'm sorry, I said that wrong. The way you would check the tail is if me's next is equal to null and me's previous is not equal to null. That's how you check the tail. The way the last two if statements take care of multiple scenarios, because no matter what, if there's a next, it will link everything behind it. It will link that stuff afterwards to the stuff behind it, and vice versa. You do not need to do that because technically you would assume that the old head is pointing, its previous is pointing to null. If you did, it wouldn't be wrong, but you don't need to do it technically because 7's previous, it's there. I just didn't write it because it's pointing to null. It's technically there. It's just pointing to null. Does that make sense? Does that make sense, Alex? Okay. All right. Any other questions on this? So again, yes, you can split it up if you wanted to, but this way's a lot less confusing. So that's a good challenge. Try out the other way on your own later. See if you can get it to work. Try it with examples like I did. All right. There's what I just did. All right, last question. This one shouldn't be as bad. I'll give you guys a second to ponder over it. The if conditions for the other methods. So I'll go back for a quick second. The nice thing is the head scenario, you're given the head, so you can just check that like we did. But then if you want to check if you're in the middle, you would check if me's next pointer is not equal to null and if its previous is not equal to null together. And then if you want to see if you're at the tail, then you would check if me's next is equal to null and me's previous is not equal to null. Does that make sense? Excuse me. No problem. All right, ready for this one? This one I don't think is as bad as the other one. All right. Complete the user-defined function that reconstructs the structure of a singly linked list. The function will take a pointer to the head of some list along with the number of nodes n, and move the first half of the list to the back of the list while the other half moves up to the front. For grading purposes, do not use recursion. The function will return the new head of the list. You may assume the original list has an even number of elements, which is helpful, and is not empty. The following figure shows the scenario. So basically, all the stuff halfway in the list gets moved to the back. That's it. It's literally that easy. Make sense? So now let's think about how we would do this. If we have 1, 2, 3, 4, we have to get, if you think about it, how would we have to do this? How could we do this? How can we move basically the first half to the back half? And this is even, so this is a little easier. You're on the right track, Ryan. Actually, yes, you're right. You're exactly right. My apologies. Yeah, basically though, conceptually, we just have to have the tail point to the head, and then whoever's in the last space or the halfway space, just have their next point to null. That's it. That's all you have to do. Because technically, this list, even though it looks messy here, that becomes 3, 4, 1, 2. Does that make sense? And that's exactly what we want to do. So we got to be really careful here. How do you think we can do this? How are we going to get to? Well, yeah, that's the whole point, but we have to get to that halfway spot. That's the trouble. How do we get to the halfway spot? Exactly. We just loop through the loop and over 2 times. Exactly. So, well, first let's make a pointer to the end because that's going to be helpful, the new tail. So node, I'm going to call it tail equals the head. Because remember, in this scenario, as we just saw, 1 was the head, and now it's well, no, it's not becoming the end, but like it's going to be the start of the end. Does that make sense? Maybe I don't like the word end or tail. Let's call it start. I think that's better. So that's going to represent the first node in the back half. Does that make sense? The new back half. Yes, you could use a while loop. Absolutely. So now we We just got to get to that halfway spot. We got to get to 2 in this example. So as we said, for int I equals 0. Now, what's I going to be less than? You got to be really careful here. Let's draw out these indices. I know this is an array, but this is basically how it's going to be. This is index 0. This is index 1, 2, 3. If you do n over 2, I is less than n over 2, it would go to 0. Oops. It would go to 0. It would go to 1. And then it would stop on 2. Is that what we want? Do you want to stop after at the new head or before the new head? Before, because we need to update this pointer here. So you got to do n minus 2 or n over 2 minus 1, because that will do 0, 1, and then stop in this example. So I is less than n over 2 minus 1, then parentheses just to be safe, plus plus. So then what are you going to do? You just move that up. You move start forward. Okay, so now at the end of this loop, let me draw back the original example. So now we have start here, and here's the head. Okay, cool. So now what do we need to do? What's the next step? Should I make 2 points to null first, or should I update the new head first? Yes, you have to update the head first. Because if you had 2 point to null first, you're going to lose access to all this. That won't work. So we can make another pointer. Oh, oops, this should be called, I just realized this should be called up here a node t pointer. So it's consistent as s. So node underscore t up here. Now that becomes, I'm going to call it new head. Now what would that be equal to? Based on what we're using. How can I access the new head? Who's going to be the new head? 3. So how can I access 3 based on what we have? Start next, exactly. New head equals start next. Good. Okay, so let me draw that in. Start next. Okay. Now what's the next step, you think? What's the next step? Any ideas? Shouldn't we break up that link between 2 and 3 now? We need to have 2 point to null, right? Yeah, start next equals null, exactly. Start next equals null. Okay, so now that's gone. Okay, now are we done? No. What do we have to do now? Right, we have to put it to the back, but how do we do that, Christian? Well, we can't, in this example, we know it's 2, but what if there's 5 things here? You can't just do next. Yes. We have to loop to the last node and then make the connection. We don't know how many nodes there could be, so we have to loop through it. Does that make sense? This is a very small example of this. If there's 20 things ahead, we got to make sure we get to the end. Does that make sense? Now, should I increment in the loop? Should I increment? Oh, I'm sorry. This should be called this is now called new head as well. I'm going to call it that instead. This is new head. So now, should I increment new head in the while loop, or should I do a different variable? Yes, you have to make start next equal to null, because otherwise start next is still going to point to the new head, which is wrong. You have to do that line. So now, how do you think? Do you think I can? We need to loop through. We know that we need to loop through the right half to get to the end of the list. Do I need to increment new head, or do I need another variable? There are two different answers. Well, it's one of those two. Exactly. You have to do another variable because 3 is our new head. We got to leave that there so we can return it at the end. So we can make a new pointer. I'm going to call it Walker, my good old favorite. That's going to be initialized to the new head because that's where we're starting. So we're here. So here's Walker. Now, if I want to get it to the end, how can I do this? Well, you need a loop, as we said. Should I use a while loop or a for loop, you think? A while loop, because you don't know how many times you're going to go. While, what am I going to write here? Walker what? Do I want to put while Walker does not equal to null or while Walker next is not equal to null? Think about it. Here, this will maybe make it a little more easy. You have to do Walker next, exactly. Because if you have Walker go out here to the null space, you're going to not be able to connect 4 back to the original list. Does that make sense? So yeah, so it'd be Walker, arrow next does not equal to null. If that's true, just increment it up. Walker equals Walker, arrow next. Why did I put that parenthesis there? That's not supposed to be there. There we go. Okay, now we're really close. So now we got Walker where we want it to go. What's next? What's the last step we need to do conceptually? Oh, you guys already got it anyway. We need to have 4 points to the original head. So in this case, Walker's next needs to point to the original head. Exactly. So Walker, arrow next, equals the head. So now we have it all ready to go. So now what do I need to return now at the end? Return the new head. Exactly. Return new head. And that's it. Now that I think about this too, if you wanted to, you could move the tail. You could have 4 point to 1 first and then break off that link in the middle after. That'd actually probably be a little easier. Now that I think about it. Yeah, you could absolutely do that too, Alex. So yeah, another way of approaching this, you just loop through once, bring this over here, and then if you knew this was the head, you just move the head to the right position, and then you can return the head. That's another way of doing it. There's many ways to approach this. So, any questions on this? All right. That is the end of linked lists. Let's keep this party train going. You're probably going to go over 4 o'clock. I apologize. I was not surprised. I'll try my best to get this done as soon as possible, but I'm hoping this pace is good for you all. Am I going too slow? Okay. All right. So now let's do section 3 today, queues. Oh boy. A queue is basically just a linked list, except it has a first in, first out property. My best analogy to this is you're in line somewhere for pay at the store, get food. Think of that as a queue. That's what a queue is. The code could be a linked list or an array. In this case, we're doing here is the linked list version. It's a linked list, except the queue stores the front and the back, or the head and the tail, same thing, just to make it a lot easier. If you don't have that, it's a lot more difficult to do stuff. If you have these 2 pointers, enqueuing and dequeuing is really easy, but no matter what, you still have to go through the whole queue if you want to traverse through the whole thing. No skipping the line at Disney. That's funny. Enqueue is putting something in the queue. Basically, what you have to do is make a new node, set the original tail equal to the new node, and then make that equal to the back. And then if you're dequeuing, you grab what's in the front and just increment the head. Pretty self-explanatory in my opinion. Now the array is gross. I know it's still constant operations, but you got to be careful with checking the number of elements is less than the size of the array. You always insert the front's always at front plus number of elements mod size. That's just how it is. There's a reason behind that. You can see it. You can play with that later. And then if you're enqueuing, you also increment the number of elements. Otherwise, you just decrement the number of elements, hold on to whatever's at the front, and then increment the front pointer itself by 1 mod the size, and return what was at the front before. This is just quick review, going through this fast so we can get to the questions. And now we're at the questions. Any questions on what I just said really fast? All right. Let's do a conceptual question. I'll give you a minute to try this one out. This one isn't too bad, I don't think. This one's really just understanding, do you know what a queue is? Give it a try for a minute, and then we'll go through it. You know what? I'm going to try something. Yeah, I've never done this before, but let's give it a shot. Here, I'll set a timer for 3 minutes. You think 3 minutes is enough? Ooh, you can pick a sound. Okay, in 3 minutes, this sound called "and the winner is going to play. After that, we can go through it. That's funny. I forgot there were timers. I don't know if you all can see that or not, but we'll go through this once this timer is over. I wonder if that's going to play in the recording later. It'd be really funny. All right, so let's go through this. I really don't think this is too bad. You're just going through. Basically, you understand how a key works. Yeah, it was Disney movie. Like that's funny. Pretty appropriate for this question, since this is all Disney. So consider the following code that represents a first in first out queue that holds a list of superheroes as strings. Show the contents of the queue at each point commented A, B, and C. You're just basically NQing and DQing. That's about it. So we're first NQing Hawkeye. And well, and at the beginning, the front is the rear, since he's the first one there. Cool. So I'll check that off. Now we're NQing Thor. Cool. Now we're NQing Spider-Man. I'm going to write him as SM. Don't do that on the exam. I'm just doing that for time. Now we're DQing. So who's going to come out of the queue? Hawkeye or Spider-Man? Hawkeye, exactly, because you DQ from the front. So he's gone, and you move these two guys up. Now we're NQing Wanda. And now we're NQing Vision, and then we hit point A. Now we stop. There's part A. And then you just copy it over and keep going. So now we are NQing Miss Marvel. So she's going to come down here. I'm just going to write her as Miss.M. Don't do that on the exam. Make sure to write the full name. Then we're also NQing Doctor Strange. I'll squeeze him in. Dr. S. Okay, now we're DQing twice. So Thor and Spider-Man get obliterated by Thanos, apparently. We move these two up. Then we move these two up. Cool. Now we're NQing Loki. Yeah, you always copy it over because you got to go through the whole question. Now we're NQing Captain Marvel. Oh, whoops, I did not mean to write Loki over here. There we go. Now we're doing Captain Marvel. Now we're DQing twice again. So Wanda and Vision get obliterated by Thanos. And then we just move them up. And then looking back, now we're at part B. So now that is the answer to part B. Now we move forward, copy everything over and finish it. So now you need to copy everything over because it's still a queue. This is all supposed to be one big queue. It's just they're asking you at specific points like, hey, what's the queue in this stage and that stage and that stage? But overall, you're using the same big queue the whole time. Does that make sense? It's kind of like infix to postfix. It's the same thing. It's like you're using the same stack the whole time, but in the middle, like they ask you for like, hey, what's the stack at this stage and that stage and so on. So anyway, let's finish it. You NQ Iron Man and then DQ. So I'm gonna just do this the easy way. That would be the DQing, and then Iron Man would be at the back. And there you go. That's it. Any questions on that? All right. That one's pretty easy, in my opinion. There it is. All right. Now we got a coding question. Take a look at it for a minute, and then we will go through it together. You know what? I'm going to set a timer for a minute. How about that? I'll do a different sound effect this time. Sorry, I almost stopped recording the meeting by mistake while trying to clear that out. That would have been bad. Okay, we're still recording. We're good. All right, let's go through this. A regular queue only supports adding an item to the back / the tail of the queue and removing an item at the front / the head of the queue. A common method of implementing the queue, as we said, is a linked list with pointers to the front and back, two separate pointers. If this method is used, it's relatively easy to add the functionality of it. It's easy to do all that. Given below is a partial implementation of this data structure, commonly called a DQ. That's the stupidest thing I've ever heard, in my opinion, because why would you call a queue a DQ? That's very confusing. DQ is the operation, not the name of the queue itself, you know? These are the kinds of curveballs I try to throw at you. Fill in the function that adds an item to the front of the queue, not the back, the front. You may call the make node function, and you may assume that my DQ points to a DQ that exists, though it may or may not be empty. All right, so basically, we're making an enqueue function, except instead of adding to the back, we're adding to the front. That's literally all it is. Does that make sense? Okay, so if we're enqueuing, what is step one? We don't need to check if it's null yet. If you're adding something to a queue, yeah, you got to create the node for it. It has to have a node. You got to make a node for the item. So, and look at that. We're given a function that does that for us, and we're told we can call it. Well, that's pretty handy. So I'll call it node, and it is just plain node in this case, looking at the structure. Node with typed F, so that's nice. So node pointer, I'm going to call it new equals make node, passing in the value provided. Does that make sense? I made the new item. I made what's going to be added to the front of the queue. Make sense? Okay. So now what do we have to do now? Think about an enqueue. Can you always just update the pointers right away? Do you have to check something? Check if what is null, Alex. Val will never be null. It can't be. That's an integer. Right. You have to check basically if the queue is empty. If the queue is empty, then new is going to be the front and the back together. Does that make sense? So we can do that. So we can say if my DQ, now looking at the structure, in this case, since we're inserting to the front, it's probably best to check the front, but you could technically check the back too. I don't see why that would be wrong. But if my DQ's front is equal to null, well, then what are we going to do? Well, then new is the front and the back. So then you would just say my DQ arrow front equals new. My DQ arrow back equals new. Now, is that it? Or am I missing something for this scenario? Think about it. If I'm inserting into an empty queue, what's next? Anything? Right, return it, but you don't have to really return anything here. So no, you're done. We did it. We inserted it. That's basically it. We're just moving the pointers around. So that's that. Well, then otherwise, what's the other scenario? The queue isn't empty. So then Now, how would I update the queue to reflect new? Imagine this is a linked list. So here, I'll just make this. We have five and well, this is backwards. Five, 3, and 8, and we're inserting 7. What do I do now? And 7 is new, and this is the front. Well, what do I do now? Right, we need to change 7 to the front. Now but we remember this is a linked list. So do I have 7 point to 5 first, or do I have the front become 7 first? That's right, exactly. We have to have 7 point to 5 first before we update the front. Otherwise, it's going to be wrong. You'll lose access to it. You won't be able to make that link basically in the list. So you would say new next equals my DQ arrow front. So now that link is made. So now what's left? We just have to basically make the new the head, or the new becomes the front. So then we say my DQ arrow front equals new, and that's that. Now this, oops. There you go. Done. Make sense? No, you can't do that the other way around. That would basically copy the value of that would basically copy 5 to 7. It has to be the way we wrote it. Does this make sense? Any questions on this? Yeah, I know. See, this is why they try to get you. Stuff like this. All right, let's do the next one. There it is. That's literally what I just did. This one's a good one. I like this one. This one's pretty new, too. So I'll get our trusty dandy timer again. Pick a new sound. Golden ticket. That sounds interesting. Here, I'll give you guys 90 seconds this time. All right, go for it. Oh, whoops. I really wonder if you're going to be able to hear those in the recording after. All right. We ready? All right. We are going to simulate a simple battle game involving players in a queue. The battle game has the following rules. The game involves several battles. Each battle will involve the two players in the front of the queue. The winner of the battle is determined by figuring out who has more HP. In this case, that both players have in the case that both players have the same HP, the second player is the winner of that round. The loser of each round is removed completely, and the winner is added to the back of the queue. The game is over while there is one player remaining in the queue. I guess my apologies, I forgot to show all this stuff to the left. Complete the following function battle game that simulates this game. You must use the provided following structure and helper functions that have been implemented already. The function should print the name of the player that won the game at the end. It is guaranteed that the queue pointed to by game queue has at least one player in it. All right. So, how do you think we can do this? What do you think is like the most overwhelming point, like the most important point that we were told? What do you think of those like bullet points? Which one's the most important? To me, the biggest thing is that the game is over when there was one player in the queue. Yes, because if you think about it, how could we use that while writing this function? Exactly. We're going to put everything in a while loop that basically does the game until there's only one player left. Does that make sense? So how can I do that? Well, while we have a size function, that's nice. Size with game queue is greater than 1. Okay, so now we're going to do all this stuff. So now let's look through this again. We have to use the two front players in the queue. So how are we going to get them? Well, we take them out of the queue. So player underscore T, I'll call him P1 equals DQ of the game queue. Now we do that again, except for player 2. Great. Now we have both players. Okay, now what? Somebody tell me. Really, we just got to take care of the two scenarios, right? So, yeah, we just check the HP. So, and we can see that in the player structure that they have that. And really, all we have to do is just see if player 2's is greater than or equal to player 1's HP. Because if player 2 has more HP or the same, he wins. Otherwise, player 1 wins. So, if P2 arrow HP is greater than or equal to P1 arrow HP, well, then player 2 wins. And whoever wins gets put back into the queue, and then the other player gets deleted. So then we would end queue with the game queue P2, and then we have a delete player function. Oh, wait, what did I not do? Oh, I see. Thank you. We're going to parenthesis. So now we have a delete player function. So we can call that delete player. And that just passes in the player's pointer. So P1. Okay, great. That scenario's done. Otherwise, it's literally the opposite. So I'm just going to copy this. I wish you could do this in real life on paper. That'd be really nice, wouldn't it? We're deleting P1 in this scenario because they would lose. Or, I'm sorry, we put them in and then we delete P2 in this scenario. Okay, great. So that's the outside of the while loop. So now what do we have to do at the end? Anything? What do you mean if it's vice versa, Jesse? Are we returning anything here? There are two things at once. If player two has more or the same HP, Jesse, then they win. So they get back put back into the queue. Does that make sense? That's why it's the way it is. Does that make sense, Jesse? Because yeah, and that's what I'm doing. I'm adding if player two, if they have the same, that's why I did greater than or equal to, then I'm putting player two back in with an NQ. You're good. We're storing the DQ result because we have to take the two players out of the front of the queue and then use their attributes as we're told in up here. Each player will involve the two front players in the queue. No problem, Jesse. Does that make sense what I just said though, Ryan? No problem. Okay, so yeah. But so now finishing up, we're not returning anything, it's a void function. We're told we should print the name of the player that wins. Yeah, so what we can do is just take them out. Oops. Player underscore T win, calling it that equals DQ. What's it called? Game queue. And then at the end, I'm going to make this really tiny. We print F percent S wins with a new line. And then to access that, it would be win arrow name. And that's that. There we go. Yes, you could do that too, Deborah. But they want you to use the functions. You're told you must utilize them reasonably for full credit. You got to make sure you do everything the question asks you to do. Yeah, see, that's an easy thing to forget. I don't know if they'd really penalize you for that, but it's better to be safe than sorry. But that's it. Does this make sense to everybody? Any questions? This one wasn't too bad either. You ready to move on? I guess. Yes? No? Someone give me something. Do you mean to review we already did, Matthew, or one to do? These are already kind of in. Which one did you want to go over? What topic? Cues? Linked list. If we have time at the end, we can do it. Is that okay? Well, that one's. I think I remember that one. Let me look at that real quick. That one I remember was pretty difficult, I think. Let me see. Yeah, that one's pretty doozy. If we have time at the end, we can do that. Is that all right? Um, Probably like an hour ish, a little over. All right, cool. So let's just finish these. All right, stacks. I don't think will take forever, well, especially in fix to postfix, because there should be. Yeah, stacks is not going to take too long because two of them are conceptual. Well, I guess we're not coding. How about that? So stack, as you know, it's the exact same thing as a queue, except it's last in, first out. Think of it as a stack of plates. Pushing, when you're putting something on, is constant. Putting on top. Popping, you're taking something off, also constant. Applications include infix, postfix, backtracking, function call, syntax, parsing, and valid parentheses, and a bunch of other things. You can also do it, you mainly do it in an array. If you push it, you just increment the top by one and put in the new elements. Pretty easy. Decrementing, you just do the opposite while saving the item you took. But you could, oh, I thought you were going to say you could do this in a linked list, but I guess not. So forget about that. Infix to postfix is probably the biggest thing you got to know, and postfix evaluation. You got to make sure you remember the priority. Priority is the biggest thing. You know, priority, remember, if I remember correctly, it's been a hot minute. The caret for exponent has level 3, the highest. Multiplication, the star, and division, the slash have level 2. Then plus and minus, level 1. And then parentheses have level 0. But parentheses kind of separate things. So make sure you know the priorities. There's that whole process to doing infix to postfix. You traverse the whole. Oh yeah, there's the priority. There you go. They're saying level 1's the highest. I said level 3's the highest. Just know the order basically. Exponents first, star, slash, then plus minus. But basically, you just go from left to right. Remember, you immediately put operands or numbers straight to the postfix expression. Otherwise, you will add operators onto a stack based on the priority. You take whatever you're reading in your hand. If the thing in your hand has a smaller priority, let me say that again. If the thing in your hand has the biggest priority than the thing already at the top, then you just put it on. Otherwise, you keep popping things until the thing in your hand has the highest priority. Then parentheses, you treat them as nothing. You just put an open parentheses onto the stack, and once you read a closed parenthesis, you just keep popping everything until you hit a closed parenthesis, or an open parenthesis, excuse me. Parentheses, you never have parentheses in postfix. Never have parentheses in postfix. It's a good self-check. Make sure while you're doing this, you're doing an infix to postfix question. I've made the mistake before of doing infix to postfix and then realizing it's postfix evaluation. So, this one's just a matter of following the process. That's all it is. So, then postfix evaluation, it's kind of the opposite. You keep pushing operators and operands from the postfix into the stack. When you hit a number, when you hit an operator in the stack, you just, oh my God, let me say that again. When you hit an operator in the postfix expression, you pop the two things at the stack. The first thing is operand B, then it goes A. You do A, the thing B, so you do like A plus B, A minus B, A divide B, etc. And then you place the result back into the stack. Then at the end, you should have only one thing in the stack, and whatever that is, that's the answer. What was I going to say? I don't remember, so I guess it wasn't important. So we're going to do infix to postfix, following the stack. Infix to postfix is very common. So is postfix evaluation, but infix to postfix is more difficult. So would you guys rather take a minute to try it, or we just go through it right away? Okay. I'll give you like 3 minutes, since this does take a minute. I was 3.5 minutes down. I think that'll be good. All right, go for it. Good luck. All right, are we ready? Let's do this thing. All right, so it's just a matter of following the process. So we start off with 9. That's an operand, a number, go straight to the postfix expression, cross it off. Now we come across a star. There's nothing in the stack, so I'm just going to put it right in the stack, no problem. 2 is a number, go straight to the postfix. Now a plus. Now, what's the priority of a plus? Is it higher or lower than the multiplication? It's lower. So you have to pop things until the plus is the higher priority. There's only one thing, so we're going to pop out the star, put it on the postfix expression, and then put in the plus. Okay, 4, straight to the postfix. Okay, now we have a minus. Can I push that into the stack, or do I need to pop the plus? You got to pop it because the thing in your hand, in this case the minus, has to have the highest priority, and it does not have the highest priority over a plus. So that gets popped, put on the postfix expression, and then we put in the minus. 3 goes straight to the postfix. Then we have a divide. That can go straight into the stack because it has the higher priority. And there we go. Now we're at part A. Now we copy these two over and continue. Okay, a left parenthesis. What do I do with a left parenthesis? You just push it in, it doesn't matter. Put it on it. Great. Okay, 6, postfix, star. Now, can the star go on, or does the divide need to be popped? Yes, the parentheses like a barrier to shield. It doesn't matter what's below the parenthesis, so the star can go on now. Another left parenthesis that gets pushed in, no questions asked. 4 goes straight down here. Minus, they can go in because of the parenthesis. 3 can go straight down. Okay, now we're right parenthesis, so you keep popping until you hit a left parenthesis. In this case, it's just a minus that was popped. And mind you, we're not putting any parentheses onto the postfix expression. Now another right parenthesis, so now the star comes out. Now we hit a plus. So what would I have to pop here to get that plus into the stack? Correct. Well, not plus. Do you mean the minus, Ryan? Yes, you pop the division and the minus. That would keep the priorities straight. And then we put the plus in. And mind you, keeping the same order. Now we have a 1. And then we have a star, which can go straight in because it has a higher priority than the plus. And now we hit part B. Now we copy this over and keep going. You're good, Run. Left parenthesis, you go straight on. 7, straight to the postfix. Minus, parenthesis lets it go in. 4, straight to postfix. Right parenthesis, pop till you hit a left parenthesis, so just the minus. We'll go to the postfix. Like that. Divide. What needs to get popped here? Yeah, you have to pop multiple expressions if needed. Yes. In this case, we're just going to pop the star. That goes to the postfix. Now we put the minus in. Where the hell is the C? The C is after the parentheses and before the 5. Okay. Now we push a left parenthesis. And now we hit part C. So you might think you're done, but you have to finish the postfix expression. So leave the stack alone and just copy it on the side. Okay. 5, straight to the postfix. Plus, and go in. 6, straight to the postfix. And then right parenthesis. That gets rid of these two. The plus goes down. And then, since you're done, you have to remember to pop everything. that, and that. Which, let me quickly check. 9 2 star 4 plus 3 6 4 3 minus star. Divide minus 174 minus star. Yep, that is the correct answer. There you go. Any questions on that? Now, sometimes they don't give you enough boxes, or they give you more. I'm sorry, they give you more boxes than you need. This one, you got the correct amount. Any questions about this? Did the process make sense? What's up, Christian? You mean like the stuff on the side? Yeah, this is part of the answer here. This is three of the points. Well, you could write the stuff like what I would do on the exam probably is like have like write small and work your way through with like crosses, cross things out like that, or just have a giant stack on the side you keep using, and then when you get to each part, fill it in. You have to make sure this is ready to go because each of those are worth a point, and then this is 7 points here. You will never have to convert postfix to infix. If you see that on an old exam, skip it because it's not taught anymore and will never be on this exam. We don't close the parentheses for end of C because its corresponding right parenthesis was after C. So I used it to finish the question, but for the stack at part C, you leave it as where it was. It will either always be infix to postfix or postfix evaluation. There is no postfix to infix, although I've heard it's pretty easy actually. I just forgot how to do it. Any other questions? Postfix evaluation, where it's like, you have this kind of expression, you have to evaluate what the final number is. You should have been taught that in class. So, all right, there's the answer. Now, we're going to do just a normal conceptual one. This is what AJ put in here. I guess if we have time at the end, maybe we could do a postfix evaluation, but for now, I'm just going to focus on these. So, why don't you give this one a shot? This one's pretty similar to the Q one, the superhero one. Give it a try, and I'll do another 3.5 minutes with a different sound again. That sounded like something straight out of the Ratatouille movie, doesn't it? All right, let's do this thing. Y'all ready? So it's just built into Zoom, Christian. That's the funny thing. All right, so we're just following through, pushing and popping in a stack. That's literally all it is. All right, so first we're pushing in 12. Go on the bottom. Then 5 and -8. And now we got to be careful here. Now, so that just reminded me, when doing infix to postfix and postfix evaluation, you shouldn't ever get a negative number. If you do, something's wrong. Anyway, so now we got to be careful. X, we're popping what's at the top of the stack. In this case is -8, and I'm writing that because I think it's going to be useful later. Then we're doing that again with 5. Check these off. And then we're pushing in 23. Okay, now we're at part A. Keep going. Now we're popping again, saving that into X. So now X is 23. That goes away. Then we're pushing on 17 and -3 in that order. There we go. Oh, whoops. Sorry. Now we're popping twice. So basically we're going to get -3 and then 17. Then we're pushing on 9 and 6. And after that is part B. 9, 6. Now we copy everything over here. Now we're pushing on -14. Now we're popping 3 times. So we'll get -14, then 6. Oops, not -6. 6 and then 9. So these go, oops. All 3 of these guys go away. Now we're pushing 34. And then we're popping. So which is the 34 we just pushed. And that's it. And that is the correct answer. Does that make sense? Literally just, you know how to push and pop on a stack. Any questions, comments? All right, let's move it forward. There you go. All right, take a look at this one. I'll give you guys the usual minute. And we'll be back. All right, ready? Let's go through it. A word is considered a palindrome. Actually, you might remember, you might remember this question from your lab exam if you took Dr. Ahmed. A word is considered a palindrome if the reverse of the word is the same as the original word. For example, the word test is not a palindrome as its reverse test is not the same as T-set. On the other hand, the word race car is a palindrome as its reverse is the same as race car. Some other examples of palindromes are Hannah, level, madam, and yay. Write a function that will take a string in the parameter and returns 1 if the string is a palindrome, or otherwise returns 0. You have to use stack operations during this process. Assume the following stack definition and the function is already available to you. The stack will be extended automatically if it gets full, so you don't have to worry about it. The top of the stack is controlled by your push and pop operation as usual stack operations. You're given all the usual functions for stack. Note that pop and peak return capital I if the stack is empty. So, how do you think we can do this conceptually? Ideas? We can't just check if the stack is empty. There's no way of seeing if that's a palindrome. Deborah, I like your idea. We can push the first half onto the stack. The middle character doesn't matter. And then we just keep popping and see if the last half matches what's on the stack while we're popping. And if we get to the end and we don't encounter any mismatches, it's a palindrome. Does that make sense? Any questions? Does that make sense, that approach? So if you think about it, like let's use the example race car. We can push rack onto the stack, skip the E because it doesn't matter. And then the other half, as we read it, we pop from the stack. And if they match, and then we keep doing this all the way through, and we get to the end and we didn't have a mismatch, we know it's a palindrome. Does that make sense, Christian? All right, so let's do it. So I think pushing the first half is pretty self-explanatory. For int I equals 0, I will be less than half of the string, which is len over 2, is given to us. Plus. Then we just push using the push function that we're given. We push, we're passing in the address of S because that takes in a pointer, mind you. Gotta be careful. And then we're passing in the current character, the string at I. Okay, great. The first half of the word is on there. Now we have to skip the word in the middle because it's not going to make a difference. So, how do you think we can do that? Well, you should actually only skip the word in the middle if it's an odd length. Otherwise, you do need to include that. Because length over 2 will give you the first half. Matthew. We're going to push on the first half of the string and then pop the second half of the string. Yeah, basically. So if it's odd, we need to skip that character in the middle. But if it's even, we need to include it. So how do you think we can do that? Is there a calculation we can do? So here, think about this. Race car is 7 characters, and len over 2 is 3. So is there a way we can only make one loop, you think? This is len, oops. How can we make it so that this will work for both the odd and even case? Exactly. We can do len minus len over 2. Because that'll work no matter if it's even or odd. So now we just do what we said. We loop through the second half for int I equals len minus len over 2, because we're starting in the middle and going to the end of the um the original string. I is less than len. I plus plus. Now, how would I check if there's a mismatch? Basically, how can I, when we pop, how do I check if there's a mismatch with what's in the string? You don't even need to save it, actually. You can just do that all in an if statement. But yeah, basically, you can just do if pop with the address of S. That was the terrible ampersand, but I don't care. If that does not equal the current value in the string, then immediately return 0 because we know it's not a palindrome. Otherwise, if we get through all that, we know it is a palindrome. So we can just return 1 to indicate true. And that's it. Questions, comments, concerns? Does that make sense? How this works? Correct, Jesse. That's correct. Because len over 2 is even. So it would, since we're starting at that len minus len over 2 index, it'll skip the one in the middle then, which is exactly what we want for odd cases. Does that make sense? Any other questions for anybody? You could use peak. Yes, you could absolutely use peak. And you could at the end too check if the stack is empty. That also works. But you'd have to keep popping while you're doing that. All right. So there it is. There's other ways to do this. So all right, last up for today is recursion. I'm gonna see if I can't get through this by 5 o'clock. I'm getting tired. Tiring talking for basically 4 hours straight. So, what is recursion? It's most easily identified as a function calling itself, usually with slightly different parameters. It's essential for using more complex tasks where you can't do a for loop, like binary tree stuff, some linked list stuff, and other trees, like red black trees and other stuff you'll learn later on. If we have time, Matthew, I don't want to go too late since I know a lot of people only accounted for 3 hours. We'll see. Is that all right? If not, we can always do it another day. All right, cool. And you also use recursion for divide and conquer. Most important thing, you need a base case that basically makes sure you don't go into an infinite loop, which is just an if statement followed by a return or doing something else. Otherwise, you can do some stuff in between, and then you usually have a recursive call at the end that calls the next function, like the next call of itself. Conceptually, you can trace out a recursive function using a recursive tree. You basically make a branch each time there's a new recursive function. And once you hit a leaf, that means you go back upwards. And you need this a lot on the foundation exam, and as you've probably seen before. Tips. Explaining recursive code is hard. I will do my best. The recursive call can be seen as, because, once in something like this, once you hit a recursive call, everything down here is paused until you come back up the recursive tree. You need to keep that in mind. So in this case, it will keep calling delete list in each recursive call before it does freeing. As it comes back up the recursive tree, it'll do freeing. Hopefully that's not new to you. Um, if you were to do it the other way around, you would lose access to the rest of this linked list and have memory leak problems. Does that make sense? Here's some examples just of how the differences work. So if you print before you do a recursive call in this example, you get 5, 4, 3, 2, 1. If you count the other way before printing, then you get 1, 2, 3, 4, 5. Pretty cool. Sometimes recursive code is used as an accumulator function. Sometimes you need to, like, it's basically a way to count stuff. You just add a counter or you hard code a number to a recursive call. Many functions use this technique, counting the number of leaves in a binary search tree, how many of even linked list nodes there are, how many nodes are in a binary search tree, yada, yada, yada. So, any quick questions on that? Also, yes. Precursor, there's a permutation question. You gotta know it. It could show up. It's evil, but it can show up. But let's do the easy one first. This one I'm just going to jump right into because this one's really easy. Write a recursive function below so that it returns the maximum integer k such that base to the k is less than or equal to answer, which are both passed into you. For example, if base is 3 and answer is 123, then 4 should be returned as 3 to the 4th is 81, and that is less than or equal to 123, but 3 to the 5th is 243, which is too big. These bounds provided to you below are to ensure that integer overflow isn't an issue. So, always start. What do you think your base case is? How do you think we're going to do this? Think we're going to working up or working down? Yes, we're going to work down. Because basically the easiest way to do this is if the answer is not bigger than the base, or if the answer is bigger than the base, you know it's valid. So then just keep dividing it by the base until the answer is smaller than the base. So, if answer in this example is 123, that's bigger than 3. So 3 to the, you add 1, 3 to the first, then you keep going. Then you get whatever 123 divided by 2 is, 60 something, 61 and a half. So it'd be 61 in this case. So then you add it again, 61 or 2, 3 squared is 9. And then you just keep doing that. There's other ways to do this too, but this is just the one that seems probably be the best scenario. Does that make sense to everybody how that works? Okay. So what's the base case going to be? Start with that. Not if base is greater than answer. Yes, if answer is less than the base. Because then you don't want to keep cutting it in half or by the base anymore. If answer is less than the base, return 0. Otherwise, we know so far we can add it on. So we're going to return 1 plus, then I have to make a recursive call. So in this case, it's called max pow LTE. And then what would my two parameters be? Exactly. Base, and then the answer divided by the base. That's it. Do you want me to quickly go through an example of how this works? Because I feel like this might be confusing for some people. Anybody? Okay. So let's just use the example we were given. 3, so we know this should return 4. 3 is the base, and answer is 123. So is 123 greater than 3? Yes. So we know there's 1. Then we divide 123 by 3, which is, I don't know off the top of my head, it's 41. So now we're in the second recursive call. Is 41 greater than 3? Yes. So now we know 2. Then we do it again. 41 divided by 3 is, I'm so brain dead right now. 13 with integer division. Then we do it again, so we know we're good. Then we do 13 divided by 3 would be 9. No, 3. 3. No, 4. 4. It's 4. I'm sorry. It's 4. So now we know that scenario is good. So our counter's at 4. Then we do it again. 4 divided by 3 is 1. So now here the base case fails. 1 is not greater than 3. So we're done. And we see that the answer was 4, which is correct. Does that make sense? All right, cool. And there's other ways you can do this, probably. So, all right, there it is. Okay, this one I'm just going to do right away as well because there really aren't any gimmicks with this one. 10 tiles each have strings of in between 1 to 4 letters on them, hard-coded in the code below. The goal of this problem is to complete the code below so that it counts the number of different orders in which all of the tiles can be placed such that the string they form creates a palindrome. Oh, another palindrome question. All of main, as well as the function which determines if a particular ordering of the tiles forms a palindrome, included on the next page have been given. You may call this function in the function go, which you are writing. Complete the recursive function named go to compute the solution. So basically, go is the permutation function. And as you can see, it's using the used array approach, not the swapping approach. By the way, this is basically backtracking, which is a CS2 topic. So I will unfortunately have to tell you that permutation, you just kind of got to memorize how it works, the code. Permutation is like the one topic you should memorize the code on. So anyway, basically, we need to use this recursively, and then if we think we have a match, evaluate to see if it is a palindrome. Does that make sense? Okay, so let's just go through this line by line. So if k is equal to n, what does that mean? It's a big N, which is 10. When 10 is supposed to represent the number of combinations. I guess. I don't know. Well, what do you think it means if k is equal to n? Ideas? Anybody? K is basically just like the incrementation of the permutation you're on, basically. It's like what character you are in the used array, I think. Right. That means if k is equal to n, that means this is a possible palindrome, so we need to evaluate it. And we're given the evaluate function, which we were told to use. So we should just basically return the result of eval with perm with the permutation and all the tiles we were given. Make sense? Okay. Now here, this is just gotta know. In each iteration of the for loop, what does the use get set to initially? Yes. No, eval checks. That checks if it's a palindrome, because that's what the question's asking for. Yes. Yes. You're good. So now, okay. So what's supposed to go in this blank? This you just kind of got to know it. Anybody know it? Yep, 1. Then what goes in the next blank? I. Good. And then skip the big blank. What's the last little blank? 0, because you're unusing, you're done with that iteration, you unuse it. So the last thing is fill in this big blank. Well, what do you think you have to do? Make a recursive call for your next permutation, right? Does that make sense? So the way you would do that is we have a counter called res that we need to use because that's just how this works. So res plus equals. Now, what would my recursive call look like, you think? You got it. That equals go with perm used. Oops. Used k plus 1 and then tiles, because k is the only thing that's changing between each recursive call. And that's it. That one is unfortunately just memorization. So if you need to look back at this, I think this one's used more than the swapping approach, but it wouldn't hurt to look at that too if you have the time. Any questions on this? I'll do my best to answer them. All right, let's get into the last question. Here's what we just did. All right. Take this minute, read it. I'll be back. Let's see, is there one more unique sound effect I haven't used? I think so. Yeah. All right. Let's do this thing. In a 2D video game, one can spray a mist from a cell from the top of the game board, so the first row. The mist will spread recursively up to 3 cells below it, the left, the center, and the right, unless there is a mist blocker at that cell. Here is before and after picture of activating the mist from row 0, cell 3. The letter M is used for mist and B for blocker. Now, do you understand how the mist is being activated here? Because when I looked at this earlier, it took me a minute to get it. Let's just quickly go through this. So you're activating the mist here, right here, and you can only activate below. So basically it activates these 3 guys if possible. So the one in the bottom left cannot be activated, but these 2 can. And then it repeats itself for each one. Down to bottom left, down, bottom right. Keeping that in mind, we do that and this. Then we do it one more time. We get this, 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 that, and that, which should match that, and it does. Does that make sense, what I just did there? How it works? Okay. So, complete the code to the right in this case so that it recursively activates the mist from row R, column C. You may assume that the array grid has num R rows and num C columns. Note the diagram above has 4 rows and 7 columns. To activate the mist, the recursive function places the character M, capital M, in the spot RC unless there's a B already there, in which nothing happens. And then recursively sprays the mist below it. For convenience, both DR, CD arrays and an inbounds function have been provided. DR and DC basically just increment the row in the column. All right, so let's go through these three parts that are already conveniently given to us. So, first up, don't do anything if RC is out of bounds or contains the letter B. So, how would I first check if it's out of bounds, if RC is out of bounds? Exactly. You use the given inbounds function below. If not inbounds, RC and then num R num C. If that fails, then just return because you're not going to do anything. Okay, great. Now how would I check if there's a B? Instead, if it is inbounds, don't overthink this part. Exactly. If grid at RC is equal to capital B, then just then just return. So those are your two base cases. Great. Okay. So if we pass the two base cases, then we got to put the mist in, right? So then how would we do that? Very similar to what we just did. You could smash those together, yes. But you could smash the if statements together, but I didn't. So how could I put the mist in location RC? This should be very easy, one line. Exactly. What Ryan said, grid at RC, that just gets the capital M. That's a capital M. It might look like a little one, but it's a big one. These should be single quotes because they're characters, not strings. Okay, great. We did that. So last up, we just got to mist everything below. So how do you think I would do that? This is probably the tricky part. And we should use these directional arrays here. Any ideas? If you're confused on how these works, these are basically going to say increment one row, and then this is go back one column, stay in the same column, go forward one column. How can we use that to recursively activate the mist below? Yeah, you're on the right track. What you can do is we can loop through 3 times to do each of those 3 combinations. For and I equals 0, I is less than 3, I plus plus, and then now we make the recursive call each time. Mist rec, so the grid doesn't change. Then we do R plus the directional of the rows at I. So that basically saying, it goes to each of these each time. Then we do the same thing for the columns. Change the columns to whatever's in the current directional. And then we don't change the number of rows and the number of columns. That's it. Does that make sense, what I just did there? All right. Any questions on the question? You could do it without the loop. Yes. You could hard code each 3 scenarios. You would just have to make sure you did it carefully. I don't think you do. It doesn't say you do. But if you're given something like that, you should probably use it. That's just how I feel. I might be wrong. I don't know. It's a good question. All right. So we did DMA, linked lists, recursion, queues, and stacks. That is day one of the FE crash course for spring 2026. Day two for the others, I forget what it is. Same time tomorrow will be recorded as well. Yeah, my brain and my voice is fried too. I gotta get my voice a rest. Hopefully, we'll see you all tomorrow. I'll get this recording up as soon as possible. No problem. I hope you found it helpful and liked my teaching style. Hopefully, I'll see you all tomorrow. Oh, the other problem. Yes. Okay. Should we? You guys want to stick around for that other problem Matthew wants to do? All right. Let's get it. Hold on. What exam was that from again? Thank you. All right. I gotta find the solution so I don't mess it up while I'm going over it. Spring 25 should be that one. Give me 30 seconds here. Nope, not DMA. Dang it. No, it was linked lists. Sorry, linked list. There it is. This should be right around here. Nope, I'm stupid. That should be in part 8. What the heck is going on? Whoa. Okay. Not use my iPad. Here we go. Okay. This will be fun. Trying to fry our brains even more, eh, Matthew? Oh, crap. Dang it. I didn't save the screenshot. That's how fried I am right now. Okay. There we go. Should be able to page. Ugh, gotta love technology. Do that. Great. Right. Here we go. I'm just going to jump into this one. The function below is two sorted. Oh, wait, hold on. I have the wrong question. There we go. The function below is given two sorted singly linked lists where each node contains a 2D coordinate xy. The lists are sorted by the x coordinate increasing order first, and then by the y coordinate increasing order. Complete the following user-defined function, merge 2D coordinates, so that it merges the 2D sorted linked list into one sorted linked list, preserving the order of coordinates. And in particular, your code should not allocate or free any memory. Instead, your code should simply change where some of the existing pointers, next pointers, are pointing and return a pointer to the front of the whole updated list. For full credit, write your code recursively, which is also shorter to write. Okay, let's write our base cases first. What do you think the base cases are going to be? We're given two lists. Right. If they're both null, just return null because you can't do anything. If PTR underscore one, nope, there was no underscore. If PTR1 is equal to null and PTR2 is equal to null, just return null, call it a day. Now, what do you think I want to do if one of them's null but not the other? Yeah, exactly. Is that a cat? Yes, it was. If PTR1 equals null, turn PTR2. You know what? I'm just going to copy it because I'm brain dead. PTR2 is equal to null, return PTR1. Okay, now for the hard part. And I haven't even thought about this one, so it's going to take a minute. So basically we have two lists. Let's draw an example. We have like 3, 1 pointed to 3, 2 pointed to 4, 8 pointed to 9, 9. This is PTR1. And then PTR2 is going to have 2, 3, 3, 3, oops, 6, 7. Yes, that was intentional. And 9, 8. And then at the end of the day, the point, I'm sorry, I can resist that. The end of the function, it will return 2, 3, 3, 1, 3, 3, nope, 3, 2, 3, 3, 4, 8, 6 or 7, 9, 8, and then 9, 9. Whew. Okay, let's think how we can do this. Okay, actually, this isn't as bad as I thought it would be. Okay. How do you think we can do this? We don't need to traverse one at a time. We don't need to traverse one list at a time. If you think about it, what we can do is basically compare each at the same index, like this. Compare these guys together. And then we can compare them based on the X and Y, and whichever one comes first, we put first, and whichever one comes second, we put second, and we just kind of append it onto the list as we go. Does that make sense? Okay, does anyone want to think about it, or do you want me just to write the damn solution? Because this one's really confusing. Anybody? Yeah, so it's going to be like a big if statement. Should we compare at each time? Should we compare X or Y first? X, yes, because that's just how it works. So if PTR1 arrow X is less than PTR2 arrow X, then we know, what do we know? PTR1 next should be get PTR2 next, basically. But then, what is there another scenario here that could cause PTR1 to come first? Yes. So if X is equal but Y is less, then PTR1 should come first too. But you still have to check if they're or if they're the same actually as well. They need to be the same. Or I might have just said that twice. I'm so brain dead, I don't even know. So if so if both of the X's are the same, you have to compare it on the Y's. And oh my god. PTR1 arrow Y is less than PTR2 arrow Y. Okay, then how can we do this? We're actually, now that I think about it, we're not kind of doing it like this. The way this is going to work is we have two pointers here because these are sorted. And then based on which is in the right order, then we move it forward, one forward. Then we would move one forward and then basically have this like point to that kind of thing. I'm not fully sure. Yes, Y is just a tiebreaker for the if X is equal, if X comes first. There will be a case if there's a Y. So then if we know PTR1 is first, we can do PTR1 arrow next. That's going to equal the recursive call for the next one. Merge 2D coordinates it'll merge PTR1 next with PTR2. It'll do some magic, and then afterwards we return PTR1 to indicate that's who we're merging together. Otherwise, if the Y's or if PTR2 comes first, we get to do this literally again, except now with PTR2, and we flip these. Oops. So basically, we're just making a link of pointers who should go in what order. Um, well, hold on one second. At the end, you just return, in this scenario, PTR2. So just return one or the other, basically. So the way I thought about that is basically, if X or Y to come first, because we were told, we need to keep the order of the coordinates where X comes first before Y, basically. So really, if you think about it, the way this works is, just as a quick example, I kind of just saw this one on the fly, but the way this would work is PTR2 is here, PTR1 is here. So we know, okay, PTR2 should come next, or comes first. So then we're in this scenario here. So then we increment, we have that point. PTR2 next is in the next. So then basically we're going to have PTR2 next equals the result of the next one. So this comes up here. Then we're in this scenario. So it comes here, then here. Oh my God. Here, there, and then this would get linked. So that's kind of how it works. It's not as bad as it seems. It's just it's kind of a doozy. So, any questions? All right. So let me say that everything before again. That's day one of the FE crash course for spring 2026. All right, it's 1:05, so let's do this thing. Welcome back to the Zoom, I guess. This is day two of the spring 2026 foundation exam crash course. For those of you who weren't here yesterday, welcome. For those of you who were here yesterday, thanks for coming back. Seems to be less people here today, but we'll work with that. No worries. So today's topics, all the yucky stuff for the most part at the beginning. Algorithm analysis, 1, 2, and 3. I know a lot of people don't like that. It's not my favorite thing in the world, but I prefer it personally over Bitwise. Recurrence relations, which I know a lot of people hate as well. Sorting, I find fun. Binary trees and binary search trees, and then we'll end it with good old AVL trees, which shouldn't be too bad. What was I going to say? Let me send in this chat. I accidentally muted myself. Apologies. Slides are in the chat. I uploaded all the stuff from yesterday, so the blank slides, the solution slides, the slides what I wrote on them, and the recording to a OneDrive folder, which I shared. Hopefully, I think that was sent out. I'm not fully sure if that was sent out to Night Hacks. I definitely sent it to a different server though. So if you want that, feel free to just let me know or somebody else know in Night Hacks. Jacob, good to see you. Here, I can send that out right now, actually. Let me get that really quickly. Give me 30 seconds here. Here we go. Yeah, my surgery went good, Jacob. Thanks for asking. Went really good. Any questions or anything before I get into it today? I think today's stuff, unfortunately, beforehand, I don't think there was a lot of time for other members to work on the slides as much. So I think most of these questions are going to be, well, some of them are, some of them aren't. They're going to be redos from last time, but that's okay. Sometimes it might be good for a fresh explanation. So any other quick questions before we get into it? We'll see how long this takes. It's probably going to take 4 hours again. I'll try to spend a good amount of time on algorithm analysis and recurrence relations, especially. Just want to make sure everyone can hear me okay, correct? Okay, cool. I guess if nobody has any questions or anything, we will get on right into it. All right, algorithm analysis. I don't know how many people love this topic. I don't mind it, but I don't love it either. So, TLDR, the biggest thing you got to know is big O. It's a notation to simplify an algorithm's runtime. You will learn in CS2 that it is the worst. Well, you already kind of know it's the worst case runtime, but you'll learn in CS2, big O runtime is basically an asymptotic upper bound for a function. Now, you don't need to know that for this foundation exam, but just figured I'd put that out there. There's also big omega and big theta, but that's not, you don't need to worry about that for the foundation exam. So, of course, as you should know from class, anytime you see a function like this and you want to determine the big O runtime, you determine which term is the dominating term, like which one will have the most control, and eliminate any coefficients. So this one at the top, you could see x squared is more powerful than x. So this would be x squared is the dominating term, and then you just get rid of the 4 for a runtime of big O of n squared. Same thing with this one. There's only one term, so it's going to be the biggest. But then you just get rid of the 4 for big O of n squared. This one down here, the third one, x to the fourth is much more powerful than log x, so that's the dominating term. Then you kill the 7 for a runtime of big O to the x to the fourth. And then the fourth one here, x factorial is much more powerful than just a constant. So the big O runtime would be x factorial. So any questions on that? Hopefully this is not new to you. All right. So, you need to also be able to derive runtimes from code segments. And usually you could either just eyeball it, sometimes you got to use a summation. The biggest thing is, look for any loops. I mean, if there could be recursive calls. That's the whole point of a recurrence relation. We'll get there later. Usually this kind of stuff you'll see is for iterative functions. Basically, you look for what the loops run to in terms of n or whatever the, I guess, input size variable name is. It could be k, it could be size, it could be whatever you have. But basically, you look and see how long the loops run. So this upper loop here, how many times will this run? Someone tell me. N times, exactly. How about the second one? Also n times, exactly. So because remember, with nested loops, you multiply the run times together, how long they'll run. If they're two separate loops, then you'd add them together. So since these two loops are nested, this would be an overall running time of O of n squared. Because this one runs n times, and the other one runs n times, and since they're nested together, n squared. Now, if you had a third one, and that one ran n times, it'd be n cubed, et cetera, et cetera, et cetera. You also need to look for operations inside or outside of the for loops, because, there could be something like, I'm just making this up, if this out here in the J loop was an I++ instead, then this J loop would only run n times once, and basically this wouldn't be n squared anymore then. I believe that would just be a constant. Or I'm sorry, linear. That would just be linear then. So you got to be careful of operations inside the loops as well. You evaluate the runtime kind of like we just did, and then reduce it to big O. Yeah, I can share the slides again, Deborah. Give me 1 second. There you go. Is there a way to pin that? That might be helpful. No problem. So any questions on this? Sure. Excuse me. Sure. So if loops are nested like this, you take their running times and multiply them together. So the outer one runs n times, and the inner one runs n times. So n times n is n squared. Now I'll just make this up. If you had a for loop up here, then there was this is the for loop. Then you had other stuff. Then you had another for loop somewhere else, and both of these ran n times. The first one runs n times. The second one runs n times. Instead of multiplying them together, you add the excuse me, piece of salt got stuck in my throat. Instead of multiplying them together, you add them together. So then the running time of this would be O of 2 to the n, which really is just O to the n. Does that make sense, Elena? No problem. So any other questions on this? The other big thing you'll see, these are common questions as well, is evaluating an algorithm. Basically, it's like an algorithm runs as worst case runtime. Oh, big O runtime of this on this person's computer. It ran in this much time. Figure out how much time it runs on this person's computer. Now, the way you do this is you always write out, t of n. That's just what they call like the overall function. That equals to some constant times whatever's inside the big O. So in this example, you do cn cubed. Then, in this example, we know that t of 100. I'll go in more. There's more of these questions, so I'll go into more detail on those. I'm just kind of doing a quick overview now. You know that t of 100 is equal to 25 milliseconds. So then you could easily solve for c by saying, okay, well, 25 is equal to c times 100 cubed. And then you can do some math to that, figure out what c is. And then using that, you can plug that c value that you get over here back in over here to solve the actual question. Pretty much in all of these, you have to find what c is equal to first in order to answer the question that they're asking you. Does that make sense? Awesome. All right, so let's do some of these questions. Two of these are going to be the ones I just did, the math ones. One should be easy, one should be a little harder. Now, just remember, you do not get a calculator on this exam, so you sometimes might have to do some stuff by hand, which can be a little annoying per se. It's helpful if you know some math rules here. So let's just take it slow and get right on into this. Do you guys want me to give you a minute to look at it again? Or should we just jump right into it? Anyone have a preference? Sure. Let's use that silly timer again. All right, so let's get right on into this. So a big O of square root of n search algorithm took 45 milliseconds to complete a search amongst n equals 4 times 10 to the 6 entries, which is the same thing as 4 million, I think, if I did that correctly in my head on the fly. How long would it be expected for an algorithm to execute a search among a database of 10 to the 8th entries in milliseconds? Now, this one's nice because both the start and the end is in milliseconds, but sometimes you need to know that conversion. I've seen before you start in seconds, they want milliseconds at the end, or vice versa. So you should know that 1 second is 1,000 milliseconds, I think, if I did that right. Someone correct me if I didn't do that right, please. But anyway, we always follow the same process with these. T of n is equal to some constant c times whatever's inside the big O, so square root of n. And we are given that, well, t of 4 times 10 to the 6, for if you see this big E notation, you might see this in physics. It's the same thing as times 10 to the whatever. So this is the same thing as times 10 to the 6. I'm just writing it this way for simplicity. So we know that that is equal to 45 milliseconds. So now we can go down here and solve for what C is, knowing that 45 equals C times, well, the square root of 4 times 10 to the 6. Doesn't it matter which way you write it? Well, okay, how do you think we could clean this up at all? If I want to get C alone, how would I do that first? Yeah, exactly. We can divide this term over to get isolate C alone. Exactly. So what we have is C equals 45 over the square root of 4 times 10 to the 6. Now, we need to clean this up a little. You should always simplify on the exam if you can, because it'll make your life a lot easier. And this is in milliseconds. So, how do you think we can clean this up at all? Let me rewrite that because it might look a little confusing. There we go, that's better. Any ideas we can clean this up? Yeah, exactly. How can we simplify what's in the radical? Any ideas? Exactly. That can be simplified to 2 times 10 cubed because the square root of 4 is just simply 2. And then 10 to the 6th, this is the same thing. If you have the square root of 10 to the 6th, quick side note, that's the same thing as saying 10 to the 6th times to the 1/2 power. And when you get something like this, you just distribute the powers together. So that's 2 times 10 cubed. And then that simplifies even further to 45 over 2000, because 2 times 10 cubed is simply 2000 milliseconds. Does that make sense what I did there? Awesome. Now that we have the value of C, we can now use it to figure out what we're actually being asked to find, which is, well, what is basically T of 10 to the 8th equals question mark. So now we can figure that out. Well, T of 10 to the 8th is equal to our C value, so 45 over 2000 millisecond, write that, times the square root of 10 to the 8th. Because remember, it's C, I can do this, C times whatever's in the big O, root N, and N in this case is 10 to the 8th. Does that make sense? Now, how do you think we can clean this up? How do we get a nice number out of this? Because you can't just leave your answer like this. Any ideas? Yeah, exactly. This root, again, same thing as before, is the same thing. If you simplify this term, that's just 10 to the fourth. And then since this whole thing is being multiplied together, this term here, whoops, this term goes on the numerator. So this simplifies to 45 times 10 to the fourth over 2000. Now, how do you think I could simplify this even further? It might help, again, maybe possibly to do this. Rewrite 2000 back into this form. Yeah, you could basically crossing out the extra zeros or dividing by 10 cubed. Same thing. So if you divide by 10 cubed, if you divide these exponents over here, this simplifies to just 10. So you have 45 times 10 all over 2. So that would be 450 over 2, which is simply 225 milliseconds, and everything was in milliseconds before, so it's still in milliseconds, and it simplifies 225, which is the right answer. Does that all make sense? Here, only move this on over here so it's a little easier to see. There we go, that's better. Any questions on this question? Here, let me rewrite this up here just for so it's not confusing later. There, that's better. Makes sense, hopefully? Kind of just plug and chug with math. What do you mean leave it in the 10 to the fourth form? Oh, the 45 times like this part here. I mean, you can. I mean, you don't have to do this exactly the way I did it. There's many ways you can do. You can do this part slightly differently, as long as you get the right answer. That's all that really matters. Does that answer your question? Okay, perfect. All right, so let's do another one. All right, this one's gonna be a little more nasty. I'll give you guys a second to look at it real quick. All right, let's do this thing. So you got to be careful here. This one, the big O, is n times the cubed root of n. That's not n cubed. That's n cubed, n times the cubed root of n. So we're being told that t of 40 cubed is equal to 2.5 milliseconds. We want to know what t of 80 cubed is equal to in milliseconds. So, in order to do what we're trying to be fully asked for, we got to use the the first given thing to find out what the c value is. It's the same process as before. So we know that 2.5 equals some constant c times the cubed root, or excuse me, 40 cubed times the cubed root of 40 cubed. So that's the same thing as 40 cubed to the 1/3. You can write it either way. So, what do you think the good first step is here? Let's not divide yet. Let's clean up the right side first. Yes, so we distribute this again. That's the same thing as saying, well, 2.5 is equal to c times 40 cubed times 40. Now how can I clean this up even further? Exactly. If you have two numbers multiplied by the same base, you add their exponents together. So you have a 3 and a 1. Don't forget that there's a 1 hidden here. That's 40 to the first. So this gets rewritten as 2.5 equals c times 40 to the fourth. And now we can divide the 40 to the fourth to the other side to get that c is equal to 2.5 over 40 to the fourth. Well, let's leave it like that for now because I don't think any of us want to figure out what 40 to the fourth is by hand, right? All right. So now let's find what we're being asked to find, t of 80 cubed. So t of 80 cubed is equal to our c value, 2.5 over 40 to the fourth times 80 cubed, oops, times the cubed root of 80 cubed. So how can we go along and figure out what this is equal to? Yeah, we can do the same thing as before, distribute this to there to get that's just 80. So we got 2.5 over 40 to the fourth times 80 cubed times 80. And then, that looks like this 404. There, that's better. We can combine these two again the same way we did before, so which gives us 2.5 over 40 to the fourth, that whole thing, times 80 to the fourth. Okay, now what do you think I can do? Yeah, well, you can simplify the zeros. Well, not even necessarily that. You could, that's one approach, yes, but 80 to the fourth this isn't 10. We don't know what 80 to the fourth is, so it's going to be some big number. We don't know what that is off the top of our head. Any other ideas? True, 40 to the fourth does equal 10 times 4, 10 to the fourth times 4. But I like what Russell said. Remember, this is the same thing. Both of these terms are on the numerator technically. We could factor out these guys together since they're all being, it's 80 to the fourth over times 2.5 all over 40 to the fourth. So what we can do is rewrite this like this: 80 to the fourth over 40 to the fourth times 2.5. Is that not the same number? Then using exponent rules, how can we simplify this even further? Oh, wait, never mind. Russell already said it. What you can do is if you have two of these to the same power, you can bring out the exponent. You'd have 80 over 40 to the fourth times 2.5. And then this guy is easy to simplify. 80 over 40 is just 2. So you have 2 to the fourth times 2.5, which is the same thing as 16 times 2.5, which 32 times 16 times 2 is 32, and then half of that is 8, so you should get 40 milliseconds. That's your final answer. And again, since we started in milliseconds and we're ending in milliseconds, that's what they wanted. We're all good. Does that make sense what I did there? Any questions or confusion? These you gotta know these kind of rules and stuff. It's annoying, but just the way it is. I did 40 by just doing 16 times 2.5. I know I just did it off to the side. 16 times 2 is 32, and then half of 16 is 8. So 8, um, you just have to add on the half. So then 32 plus 8 is 40. Any other questions? Yeah, these just take some practice. So, all right, let's get a move on. This one's a bit of a doozy, so I'll give you guys a couple minutes to take this one out. All right. Just curious, what did you guys say for this one? What do you think the big O running time is? Did anybody get an answer? Okay, we have a log. Somewhat. I like how you're thinking log. It's on the right track. Log n is a good choice as well. Lost and scared is also a very valid answer. This one's a bit of a doozy. So let's just go through this slowly. Good job, Eric. That is the correct answer. Yeah, it's NK, same thing. It doesn't, multiplication doesn't matter the orientation. But let's go through how you get there. So we have first, when you're the first thing you see while you're looking at this code is that there's two loops and they're nested together. So that means at the end you should have two terms multiplied together. And because the loops are going to be what really determines how long this code runs. And there's really nothing that there's only one operation that kind of simplifies the code a little in the loops, but we'll just go through each line by line. Okay, well, the first line, I think that's pretty self-explanatory. We're setting a lower bound to 0. That's pretty self-explanatory. Now, this setting the higher bound, this is a bit of the doozy here. What does this mean here? Does anyone remember what this notation means? Correct. You're bit shifting to the left. And when you're bit shifting to the left, that means you're raising whatever number's there by 2 to whatever's on the right. So, if this was, I'm just making this up, 1 left shifted 5, that's basically say 1 times 2 to the 5th, which is just 32. So, in reality, what does high equal to, if you want to simplify this? 2 to the k, exactly. So, but remember, now let's also keep going, and we'll get back to this in a minute. So we know high is equal to 2 to the k. So now let's look at this loop. We have while low is less than high. So at first, you're probably thinking, okay, this is, linear runtime. But now let's look at the one after that. Int mid equals low plus high over 2. What should that ring in your bell right away? What is that very similar to? Yeah, I can do the 2 to the k in 1 second again. Actually, I'll just do it now. So remember, Jacob, shifting anything to the left is multiplying. You raise something like to 2 to the whatever. It's you multiply by 2 to whatever's on the right side here. So in this case, k. And since it's 1, it's just 1 times that. So this was like, 5 times left shifted 3. That would be the same thing as 5 times 2 cubed, which is 5 times 8, which is 40. So applying that same logic, you just have 1 times 2 to the k, which is just 2 to the k. Does that make sense? No problem. And if it's right shift, you're dividing. Um, but yes, I like that Deborah said binary search. This is very much like binary search. And keeping that logic in mind, even though it's not log n, if you think about it here, we could solve using that logic that, this is basically in a logarithmic time. We can use that to basically simplify this bound. Using that log base 2 of 2 to the k, well, that's just the same thing as k. So in reality, this loop in this mid part here, this part runs or k times. It runs k times. Does that make sense? Any confusion on that? So you just kind of got to know, like, okay, this is log base 2 times, since you're cutting it in half every time. And since the upper bound is 2 to the k, that upper bound in reality in the loop is just k. So that's helpful. So we know this outer loop runs k times. Now let's keep going. Declaring a variable that's constant. Now we have an inner for loop here. Is there anything in this loop that's going to make it run any differently than what's given? No, there's not. So how many times does this loop run? N times. And then everything else is constant. All these operations down here are constant. So in reality, if this loop runs n times and this one runs k times, since they're nested, you multiply them together. So the overall big O running time is kn, or big O of nk. Same thing, it doesn't matter which way you put it. Does that make sense? Any questions or confusion on that? So you would need to basically say everything that I said to you verbally on the exam. But I'm not going to, just for time's sake. I don't feel like writing it. K is logarithmic, Elena, because remember that. So do you understand the 2 to the k part up here? How that's just 2 to the k plainly? So the thing is, because we're cutting k in half every time, or the high bound, or Jesus Christ, how am I trying to say? Because you could see here with this, I should have made this a little more clear. I apologize. With this and down here, we're doing basically a binary search. You should know in your head, okay, that's logarithmic time. But if my upper bound is 2 to the k, you can use this to just realize that the upper bound is just k. Sorry about that. I should have clarified this a little better. Yeah, it's just you should basically just realize it's binary search with one other thing in the middle of it. That's all it is. Any other questions? No problem. Wow, we actually got through a section under an hour. That was pretty good. Am I going too fast? Okay, just making sure. All right, let's keep this party train rolling. So that is algorithm analysis. Now let's get into more algorithm analysis stuff. Summations, everybody's favorite. Now, if you think about it, a summation is just a tool. It's just an overall sum that it helps us to analyze algorithms. If you think about it, a for loop is basically a summation as well. To evaluate a summation, you just have to use techniques using formulas, as well as shifting and splitting. These formulas here that you see that is given to you on the formula sheet on the exam, so you do not need to memorize those. Generally speaking, if there's something kind of crazy and there's a formula for it, they'll provide it to you. Like, if there's like, I'm just making this up, like an I to the fifth or something. Like if this was to the fifth, they'd give that to you usually. Yeah, I know it's yucky, but you don't have to memorize this, which is very nice. Although one good trip, if you're ever or tip, if you're ever struggling to remember the cubic formula, it's literally just the linear formula and everything's squared. Did you ever notice that? Everything's just squared. I don't know why that is, but that's just how the universe works, I guess. So, as I said a minute ago, there you will likely have to do some shifting or splitting. Splitting's really easy. That's just if you have a summation that has two terms being added together, you can split that up into two separate summations with the same bounds and evaluate them separately. You get the exact same answer, and it's a lot easier that way. Shifting is mainly used when, all these formulas have the lower bound is 1. So if you don't have a lower bound of 1, you need to shift it to reflect that. Basically, what you do is you use this technique. You have one of them go from 1 to b minus a plus 1, or it's the same thing as, or oh, I'm sorry. If you have one from a to b, you can simplify it like this, or it's the same thing as this. You kind of just got to know these. Hopefully that's not new to you. And then series, these you kind of have to also know as well. An arithmetic series, that's just a series where, it's summation where something's being added by the same value every time. So, I'll just make up a quick arithmetic series. The odd numbers, for example, 1, 3, 5, 7, 9, dot, dot, dot. That has a common difference of 2. CD, everything's being added by 2 every time between terms. So you could simplify this if you want to find, I don't know, figure out what the fifth term in the series is. Then you can just figure out, okay, well, it's 5 times the first term, which is 1, plus the, this actually might not be the right formula for that. I apologize. I forgot what this formula is for. But basically, that's what an arithmetic sequence is, or series is. Oh, it's the sum. I'm so stupid. It's a summation. I'm sorry. If you want to figure out what the sum up to the fifth term is, so it'd be 5 times the first term, which is 1, plus the fifth term, which is 9, right? 1, 3, 5, 7, 9. Yeah, 9 all over 2, which is the same thing as 5 times 10 over 2, which is simply 25, which does sound right. I think that's what 9 plus 7 plus 5 plus 3 plus 1 is. Someone can fact check me on that if you want. Yeah, I just did in my head. So this is the formula to figure out the sum of a random number. If you want the 10th term, you just apply like the sum of the first 10 numbers. You do the same thing, just with tens, 100, 50, whatever it may be. Now, a finite geometric sequence is a very similar thing, except instead of adding every time, everything's multiplied every time. So we could do, let's do something different. You could do 3, 9, 27, 81, right? I think that's what 27 times 3 is. Dot, dot, dot. Everything here is between terms. You're multiplying by 3 every time. That's what a geometric sequence is. So then if you want to figure out a finite geometric sequence, rather, yes, you do need to know these. So the sum of any number, S of n. So if you want to figure out, let's say, the sum of the first 3 terms, S of 3 is the same thing as the first term, which we know is 3 times 1 minus the common ratio in this case was also 3. 3 times 3, there's a lot of 3's here. This 3 up here is the n, and this is the r. And then all over 1 minus r, which is 3. So here you would get, that feels very odd. Actually, never mind. This is right. So you'd have 3 times 1 minus 27 all over 2. So you'd have 3 halves. Or I'm sorry, negative 3 halves. This is negative here. So you'd have negative 3 halves times negative 26, which is the same thing as negatives cancel. You have 3 times 13, which should be 39. And, well, 27 plus 9 is 36. Yep, that's right. Does that make sense there? Kind of just plug and chug. And then an infinite geometric series is just like a finite geometric series, but its upper bound is infinite and never stops going. So if it's basically the same thing, just slightly different formula. So if this one here is that I'm just making up a number. I don't know if this is in the actual sequence. 512. This one here would just it'd be 3, 9, 27, and just go on forever, 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 and it never stops. It goes all the way to infinity. Hence why it's called infinite. So if you wanted the sum of that, it would just be the first term, 3, all over 1 minus the ratio, which is also 3. So it'd be negative 3 halves, which is kind of weird, but I guess it makes sense. I don't know how. It feels very odd. But I'm just going to roll with it for now. So these are just kind of plug and chug formulas to figure out what the sum is of some term in the series. This one here, it's just the sum of the overall series. Any questions? Make sense? We feel okay? Because I know this stuff is confusing. I just want to make sure. Basically, if it asks you here's a geometric series. What's the sum of the a finite geometric series? What's the sum of the first 10 terms, for example? Well, then you would just know. Okay, use this guy. But mainly, I think the most of the stuff you'll see is the shifting and the splitting and these guys here. That's the main stuff you'll see. So here, I can do another quick example, Deborah. Why did my Siri just turn on? So let's just say, yes, you're given the summation formulas. Let's say you're given the sequence. I'll do an arithmetic sequence. Let's do 1, 5, 9, 13, 17. Nope. Yes, that's right. 21, 25, dot, dot, dot. And you want to know, okay, hey, what is the sum of the first 4 numbers? So what's S of 4? Well, then you would just use this formula here. So how would I do that? Well, if we want the sum of the first 4 numbers, n is simply 4, so it'd be 4 times ace of 1 is just the first term. The first term here is 1, so it'd be 1 plus ace of n, that's basically the fourth term. So 1, 2, 3, 4, 13, all divided by 2. It's the same thing as basically saying 2 times 14, which is 28. Does that make sense, Deborah? No problem. All right, so let's do some questions. I think we're doing. Yeah, there's 3 of them. This is an old slide here. These are the ones we'll be doing. Easy, medium, and hard. Just summation ones. You usually see the summations. I don't think you really see the series stuff that often, but it's good to know it just in case, because anything can really be asked on this exam. So, determine a closed form to the summation in terms of n. I'll give you guys a couple minutes to try it on your own, and we'll come back together. Anyone get an answer? That is correct. Nice. Good job. Let's go through this one. This one shouldn't be too bad. So the summation, since there's two terms in one summation, you should split them up into two summations. So this is the same thing as I equals 1 to 3n of 2i plus the summation of I equals 1 to 3n of 5. Now, this guy over here should be pretty easy. If you have something like this, what would this simplify to? Well, you just multiply what's on the inside by the upper bound. So that simplifies to 5 times 3n. Now, how can I simplify this guy anymore? Exactly. The 2 is not making a difference to anything, so you can pull it outside. So you have 2 times the summation of I equals 1 to 3n of I. Let me move that down. Oops. Move that down a little. Oops. Oh my god. There we go. Then, keeping that in mind, what's this guy simplified to? Well, this is just kind of using the formula and knowing. That's the same thing as I, or n, so 3n to the n plus the upper bound plus 1, so 3n plus 1 all over 2. But we also have this 2 being multiplied from it outside. And then we still have the extraneous 5 times 3n, which I'll just multiply real quick to get 15n. So now this is really nice. The 2's will just cancel, they're gone. So you have 3n times 3n plus 1 plus 15n. So you have 9n squared plus 3n plus 15n, which fully simplifies to 9n squared plus 18n. If you really wanted to, you could factor out a 9. I don't think that's necessary. This is what they have on the solution key. So there you go. Makes sense? Any questions? All right. Let's ramp up the difficulty a little. I'll give you guys an extra like 30 seconds this time. Good luck. See you in a few minutes. Anyone get an answer? You guys want more time? I can give you another 2 minutes. Okay, I'll just do the same thing again. How'd we do? I think that's right. But the problem is, Jacob, it literally says right in the answer for the question, do not multiply the answer out into polynomial form. The recorded section, Jesse, is going to be here. I'll send this link again. Everything will be in. Oops, wrong button. Everything here will be. Hold on 1 second. Sorry. The recording and slides and everything will be. And today's slides already in there. Will be in this link here. Just a OneDrive folder. Just log in with your UCF stuff. No problem. All right, so let's go through this one. Determine the following summation in terms of n in factorized form. So basically, it needs to be factored at the end. Do not multiply the answer down to polynomial form. Same thing. Your answer should also not have a fraction in it. It should just be terms that are multiplied together. All right, so what do you think step one is with this guy? Split it, exactly. Two terms in the same summation, at least two, split them up. So this is the same thing as the summation from I equals 1 to 2n minus 1 of I plus the summation of I equals 1 to 2n minus 1 of 3i squared. Now let's take care of the first one first. How can I simplify this guy? use the formula, exactly. Because it's just an I term on the inside, so it's just the upper bound of, it's the upper bound times the upper bound plus 1 over 2. So in this case, that's 2n minus 1 times, well, 2n minus 1 plus 1 is just 2n all over 2. Leave that for now as is. Then over here, how can I simplify this? Any ideas? Before we jump, I don't want to jump straight into the I squared formula yet. You're on the right track, but yeah, let's first pull out the 3. I think it's a little easier to pull out the 3 first. So you have 3 times the summation of I equals 1 to 2n minus 1 of I squared. So now I'm going to copy this stuff down on the left. So then we have plus 3 times, now I actually forget what that is off the top of my head, the I squared formula, there it is. So it's going to be your upper bound. So in this case, 2n plus 1, or minus 1, excuse me, times the upper bound plus 1. So in this case, 2n times the upper bound, or 2 times the upper bound plus 1. So this will be times 2 times 2n minus 1 plus 1. I think that I did that right. We'll see in a minute. And then it's all over, what was it, 6? Yes, 6. All right, so let's now, I'm going to need another page. There we go. Now let's clean this stuff up. Let's clean up the left side first. This hopefully shouldn't be too bad to simplify. On the left side, we can distribute the 2n minus 1. So we get 4n squared minus 2n all over 2. Plus, okay, now this is going to be fun. Let's clean up the inside first. You'll have a 3 over 6. That just simplifies to 2. That's not, or I'm sorry, 1 over 2. So you have 2n minus 1. Hold on. So it's something, it's some big mess all over 2. So then let's distribute these guys together and clean this up. So first distributing, you'll get 4n squared minus 2n. And then that whole thing times, you'll get 4n, you'll just get 4n minus 2 plus 1. So simplify, let's clean this up even more. This whole guy here, we can simplify the 2. So we have 2n squared minus n. Plus, now over here, we still have 4n squared minus 2n times 4n minus 1 all over 2. So now we can FOIL this guy. Just rewrite this. Okay, so let's be slow with this. You'll have 4n squared times 4n, so that's 16n cubed, minus 4n squared, minus 8n squared, plus 2n, all over 2. So, on the left, you have 2n squared minus n. Now we can clean up, get rid of all these factors of 2, plus 8n cubed minus 2n squared minus 4. Wait a second. Oh, we should simplify those first. So this is just minus 12n squared. Yeah, I'm gonna do it like this, and then we'll factor at the end, Russell. I think it's easiest to get to an answer, then we can factor it at the end. So this guy here is minus 12n squared. And then we have the plus 2n. Okay, now we can clean this up even further. You have an 8n cubed on the outside. And then 2n squared minus 12n squared, that's minus 14n squared. No, it's not. That is minus 10n squared. And then n net, or 2n minus n, same thing, that's just plus n. Okay, So what can we factor out from all of this? Something does not seem right here. Let me just double check our work. Maybe it is. Hold on a second. I think it might be actually. Okay. So what can we do here? How can we clean this? How can we factor something out? Well, there's an end turn and everything. So then if we did that, we'd have n times 8n squared minus 10n plus 1, which still doesn't feel right. Doesn't feel, I think I might have done something incorrectly here, actually. Everyone makes mistakes in life. Because I'm just trying to think. Here, hold on a second. Where did I go wrong? Negative 6n squared? Oh, up here. Yeah, thank you. Good catch. I just rewrote the same thing. This guy here, these two together are negative 12n squared, but I didn't divide by 2 there. Thank you, Jacob, for catching that. Okay, so now let's redo all that. So now you'll get 8n cubed minus 4n squared plus n. Okay. Now, yeah, this is looking better. Now what we can do, these two guys, we can factor out a 2n squared. So then you would just get 4n, just 4n minus 2. You still have the plus n. Still really, something still doesn't see. Minus n, where did I? This guy, you mean, Jacob? These two guys? Isn't 2n minus n positive n? Did I say? Oh my god, I did that again. That's why I got to be careful with these. I didn't divide again. Thank you. Sorry about that, guys. I didn't divide these guys out. Okay. Did I divide the other two? Let's check. That I did. Okay, yeah. Okay, we're good now. Sorry about that. Yeah, so the ends cancel. Okay, yeah. Now this is looking right. I apologize for all that confusion. So just to recap, 16 divided by 2, that's where the 8n cubed comes from. These guys are 12n squared. It's negative 12n squared, which is where this comes from. And then 2n over 2 is just n. Okay, yeah, now this is looking a lot better. So now these guys cancel each other out. They get 8n cubed minus 4n squared. Now we were told not to leave this in factored form, so we can factor out a 4n squared from both terms, and you end up getting a 2n minus 1, which is the final answer. Sorry about all that mess up. Damn, nobody's perfect. Does that all make sense? That's why you gotta go slow with these and make sure you don't forget to do stupid stuff like I did. Any questions or anything? Which part do you mean with the top part? Like, can you give me a line number? Like, this is 1, 2, 3, 4, 5. From line number 2. Okay. So what I did here, we just applied the formulas. First, I applied the formula here, just the single I formula. Then what I did here is I pulled out the 3 and left everything else alone. Then on line 3, I didn't touch this guy at all yet. Then on the inside, I just applied the squared formula. Correct. They want you to factor common terms. I'll go. Sorry, I got distracted. So I factored out, or I just applied the squared formula here. So the 3 on the outside. Then it was just a matter of cleaning everything up. On the left, I distributed these two guys And on the inside here, for these two terms on the right, how would you multiply the 2n in line 2? Here, what's 2n times 2n? Well, that's the same thing as 4n squared. I just did it 2 lines later. And then 2n times minus 1 is just negative 2n. Does that make sense? Do you need me to explain the rest again, or was that what you were asking for overall? Okay. So hopefully the rest of it makes sense. Deborah, so yeah, it basically says you have to have it in factored form. You can't have it in a polynomial form. So basically, you can't have something like this: 8n squared plus 3n plus 2. That if you had that, it would be wrong. You have to leave it. They want it if they want it in a specific form, you have to get it in that form. Yeah, so they just basically want you to factor common forms. So you could do it like I did, just get it into something like this, and then factor at the end, which is what I think is the easiest thing to do. But if you wanted to do some factoring along the way, you could also do that as well. Any other questions with this? So basically, Jacob, you have to leave it in like a fact. See how like there's a common factor? I factored out from here to here. If you left it like this, it's not, you won't get full credit. It was we were specifically asked to do it in factored form. If you left, I'm looking at it now. If you left it like this, that's an automatic 3 point deduction. The max you can get is a 7 out of 10. So make sure you read what the question's asking you. And you'll see this as well on the next question. So if we have no more questions, are we good to move on to the harder summation? This one's also a doozy. The grading criteria, when the solution slides are in there and all the grading stuff is in there. Really, it's like so doing this up here is a point. Applying this formula is 2 points. Applying the I squared formula is 2 points. Canceling terms are 2 points. Factoring this guy is 2 points, and then this guy is a point. But again, if you left it like this, that's 7 out of 10 max. So you can look at this more later. He did it a slightly different way. As long as you get to the right answer at the end, that's all that matters. He was kind of doing it, leaving things as factors. He was leaving, factoring stuff out as he went. Again, I just think it's easiest to do it like this, but you do you. So, all right. The next one's going to be a bit of a doozy. I'll give you guys 5 minutes to work on this one since this one's a bit difficult. Here's again, please leave your answer in a factored form where everything is in this form here. Good luck. We'll be back together in 5 minutes. I don't know if that was 5 minutes or not. Something happened with the timer. Y'all ready? Anyone get an answer? Anyone want more time, or should we just go through it? 2 minutes? Okay, we can do 2 more minutes. All right, are we ready? Did you guys finish it? All right, it's good you're stuck. That means you're in the right place. I know, thank God for the formula sheet. All right, here we go. Let me add another page preemptively because I already know I'm going to need it. Okay, so how do you think I would start? Right, if you have two summations multiplied like this, you start with the inner one. Now, how would I solve this here? How can I solve this inner summation? Yeah, you use the linear formula basically, except of instead of n, it's going to be I. So you have the outer summation still of I equals 1 to n times the upper bound times the upper bound plus 1 all over 2. So that's just I times I plus 1 all over 2. Make sense? So now it's basically this this summation is being applied to this whole thing. Yeah, it's the same thing. You just use I instead of n. So now, what do you think I should do here? Should I solve this right away, or should we clean this up at all? Yeah, let's clean it up. How can I clean it up? We can distribute the I, sure. So you have the summation of I equals 1 to n of I squared plus I all over 2. Can I do anything else? Yeah, let's factor out the 1/2. I think that would be a good approach. because the 1/2, there's technically a 1/2 that's not really doing anything. So you have 1/2 times the summation of I equals 1 to n of I squared plus I. Now as Jacob said, let's split it into two summations. So you'll have 1/2 times the summation of I equals 1 to n of I squared plus the summation of I equals 1 to n of I. Okay, now let's just use the formulas. So the first one, using the squared formula, it's n times n plus 1 times 2n plus 1 all over 6. Then we have over here n times n plus 1 all over 2. Make sense what I'm doing so far? All right. Now let's start distributing on each. So we still have an over 6 and an over 2. This guy is pretty easy to distribute. On the numerator on the right, you'll just have n squared plus n. Now over here on the left, you'll have, let's first distribute these two terms. You'll get n squared plus n, and you have that whole thing times 2n plus 1. Now if we keep going, now we can distribute these two guys. So we'll get, let me erase it. There we go. So now we'll get, if you do this very carefully to FOIL, you'll get 2n cubed. Oops. Sorry, I'm just making sure I'm doing this right. Plus n squared plus 2n squared plus n. Now I think we should distribute this 1/2 to get rid of some things. So you'll have 2n cubed plus n squared plus 2n squared plus n all over 3 plus n squared plus n. Okay? Now we can combine these two guys. So you have 2n cubed plus 3n squared plus n all over 3 plus n squared plus n. All right, so really that just simplifies even further to 2/3 n cubed plus n squared by the 1/2. Yeah, shoot, good catch. This is why I don't like math sometimes. Okay, we're going back up here. Sorry about that. So, thank you for catching that. I should have multiplied these out. So you have a 12 on the bottom and then a 4 over here. There we go. Okay, so now let's see what we can do here. Well, this is simply 1/6 n cubed plus 1/12 n squared. Well, really, it's 3n. This is 3n squared over 12, so 4n squared. No, that's not right. You have n 1/4 n squared plus n over 1/12 n plus 1/4 n squared plus 1/4 n. So you have 1/6 n cubed plus 1/2 n squared, and then a 12th plus a 4th. I don't know what that is off the top of my head. Well, you can do a common denominator, multiply by 3, this guy by 3 on both sides. So you would get 4/12 n, which is just 1/3 n. And let's think, how does that help us? Well, we can get a common denominator. Oh yeah, that's probably an easier way of doing it. So you can do this, but I'm gonna go back to what Jacob says. I'm sorry, I'm doing So many different side notes here, but these are difficult even for me. So yeah, that's a good approach. We can multiply this whole thing by 3 to get a common denominator. I like that. So you'd have this plus 3n squared plus 3n all over 12. So now we can just combine like terms. You would get 2n cubed plus 5n squared. No, why did I say 5? You have 3 plus another 3, so 6n squared plus 4n all over 12. So then we can clean this up some more. You can get, well, 1/6 n cubed plus 1/2 n squared plus 1/3 n. I'm trying to think how this helps us though. Combine what first? Easier to divide 2 instead of 12. What do you mean easier to where Lauren? Where are you talking about? This is the problem. I'm just not sure where are you supposed to get it because remember we have to get it in this form here. I think I remember I struggled on this question last time too. You keep 6 in the denominator. Oh, you just get a common denominator between these two, you mean? Yeah. Okay. Yeah, yeah, yeah. I like where you're going with this. This is right, I think. So, yeah, let's multiply here. Let's get everything with the same coefficient. So, let's leave this. So, we're going to have some all over 6. We have an n cubed plus. Now, with this guy, if I want to get the denominator 6, I have to multiply both terms by 3. So, you'd have a 3n squared. Then, over here, if you want, you'd have to multiply by 2, so you'd have a 2n. So now what we can do, well, first we can factor out an n from this. So you'd have n times n squared plus 3n plus 2. Okay. And now what do you think we can do with this? How can we go from here to get this into the form we want? Which again, here is this form again. I can zoom out to show the whole thing. How can we simplify this? Oops. How can we simplify this into this form? Any ideas? No, that wouldn't. That's you're on the right track, Jesse. Any ideas how we can? We're really close, guys. We're really close. We can factor it exactly. So let's do a quick side note over here. Let's factor n squared plus 3n plus 2. I don't know if you guys know the ABC method, but this is what I was taught. A times c is 2, factors of 1 and 2. That's literally the only thing that works. So you'd have an n plus 1 times n plus 2. Now we can bring that over and simplify that in for this. So you have n times n plus 1 times n plus 2 all over 6, which is the correct answer. The ABC method is just, this is supposed to be the quote unquote, it's this is what I was taught in high school. This is A, this is B, this is C. You multiply A and C together and you list out the factors of that number you get here and try to find a pair that multiplies to C but adds up to the coefficient for B. So this approach here, I'll do this. Bad, good. Okay. So sorry about the confusion. It's a tough question for a reason. Any questions, comments on this? You could put n plus 0. I don't see why that would be wrong, but in the solution, it is just n because it's the same thing. So if you wrote n plus 0, I don't see why you'd be penalized for that, Jesse. Any other questions? No, it's understandable. You could put n plus 0. I don't see why. I don't see why you'd be penalized either way. Any other questions? Does this make sense what we did? Does anyone want me to repeat anything? If we have time at the end, I could do a quick shifting one, sure. But for time's sake, I just want to make sure we get through everything else first. Is that okay? All right. So any other questions here? That one, I don't like that one. That one's annoying. That one feels like a Guha question. All right, then. Now let's get to the probably the most annoying thing today, recurrence relations. Ugh. Everyone's least favorite, probably. One of the least favorites. A recurrence relation, quick refresher, is how you determine runtime for recursive functions. You basically, it's just like a recursive function itself, where you have a base case and a recursive step. The way you solve them, you need to perform a minimum of 3 iterations, where the one given to you does count as an iteration. You basically plug the iteration in the equation into itself. Here's an example here. You should hopefully know this. We'll go through some. Afterwards, you try to find a general pattern from the iterations you have. For k is the kth iteration. You do it in terms of k. You solve for k in terms of the base case. This should say here in terms of the base case. I remember we forgot to update this again. It's not always equal to 1. It's in terms of the base case. It's usually 1, but not always. Then afterwards, you plug in k into all the occurrences to simplify and hopefully get an answer. Basically, you're trying to get rid of a t of, there's 2 on both sides, there's a t of something. You want to get rid of that on the right side. That's the whole point of this. This is called the iterative substitution approach. You will learn in CS2, you may have heard of this, of something called master theorem for recurrences in this form. Don't use it on the foundation exam. You have to do it in the iterative substitution approach, or you'll probably get an auto 0. So then for this one, here's where they are expressing in terms of k down here. And then they use this k pattern iteration, using that to solve for whatever k is, and then substituting it in to get a final answer. So looks like there's 2 of them here. I don't know why it says there's 3, but always iterate 3 times, where again, the one given to you does count as an iteration. 3 proper iterations will award half or more partial credit. So always do that. So here's the first one. Some of these you have to find an exact closed form. Some of them you have to find a big O. So this one's, again, your answer should be in this form. Great. You guys want to try this one on your own, or should we just do it? I feel like these might be good ones where we just do it right away together. All right, let's just do it. Cool. All right, so let me show you guys the way I like to do these recurrence relations. I think, I know you can do this in the exam, but for teaching purposes here, I think it's really helpful to do some color coding. So I'm just going to do this straight on a new page. So what are we given? Use the iteration technique to find an exact closed form solution to this recurrence relation. All right, so I like to color code. Iteration 1 is the one that's given to you. T of n is equal to 2t of n minus 1 plus 5. Well, how do we go from here? Remember, you should be doing some side computations, or the side note as it's called. Well, we need to figure out what t of n minus 1 is. Well, how do we do that? We go to the side. T of n minus 1 Well, the way I like to think of this is, if you had, as a quick side thing, if you had a function like f of x equals x cubed plus 5x, and then wanted to figure out what's f of 5, well, that's the same thing. Everywhere you see an x, I'm going to substitute in a 5. So that'd be 5 cubed plus 5 times 5. Same logic here. Anywhere I see an n here, if I want to figure out what t of n minus 1 is, I'm going to substitute in n minus 1 into the n. Does that make sense? Any confusion on that? Okay, just making sure. Okay, so now let's figure out what t of n minus 1 is. T of n minus 1 will be 2t of n minus 1 minus 1 plus 5, which simplifies to 2t of n minus 2 plus 5. Okay, cool. That's as simplified as you can get that. So what I like to do is now use a different color. I'm going to signify, I'm going to input this over here in blue. So iteration 2 now, we know that t of n is equal to, we have the 2t the 2 from before multiplied by what we just got. So 2t of n minus 2 plus 5, and then we have the plus 5 from the first iteration. Makes sense how I substituted that in? Okay. Now we can clean this up by distributing. First, we can distribute this 2 to everything. So you get 4t of n minus 2 plus 10, and then you have the plus 5. So cleaning this up, if you think there might be, if you usually can't combine things nicely or there's fractions and what stuff, there might be a summation involved. But this one's pretty straightforward, so I think we can just leave it as is without a summation. So we get 4t of n minus 2 plus 15. And that's iteration 2. Make sense? So now we can continue. If we want to do a third iteration, well, we need to know what t of n minus 2 is. So we can do a side computation again. And every time you plug something in, you have to plug it into the original form up here. So we know we want to find t of n minus 2. Well, that's just 2 t of n minus 2 minus 1 plus 5, which, cleaning that up, is just 2t of n minus 3 plus 5. Now it's, I don't know, green. I like green. We know that t of n is equal to, we have the 4 from the last iteration times, well, we know what t of n minus 2 is now. That's 2t of n minus 3 plus 5, and then we have the plus 15. Now to clean this up, we can distribute again. I get 8t of n minus 3 plus 20 plus 15, which simplifies to 8t of n minus 3 plus 35. Everyone makes sense how we did that? I got one yes. Just want to make sure. Can I get a couple more? Just to make sure everyone gets this. Okay, cool. Just making sure, because I know this is confusing. Yeah, I can leave it for a quick minute. Sure. You're good, Christian. Give my hand a break anyway. Okay, cool. So now we have 3 iterations. Again, the one given to you counts as an iteration, which is nice. This one, we were actually told, I forgot to point this out, please explicitly show the work for the first 3 iterations. But if you're not told that, if you need to do more, you can. Don't do too many because it'll get a little complicated, but 3 is usually the good magic number here. And yes, this counts as showing work for the first iteration. First iteration is always given to you. So now, let's try to figure out the k iteration using the pattern here. So with the kth iteration, t of n is equal to, well, how do you think we can using each iteration's index value, how can we do a general pattern here? Let's just go one term at a time. But the first term on each iteration, how can I simplify that in terms of the index it's at? 2 to the k, exactly. Nice. So this is 2 to the k t of n minus, how about this term here? N minus k, exactly. N minus k. Then how about the last term? This one might be a little tricky. It might help the most to do it on the first iteration for this one. Oh, Ethan's got it. Nice. Yes, that's correct. This can be simplified as these extraneous terms as 5 times 2 to the k minus 1. And if you're ever not sure, just check it. So like on the first one, 5 times 2 to the first minus 1 is the same thing as 5 times 2 minus 1, which is the same thing as 5 times 1, which is 5. Then you try on the second one, 5 times 2 squared minus 1, that's 5 times 3, which is 15. And then same thing, you get the idea. So you might kind of just have to do some plug and chugging on the side. But does that make sense how this works? Kind of just doing these problems a lot. What I would do on the side here, Jesse, is like, okay, if I have the term 5 and then that's in relation to 1, the index, like if n is 1 and then like, this is the term. And the second one you have 10 and, or no, I'm sorry, 15 and 2 and then like it was 35 and 3. Usually it's some kind of like, um 2 to the something minus something, 3 to the something minus something, things like that. So it's kind of, yes, it does just take some practice. But does that help? No problem. Okay, so now that we have our kth pattern, let me just rewrite that. I don't like that. Uh-oh. Oh, there we go. Then my iPad froze. Now we have our kth iteration. Knowing that the base case of t sub 1 is equal to 1, we can solve for k. Right here. We use the base case right on this guy here every time. So on the side, if n minus k is equal to 1, well, then what's k equal to? What would k be equal to? N minus 1, exactly. You add the k over, you get n equals 1 plus k. Then if you just want k, k equals n minus 1. Cool. So now what we do, everywhere we see a k up here, we're going to simplify in n minus 1. Except here, since we use the base case, we're going to use that instead. So we know that t of n is equal to 2 to the n minus 1 now times t sub 1 plus 5 times 2 to the n minus 1 minus 1. So we can clean this up slightly. We have 2 to the n minus 1. This guy here just goes to 1 since we know that the base case is equal to 1 and anything times 1 is just itself. Then we have plus 5. The only thing we really can do is just distribute this out. So you have 5 times 2 to the n minus 1 minus 5. Okay, now we got to be a little careful here. Our goal, remember, is to get it in this form where a, b, and c are all integers. So I'll put that on the side so we have it. Okay, how do you think I can continue here? We're not actually that far off. Any ideas how we can keep going to get it in that form? You guys stuck? No, that's right, Jesse. That's exactly right. What you can do is if you have five of something and you have another of something, that's six of something, right? Here's a quick side note. If you have 5x and you have another x, wasn't that just 6x? Same thing. Same logic here. So we could simplify this to say you have 6 times 2 to the n minus 1 minus 5. Does that make sense, everybody? Okay, cool. Now we're really close. Any ideas? Because the only problem is we need to get this minus 1 in the exponent to go away. Because it has to be just a plain n. What could we do here? Exactly. We can simplify. Oh, wait, I see what do you mean simplify this? Like a pull out a 2 here? Like have it like 2 to, like you're saying 2 to the n times 2 to the negative 1? We could, but I don't really see how that would help us here. Well, actually, yes, you could do that. There's two ways you could approach this here. I'll show both here. So there's the way Elena just said. We could simplify this to be 6 times 2 to the n times 2 to the negative 1, oops, minus 5. Will someone tell me what's 2 to the negative 1? Not 1, 2 to the negative 1. What does it mean 1 half? You have to bring it to the denominator. So really this is the same thing as saying 6 times 2 to the n all over 2 minus 5, which is 3 times 2 to the n minus 5, which that is the correct answer. But the other way you could do this, both ways are valid. You could split up the 6 to be 3 times 2 times 2 to the n minus 1 minus 5. And then if you have two exponents with the same base, you add their exponents together. So this has an exponent of 1, remember. So it'd basically be 1 plus n minus 1, which is the same thing as n. So you'd have 3 times 2 to the n minus 5. Both approaches are valid and get you the correct answer. Does that make sense? The 6, um, that came from here, right? Oops, right here. Remember, it's like the same logic, Yeah, give me 1 second, Elena. So here, if I got 6 because remember, if you have just like think of algebra, if you have 5x, if you have 5 of something plus another of something, that's the same thing as 6 of something. If I have 5 apples in one hand and 1 apple in my other hand, I have a total of 6 apples. So if you have 1 of 2 to the n minus 1 and 5 of 2 to the n minus 1, you have 6 of 2 to the n minus 1. Does that make sense? No problem. Now, for the second approach, how I went from 6 to 3, I just realized that 6 is 2 times 3. Because I was thinking, if I want to get a factor of 2 so I can cancel out the exponent. So I'm like, hey, 6 is 2 times 3. And then I was able to smush it together. Any other questions with this? Does this make sense? Oops. This was all the question. We got it into this form as we were asked. Now, just as a quick side note, what if you were asked this instead? What's the big O running time of this? It would not be log n. It'd be 2 to the n. Don't overthink it. This is literally the only term that has power here, so it's just 2 to the n. Any other questions? Um, from where? Like, give me a line number. A log n situation would literally say log n. Like the k would be log n probably. Sure. Do you both approaches or just one of them? The right one. Sure. So the point when at this step we realize, okay, hey, we have an n minus one in the exponent of the two, but the question's asking us for just a plain n. So we need to get rid of that minus one. Now, how can you get rid of that minus one? If we had a two out here, you can add the exponents together. Since, you know, 2 to the first times 2 to the n minus 1, you add the exponents together, and that's just 2 to the n. So I thought to myself, okay, hey, how can I magically make a 2 appear? Well, 6 is the same thing as 3 times 2, and then you still have it multiplied by that other term. And then I was able to do this here and simplify it to this. Does that make sense? Cool. I can leave that there. Any other questions? Good questions. So that was a bit of a long one. Now let's do I'm just going to jump right into this one too. This was on my foundation exam, and I don't know why AJ called this one the evil. It is kind of evil. This is the evil recurrence. This one's pretty. I remember this one was pretty tough, and I remember I was so happy when I got the exam. I was like, yes, it's asking for a big O and not a final form. But this one's not going to be fun. But it's following the same process. So using the iteration technique, determine the big O solution to this recurrence below in terms of n. All right, here we go. Iteration 1 is given to us. T of n is equal to 2t of n over 2 plus n cubed. All right, so yeah, I know, it's an annoying question. So to do this, we first need to figure out what is t of n over 2. We'll go to the side. Well, remember, everywhere I see an n, I'm going to substitute it in n over 2. So we have t of n over 2 is equal to 2t of n over 2 all over 2 plus n over 2 quantity cubed, which this simplifies to 2t of n over 4 plus, and I'm gonna leave this alone, n over 2 cubed. You see, when I see something, I have an alarm bell ringing in my head. When I see something like this, leave it. Don't distribute anything. Because that I feel like a summation might be involved later. So now we're going to bring this over. We'll do blue. For iteration 2, we have t of n is equal to the 2 from before times 2t of n over 4 plus n over 2 quantity cubed. And actually, my apologies, I will distribute this out. This simplifies to n cubed over 8. Just distribute the 3. So it'll just be easier in the step, leave it like that. So this is, you'll get n cubed over 8 plus the n cubed from before. There we go, that's better. This is why I think color coding is helpful. So now if we want to keep going, we distribute this and this. So you get 4t of n over 4 plus n cubed over 4, n cubed over 4 plus n cubed. Does that make sense, what I did so far? Now this is where I'm like, okay, fractions, I'm not going to combine those. Let's leave those alone. Okay, now let's do another iteration. How come we had to put 2 n over 2 cubed? Um, because remember that's just the way exponents work up here. When you have a quantity to a whole exponent, it's the same thing as the numerator to the exponent and the denominator to the exponent. Does that answer your question? I see what you're saying. Because remember, it's like it's where you're substituting in, like, in a math problem. Anywhere you see an n, you have to substitute in n over 2 in this case. It counts for this as well, not just this guy. It counts for both. Does that help? All right. So, ready to keep going? All right. Now let's do the third iteration. We want t of n over 4. Now, plugging this into the original formula, you always got to do the original. That's equal to 2t of n over 4 all over 2 plus n over 4 cubed, which simplifies to 2t of n over 8 plus n cubed over 64. Now let's use green again. Nope, I wanted green. Thank you. Green again. Bring that over. So we're going to have t of n is equal to 4 times 2t of n over 8 plus n cubed over 64 plus n cubed over 4 plus n cubed from before. Now, once again, we distribute to get that a t of n over 8 plus n cubed over 64 divided by 4, 16 plus n cubed over 4 plus n cubed. This is why I think the color coding is helpful. Okay, and there's iteration 3. Great. We did 3 iterations. Time to find the kth iteration. So in the kth iteration, t of n, let's go term by term again. How is this related to each index, the first term at each final form? 2 to the k again. Good. 2 to the k. What about the term inside the t? 2 to the k again. Or yeah, n over 2 to the k. N over 2 to the k. Good. I just realized I zoomed in. Sorry about that. Now, what about these guys here? How can we represent that? You can't just do n over 2 to the k. Because remember, how n over 2 to the k, that would just basically say on this iteration here, well, that's just n over, that'd be n over 8. We don't even have that. That's not correct. Jacob's on the good rule of thumb, if you have fractions or terms like this you can't combine easily, it's almost always a summation. So yes, we need a summation. What do you think is going to go on? What do you forget the bounds for a second? What do you think the term inside the summation is going to be? The numerator should be pretty straightforward. N cubed, yes, for the numerator. And then, yes, Ethan's got it. It will be n cubed over 4 to the I. Because if you think about it, 4, 16, it would keep going. It won't be 2 to the I because you won't work out. You won't be able to get, there's no 2 anywhere, Jacob. So now what do you think the bounds are? Yes, you have to start at I equals 0. Because if you did I equals 1, if you did I equals 0, Think about it. If I is 0, that simplifies to n cubed, which is exactly what you want. If you started I equals 1, well, then that wouldn't work because then you get n cubed over 4 for the first iteration, which is wrong. Does that make sense? We have to start at I equals 0 versus 1. Make sense? Question mark? Yes, now what's the upper limit going to be? So let's think, what if it's k, let's see what happens if it's k. Well, let's just pretend k is equal to 3 for a minute. If k is equal to 3, that means you're going to get n cubed plus n cubed over 4 plus n cubed over 16 plus n cubed over 64. So that the upper limit is not k. You're close. Instead of k, it would be k minus 1, exactly. Since you don't want this extra term. Okay, great. We have the kth iteration. Now let's use the base case, which I'm pretty sure, yep, t of 1 is equal to 1. Yeah, that's another way to think about it too. It's k minus 1 because we're starting at 0, not 1. So using the base case, well, if t of 1 is equal to 1, that must mean that n over 2 to the k is equal to 1. What does that mean k is equal to? Well, multiply the 2 to the k over, n equals 2 to the k, so k equals log base 2 of n. By the way, if you see a log on the exam, just assume it's base 2. Anything with log, you can assume it's base 2, unless it's explicitly stated. Okay, great. So we have k. Now we can substitute that in. Gross t of n equals 2 to the log base 2 of n times t of 1 plus the summation of I equals 0 to log base 2 of n minus 1 of n cubed over 4 to the I. Okay, how's this guy simplify? N, exactly. So you get n, and then the t of 1 just goes to 1, so you get n plus the summation. Now, if you had to guess here, what do you think the big O is? N cube's a good guess. That I remember on the exam, I stopped here because I'm like, I don't even know what to even do. It is n cubed, yes, but let me just show you how to finish this. If you finish this with n cubed here, you'd only lose, I think, 1 or 2 points, which is pretty good overall. Um, but basically, this is not really explicitly stated that well. What you can realize is that this term is bigger, basically, that t of n is less than or equal to n times t of 1. Because remember, this whole thing is this. Because there's an n multiplied, that must mean this is bigger, is less than or equal to that. Because it's, I think also you can do that because it's big O. It means it's less than or equal to. But basically, what this allows you to do is turn this into an infinite summation. Why? I'm not fully sure. So then, if I wanted to solve this, well, what you can do is factor out an n cubed because that's not even doing anything. So you have n cubed times the summation of I equals 0 to infinity of 1 over 4 to the I, which is the same thing as n plus n cubed times the summation of I equals 0 to infinity of 1 over 4 quantity to the I, which then, what is this? not zero. Like what? Not generally. Like what kind of thing is that? I guess is what I'm asking. It's a series, exactly. That's an infinite series, an infinite geometric series, all the way from back up there. So if we remember, the sum of an infinite geometric series is the first term over 1 minus r. So this would simplify to n plus n cubed times, well, what's the first term in this summation? 1, exactly. The first term is 1. You have 1 over 1 minus, and then what's the ratio every time? It's just a fourth. 1 minus a fourth. So then you can simplify that even further. You get, here, let's add another page. Screw it. Oops. Hold on. There we go. Then you would get n plus n cubed times 1 over 3/4, which equals n plus n cubed times 4/3. Then there's really not much else you can do here. So then you can just be like, okay, it's just like easy stuff. The n cubed is the denominating term, get rid of the coefficient for final answer, big O of n cubed. The series formulas will not be given to you, so you need to memorize those. How is it infinity? Well, I'm being honest with you, I'm not fully sure. Yes, you get minus points for not memorizing a Calc 2 topic. Yeah, that's why it's called evil for a reason. It has something to do, I think, Jacob, with that, like, this is using the formal definition of big O, and then you just have to realize that this is going to eventually converge and it's an infinite geometric series. Yeah, I know. This is clearly a Guha question. Any other questions? Well, remember, if you could just get to here, and realize that it might probably n cubed, you get 80%, which is pretty good. Any other questions on this? How many sections are there today? I think there's 6 today. All right, so we're halfway done. Yay. And we're only 2 hours in, so we're basically right on track to be at 4 hours again. All right, so let's continue. Give our brains a break, do something a little easier. Sorting, yay! Sorting's fun. Sorting makes a lot of things run easier. Sorting algorithms, what you got to know. There's something missing here. I forgot about this again as well. So there are 6 sorting algorithms you need to know. 3 of them, their average running time and worst case running time is O of n squared, bubble, selection, and insertion. And 3 of them, their average running time is n log n, which is much better. Merge, quick, and heap sort. Just curious, how many of you do not know what heap sort is? Don't remember? That's okay. Vaguely. Okay. I could show it real quick in a minute. So, first off, let's just quickly go through everyone. Bubble sort is not is annoying. You start at the first element basically, and while it's smaller than the next, you swap it. You basically on every iteration, you bubble up the biggest element that's not sorted. So like here, 8's already sorted, but then I'm bubbling up 5 to where it needs to go. And then in the second iteration, we know 5 and 8 are already sorted. So then 4 gets bubbled up, and then 2 would get bubbled up, and 1, etc. Now there is a way you can make this terminate faster by using a flag variable to do the running time, make the running time better. But generally, this is n squared because it's a nested loop, as you can imagine. Next up is selection sort. I like this one. It's somewhat similar. Every time you basically, you start off on the left. Also, the thing I should point out too, bubble sort, good self check. The sorting should be bulging out from the top right to the bottom left, like this. If you notice that every time, it kind of bulges out like this. That's a good way to know if you're doing it right. Selection sort's the opposite. It bulges out the other way around eventually. Or no, wait. No, yeah, it's selection sort. This is one iteration. So yeah, selection sort. It's not in this picture, but it would bulge out like this in sorted order, basically. But anyway, selection sort on each iteration. You start at the first element that's quote unquote not sorted, which in this case is 20. You look for the smallest element in the rest of the array. Once you find it, you basically swap it with the position that you're trying to fill. In this case, it would be the first position here. So first, I'm like, okay, 12 is the smallest. Up 10 smaller. Up, I find out eventually later 2 is smaller. And since I'm trying to fill the first spots, I would swap 20 and 2 to get this guy here. And then you keep doing that over and over again for each iteration, but there's only one swap per iteration, whereas bubble sort had a bunch of swaps. Now, insertion sort, this is like the bookshelf sliding one. You start with element 1, and basically, you start here, not the element 0. You basically slide versus some swaps and whatnot. You basically slide each element into where it will go in the sorted array. So here I'm like, okay, 1 needs to go here. It's smaller than 23. Now 10, I'm like, so once you get this, I'm like, oh, okay, 10 goes between 1 and 23. So you get this. Then when you're doing 5, you're like, okay, 5 needs to go between 1 and 10. You get this. And then the last one, if you have 2 unsorted, okay, 2 needs to go between 1 and 5. So you just basically shift everything else over to get that. And you keep doing this over and over again. Merge sort, my personal favorite. You keep splitting the array into left and right halves. You keep cutting it in half every time until the length is less than 3. Once you hit a base case where you basically have 1 or 2 numbers individually, this is recursive, remember. You work your way back up and merge the smaller subarrays together. For each half, you do the left half first, then you do the right half, get that, and you finally get all that. This does require the use of an extra array, but this is a divide and conquer algorithm, and you get n log n, which is much faster. And also remember, if you have an odd amount sorted array, as you see here, the left half is always bigger, not the right. Keep that in mind. As you can see in this picture, the left half is always the bigger size. Quick sort, this is the one where you choose a pivot randomly. You choose the pivot, and then basically you have a low and a high variable that moves from the left and the right until they get what I like to call quote unquote stuck in the mud. It gets stuck in the mud on the left when you have a value that's bigger than the pivot, and on the right when it's smaller than the pivot. You keep doing that over and over again on each iteration until you have the low and high cross each other. And once you do that, you swap the pivot with the high and return the high index, because then you basically get the pivot in its magical index where it would go at the end. And the worst case runtime is big O of n squared, although generally it's n log n. Could somebody tell me the 2 scenarios that would cause the runtime of quicksort to be n squared? There are multiple versions of quicksort, yes. When I was in a grad class for a few weeks, it was taught very differently. You have to do it this way. Do it the way it's taught to you. Yes, bad pivot. So then what do you mean by bad pivot? Like where? If the pivot's on the end, the left or the right end, it doesn't matter. Then that would cause the worst case runtime, because intuitively it's kind of hard to imagine, but it basically have to go through every possible combination. Now, what's the other scenario? Anyone know? This one's not really emphasized as much. Not if the array is sorted. Although actually, now that I think about it, that might be a reason too, yes. So I guess there's 3 scenarios really. So we have 2. What's the third one? Yeah, if there's a duplicate of a number in the array, that also causes an issue. So just curious if you guys knew that, because sometimes it's asked. Um, yeah, so basically what I said, if the partition was always, this is the main one, if it is always the largest or smallest element, or on the ends, you'd always have to swap with all the others, making it a glorified bubble sort. Here's a cheat sheet of best, average, and worst case runtimes with stability and space complexity. Now, stability and space complexity was not on taught in the class when I took it. God, that was 2 years ago now. That's crazy. 2 years ago. Um, so I don't know if that's on the exam or not. It wouldn't hurt to know it, basically. But this is here. You can look at it later. Yeah, always a certain worst case unless said otherwise. So before we do a quick problems, I'll quickly reiterate what heap sort is. Generally, this is done with a min heap. So if I make up a heap, you all should know what a heap is. I think that's technically tomorrow's topic, but I'll cover it real quick anyway. If you have a min heap 5, 15, 38, 20, 25, 80, 7, no, that's not going to work, 99, 6, 7. I had to do it once today. If you add a heap, this is a min heap, or if you're at any element, you're smaller than your two children. So as a quick remember, so there are 7 elements in this heap. The way this heap sort would work is on the side ready to go, you'd have an array of 7 elements, or for space for 7 things, to basically store the sorted heap into. And the way this works is basically what you do is you have a for loop that runs n times. So in this case, it'd be 7 times. And on each iteration, you literally just call delete from the heap. And in the end, it will get sorted. Because remember how heap deletion works? You first immediately remove the root, and whatever is saved. In this case, it was 5. That gets returned, and you put that in the current iteration of the array. Then, how would deletion work? Well, then you bring up the element that's furthest to the bottom and all the way to the right in the tree. In this case, it's 67. And then you would percolate it down. So here it would, since it's a min heap, you'd want to swap it with 15 and then 25. You'd have 15, 25, 67. That's iteration 1 done. Then you do it again. So now you would get 15 in here. And then you bring up 99 because that's the one furthest to the bottom and all the way to the right. Then you swap with 25 and 67 as it's percolating. And you do it again, delete, get the root out, 25. Now you would bring up 80. Now to percolate this down, it just simply swaps to 38. Then you do it again, 38 gets removed and saved into the array. Now we bring up 99 once again. Now to percolate it down, it will swap with 67. Oops. Now, oh, whoops, I just read the same thing twice. I did. My bad. There we go. Do it again. Remove the roots. 67 goes away into the array. 80 gets brought up. Nothing gets changed. Do it again. Delete 80. Gone. And then 99 is the only thing left. Do it again. It'd be the root. Now that you lose the heap, but look, everything is sorted. Isn't that cool? And I guess technically you could do this with a max heap and then just flip the array, reverse the array after. But did that make sense? Yeah, it is funny, Jesse. It's true. So that's heap sort. So let's do a few questions, bubble, merge, and just runtimes and stuff. Here's a bubble sort. You want to try it or you want me to do it? I'll give you guys a minute here. Give my hand a break. Actually, I'll do 2 minutes. All right. Let's just do it. This one's kind of just got to know how it works. So bubble sort every time you go through each element and bubble up to the max if it can. So does 10 need to swap with 22? No, it does not. Because 10 is less than 22, so it stays alone. What about 22 and 16? Yes. So we'd have 10, 16, and 22 so far. Now, does 22 need to swap with 30? No. That's already good. Does 30 need to swap with 13? Yes. So instead, this comes 13 and 30. Now, does 30 need to swap with 17? Yes. We have 17. And then does 30 need to swap with 8? Yes. 8, 30. So there's the first row. So now 30 is sorted. Now we do it again. Does 10 need to swap with 16? No. So we have 10. Does 16 need to swap with 22? No. Does 13 need to swap with 22? Or does 22 need to swap with 13? Yes. Would 22 need to swap with 17? Yes. Would 22 need to swap with 8? Yes. So 22 would have to go here because 30 is already sorted. So we can now keep those the same for every following line. There we go. So now these two are fully sorted. Now we keep going. Would 10 need to swap with 16? No. Would 16 need to swap with 13? Yes. 16 to swap with 17? No. Would 17 need to swap with 8? Yes. So now these three are fully sorted now. Would 10 need to swap with 13? No. 13 to swap with 16? No. Would 8 need to swap with 17? Wait, hold on a second. That doesn't seem right. 10 needs to swap with 13? Yes. Would 13 swap with 16? No. Would 16 to swap with 8? Yes. 8, 16. There we go. So now all four of these guys are sorted. On this iteration, does 10 need to swap with 13? No. Does 13 swap with 8? Yes. 8, 13. And then on the last iteration, these two would swap and it would be sorted. Now, see what I mean? How it's the sorted elements kind of bulge out like this in like an upward staircase. See what I mean with that? That's a good way to self-check that you're doing it right. Selection sort, it's the same thing. It just comes from the other side. Any questions on this? Just kind of got to know how it works. All right, let's move on. It's a merge sort problem. I'll give you all a couple minutes to try this one out. Yeah, don't do this on pen in case you make a mistake. It's always on the left, Jesse, unless it's stated differently. This one it also says that in the question. Alrighty, let's go through it. So this is an odd-sized array. So as I said a minute ago, and as it says in the question here, and you can always assume this unless otherwise told, the left half will be bigger. So basically, this is the left half, and 6 through 10 is the right half. Now the nice thing is we can shortcut this a little. The right half of the array, 6 through 10, indices 6 through 10, remain unchanged through half of the iterations, the first half. So there's 10 merges. So for merges 1 to 5, they're literally identical. We can just shortcut that right now. Sorry, 1 second. 15, 15, 15, 15, 15. Because now remember, it does the left half first before the right. Okay, so now remember, basically it's going to split the left half in half again. So we go from 5 or 6, excuse me, to 3, and then from 3 to 1, because 3 divided by 2 within a computer is 1. So the first merge, you basically would have this guy and this guy. So when we merge that together, would anything change? No, it wouldn't. We'd have 13. Hold on a second. Yeah, no, it was not right. It's just, let me see that one more time. So you have, oh, wait, never mind. I'm stupid. No, wait. So yeah, you cut in half. And then, yeah, sorry. So since it's odd, you would get these two together and then this guy's alone. So yeah, there's nothing changes for the first merge. 13, 18, 19, 11 to 7. Now we need to merge these two with this guy. So would anything change again? Oh, no, wait, we just did. Jesus Christ. I'm sorry. The first merge, we just did merge these two with this guy. I apologize. Now we need to merge these. It would be these two with this guy. So would anything change here for these last three? Yeah. We're merging now, so we have to sort it. We get 2, 7, 11. Now, basically, we need to merge. We merge the two, all the three little ones, so we got to merge. Um, God, why am my brain is just like blanking all of a sudden. We need to merge the two halves together, but this feels a little early. Hold on, I'm glossing over a step. I maybe should have drawn this out. We merge these two, and we merge these two. Now we need to merge. Wouldn't it not be the two halves? What the hell am I missing here? Did I just draw this out? Let's draw it out. I think that's going to save everyone a headache. Okay, so we first start with. I'm just going to draw the left half for time. 1, 2, 3, 4, 5, 6, 7, 13, 18, 19, 11, 2, 7, 2, 7. Sorry. It should not be there. Okay, now we split it up in half again. So you have 13, 18, 19, 11, 2, 7. Cut it in half again. You'll have 13, 18. Yeah, okay, I see what I was doing wrong. My apologies. And you'll have 11 and 2 and 7. And you cut this in half again, you get 13, 18. That stays alone, then you get 11 and 2. Okay, so now we see all the merges. So we first merge these two. Great. That's what we did already in this guy. Then we would merge these two, which we just did again. No, that doesn't feel right either. Hold on a second. You always see the left half first. Sorry, I apologize. My brain shut down a little. Because the base case I thought the base case was always one. I guess. Oh no, wait. We just said it was two, didn't we? Yeah. Okay, that's what it is. Okay. 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 So we merged. Yeah, because the base case is two or less. We literally up here when the length is less than 3. Okay. I completely forgot about that part. My apologies. Okay. Now keeping that in mind. Okay. So we merge these guys. That's 1. We merge these guys. That's 2. So now we're here. Now we merge these 3 together. So we would get 13. That's what's wrong. Thank you, Russell. I thought that's what this was. Okay, we're gonna start over. I apologize because I see exactly what happened here. This is why you have to read the question. Normally, the left is bigger than the right if it's an odd size, but assuming the odd size it's relating to recursive calls that the right is bigger. So that's what's wrong here. Okay, yeah, I remember I did that exact same thing last time. Sorry about that again. So now we're gonna start over. This still applies. Okay. So now the right half is going to be the bigger one. So this doesn't change either because there's 11 elements. So this will get the right half gets 6, the left half gets 5. Okay. Okay. I think we're good now. 13, 18, 19, 11, 2. This is why you have to read the question carefully. Okay, so now we cut this in half. It's odd. So now the left gets smaller, 13, 18. The right is the bigger. This is not what merge stores usually like. That's why I was confused. Okay, so that is as small as it'll go. But this guy we got to break up one more time. You'll get 19 and then 11 and 2. Okay, so now we can start merging. This doesn't need to merge. It merges itself and remains unchanged. So you have 13 and 18, and then the rest remains the same. Now we merge these guys, so you'll have the left 2 be the same, but then you'll get 2, 11, and 19. Now we merge all of these together, which will give you 13, 18. 13, 18. Yeah, the first merge makes perfect sense. The second merge, those two shouldn't. Oh, I'm stupid. I'm sorry. I completely went over an iteration. You have to remember, I completely jumped. This counts as a merge, even though it's just one. So you get the same thing. 13, 18, 19, and then it merges these two. Jesus Christ. This just doesn't change, and then it merges those two. 211. There we go. Okay. Now, now it's going to merge these two guys. Did that make sense what I just did? So we did the left here. We merged that together. We did the left here. We merged that. It doesn't need to be merged, Jacob, because it's one alone. Then we did the right. We need to merge those two together. Okay, now we're on the right track. Now we merge the three together on the right. We did 13, 18, 2, 11, 19. Okay, there we go. There we go. There we go. Now we merge the five together. So we get 2, 11, 13, 18, 19. Okay. Okay. There we go. Now we're on the right track, finally. So now the left half is good to go. Let me actually just erase this. So you might not, maybe the shortcut wasn't the best idea. But now we have to do the same thing with the right half. So now there's 6 things, right? 1, 2, 3. Yep, 6. We had 7, 4, 15, 6, 12, and 1. So cut it in half with the right always bigger. So 7, 4, 15, 6, 12, and 1. 7, 4, and 15. 6 and 12. I just did the old trick. Oops. 6, 12, and 1. Okay. So now we continue. So now the nice thing is, all the way until the end, the left half remains the same until the final merge. Okay. Now we just got to deal with this carefully. So this has a merge. It doesn't change anything. So you'll have 7, 4, 15, 6, 12, and 1. Now we merge this guy. So now we have, still doesn't change. Then we have to do this guy, right? Nope, I'm sorry. We have to merge this guy. You got to do the left half first. 4, 7, 15. Yeah, this is right. Now we do the right half. This gets its own merge. So nothing changes visually. Hold on. Oh, why did I write 7? Generation. Something went wrong here again. Oh my God. I'm so embarrassed. Okay. So this is why I like normal merge sort better. Yeah, I did an extra iteration. Yeah, we don't need to do this guy. So we just merge 4 and 15. Doesn't change there. We already did that. Then we merge these guys. So yeah, this is wrong. Now this is basically starting the second half over again. So now, okay. So this doesn't do anything. That's what I did before. I don't know why I did that mistake. Sorry. So this gets its own merge. Nothing changes, which we have already. Then now these guys merge. 4, 7, 15, 6, 12, 1. There we go. Okay. Now the left half is good. Now we do this guy. 6, 112. Then we do this guy. Then we do these guys. There we go. And then, Jesus Christ, I did it. I know, it is like that. So yeah, the doozy was, it's confusing because, the right is bigger than the left. Does that make sense how I did that? I am so sorry. Anyone have a question? Correct. Yeah, it's only one thing. What's it supposed to merge with? It can't merge with anything. Any other questions? I apologize again about that. Got it. 2 years, 2 semesters in a row. I'm making sure next time I change this question. All right, let's do something probably a little easier. This will be good. Okay, right away, before you guys even try the top, let's just do this. What's the average case runtime of insertion sorts? N squared, good. It's always n squared almost. What what's about selection? N squared again, good. What about heap sort? N log n, good. Merge, n log n. Heap sort is n log n, not log n. Be careful. And then what about quick sort? Average. N log n. Good. Quick sort's average n log n. This is why though, like someone asked, if it'll tell you if it's average. Okay, now this question, do you guys want to try it or okay? Try it for and then see if you get an answer. I'll give you guys like 2.5 minutes. My reason, no, your reasoning is actually doing it. Anyone get an answer? $25 is the correct answer. Good job. Let me go through it real quick for everybody else. So each move is basically a swap. It just asks how many swaps there are. So we're just going to keep a tally on iteration. I'll just count them. So for 35, you don't really do anything. You should always start at the first. You start here for insertion sort. Remember, this is the book sliding. So remember, it just basically, at each element, it slides over to where it needs to go by swapping. So in the first iteration, 25 needs to swap once to get to where it needs to go. So we can draw this out. So we have 25, 35, 15, 29, 39, 22, 19, 6 and 6, and 21. Okay, so that's 1. Now we're good there. Now we move up to 15. 15 would need to go before 25. So we'll take 2 swaps for it to get there. So you get 2. Then 35, well, it's already in the right place, so nothing. Now we have 29. It needs to swap once because it needs to get before 35. Add a 1. 39 is all good. 0. 22 needs to get all the way before 25. That would be 1, 2, 3, 4 swaps. All right, right, 22. Oops. $19 needs to go all the way before 22, so that's 1, 2, 3, 4, 5 swaps. Five. I got room. We were at 6. 6 needs to go all the way to the beginning, which is 7 away. They're good enough. And then 21 needs to go before 22, which is 1, 2, 3, 4, 5 away. Let me write that down. Squeeze it in. And now that the array is sorted, we just add this together. 1 plus 2 is 3. You got plus 1 is 4. Plus another 4 is 8. Plus another 5 is 13. Plus 7 is 20. Plus another 5 is indeed 25 swaps total. Make sense? Questions? What's up, Christian? Yeah, you got to write each swap for the reasoning. You basically be like, this number swapped 1 time. This number did 5, whatever it is. Yeah, so basically like 35, like the last one, 6 had to go all the way to the beginning because it's like, okay, 6 comes before 39, before 35, before 29, before blah 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 blah, all the way it comes before 15, so let's go there basically. You basically compare it to all the past ones and see where it needs to go. Does that make sense, Christian? No problem. All right. That concludes sorting. Sorry again about that mess before. Let's keep rolling. Binary trees, binary search trees. Yay! Oh, hold on. Yeah, basically, Deborah. Basically, what you'd have to do. All right, binary search tree. What the hell's the difference between them? Well, binary tree is just a hierarchical data. I don't know. I did not say that right. Hierarchical data structure comprised of nodes, where each node has at most 2 children, which are referred to as the left and right child, and there's no really rules between them. No matter what, though, The searching, insertion, and deletion is linear time because nothing's sorted or anything. Binary search tree, the other hand, there's a specific ordering property for any node. All elements in the left subtree are smaller than its value, and all elements in the right are bigger, which facilitates better searching, insertion, and deletion because you can basically do logarithmic runtime by binary search in the best case scenario. However, there is a worst case scenario where the time complexity does go to linear time, aka it's just a linked list, basically. Yeah, I love that guy. Are those like the sorting in 2 minute videos? Those are great. But yeah, just be careful with the quick sort approach. Primary properties of a binary tree. The height is defined as the number of edges from the root node to the deepest leaf node. Say basically it's the longest path as well from the height from the root to the leaf. Same thing as the depth. A full binary tree is that all nodes except the leaves have two children. Each node is full of children. A complete binary tree is that all levels of the tree are completely full, but not the last. A complete tree must be filled from left to right. In a balanced binary tree, the height of the left and right subtrees of every node differ by at most one, aka an AVL tree. We'll get there later. The in-order, pre-order, and post-order traversals of a binary tree are the three common ways to traverse the tree. We'll get to that right now. We pretty much said all this already. The left and right subtree must also be a binary search tree, and them typically are not duplicate nodes. So here's examples. The left one's a valid binary search tree, satisfies all the properties. The middle one is not a binary search tree because 6 should be to the left of 7. That was not intended. This picture was already here. And then the second one is not a valid binary search tree because why is that not isn't that valid? Oh, it's not valid because they're putting 3 to the left of 2 when it should be to the right of 2. Kind of just looks weird in that picture. So pre-order traversal, you go root, left, right. You just follow that traversal all the way through. In order traversal is left, root, right. Now in a binary search tree, this will print everything out in sorted order. Here it's not in sorted order because this is just a binary tree, not a binary search tree. In a post-order traversal, you go left, right, root. That's the best way to free like a binary search tree. You got to use post-order. Inserting, you always compare. You work your way down basically based on the binary search tree property to where it would go. So if you're inserting 40 here, well, it's less than 100, bigger than 20, bigger than 30. So then it would go here. You always insert out a leaf. Deleting, there's 3 cases. Deleting a leaf node, you just kill it. It's gone. Deleting a single child, a node with a single child, you just basically bring up the value, its child, and the whole subtree below it, and then delete the node that you want it to delete. And then after that, deleting a node where it has 2 children, we want to delete 50 here, you either bring up the max from the left subtree, so 40 here, or the min from the right subtree, which is 60. And then you delete that leaf node instead. Or not delete that, whatever node that is instead. So hopefully that's a recap for you. 3, any quick questions before we get into these questions? Finally, a conceptual one. All right, let's do it. This one's a good one, pretty new. Hopefully I won't mess this up. Give it a minute, give you like 2 minutes to try it. After binary trees, there's just AVL trees, and then we're done for today. Yes, you have to use the ABC method. You really find that confusing? I think that's the easiest thing ever once you get the hang of it. Oh, scroll up. I'm sorry. Scroll up to what? To this? Or Ooh. Is that what you needed? Whoever wanted to scroll up? No problem. Okay. Give this one a try for like 2.5 minutes. It's not a binary search tree. It's just a binary tree. Gotta be careful with that. You're good. Okay, so let's go through this. This code, when passed to the root of the following binary tree, returns a result. If the function what does it do is called on this tree, for each value, indicate whether it gets added or subtracted with respect to the original call of the tree. No need to state the final return value. So you're given a general binary tree structure. Let's go through this together. So we're starting at the root. Is the root null? No. So skip that. This here is basically saying, is it a leaf node? No. Here it's checking, does it only have a right child? No. Does it only have a left child? No. Is the left child bigger than the right? No. So we're doing this here at the bottom. So we're turning root data plus, so it's being added, so that would get an A, plus the right, so it's adding the right, so it's adding 22, but then it's subtracting the left, 16, so this will get subtracted. Does that make sense? So now we're going down to the right. Usually the left gets executed first because that's usually what it's called, but this time it's the right, so we're going down the right. Okay, it already has two children, so I'm going to skip right down to this part again. Now, is the left bigger than the right? Yes. So now we already know what happened to 22. Okay, but 40 is now going to be added. And then 25 would be subtracted. And we're going this way. Okay, now it has two children again. We're going to the last two if statements. The right is bigger than the left, so it's the bottom case again. So we're going to be going. First, we're going to be going. Jesus Christ, I just blinked out for a second. Sorry. So we're adding on the right child, 23. And then we are subtracting the left child of 14. Now we go this way first. It does not have any children, so it's just going to return. Now we go here, same thing. Now back at 22, we go over here. Doesn't have any children, same thing. Now we're back up at 30. Now we're going over to the left. 16 has two children, and we can see that the left is bigger than the right. So we're going to add 19 and subtract 18. No, I got that backwards. Sorry. We're going to subtract 19 and add 18. There we go. Because the left is bigger than the right. Hold on a second. We're at 16. The left, it has two children. The left is bigger than the right. So we're adding 19, right? Yeah. That's not what the key says. I'm confused. Don't you guys say add? That's what it's. Yeah, me too. Oh, yeah, you're right. Because respect to the original call of the root. Yeah. So because 16 was being subtracted, Jesus, it flips them all. Okay. Okay, this is subtracted and added. And then 6, well, it's a left child, so it would add it. So 6 would be added. Yeah, that's stupid. There you go. 18 got added um it because that's just what the code says to do. Because normally it's subtracted, but we flipped everything. Because That's what they mean by with respect to the original call in the root. That's really deceiving. Yeah, me neither. That's dumb. That's really stupid. Any other questions? I? Is that what this is? Yeah, we flipped them, Christian, because 16 was being subtracted by 30. So then everything here has to get flipped, basically. We're told this. You won't ever get minus points. No problem. Okay, let's do a quick coding question. This one's going to be a little tedious, I think. Let's just jump into this. All right. Demonstrate your understanding of rewriting the following recursive function, which operates as a binary tree, as an iterative function. So with a loop, basically. In doing so, you must abide by the following restrictions. No helper functions and no recursive calls. All right, so let's just take this slowly. Let's first work with, if you think about it, well, I'm pretty much all but the first two cases, there's some multiplication going on. So I think it'd be helpful to have some kind of counter thing, like a tracker variable. Doesn't that make sense? That makes sense to me. So we need to have a tracker. Int count. And we initialize it to 1 since it's multiplication. Okay, so now what we can do, we need to loop, obviously. So we don't need to check if it's null. Well, we do, yes, but we can do this with the while loop, right? Can we just check in the loop, hey, like while root is not equal to null? Yeah, let me maybe call it Walker. I think that might be a little more easier. Node Walker equals root. Okay, so we can just do a loop. Yeah, you got to be careful with that. You only do initialize the counter to 0 if it's addition. So, okay, so what we can do, you guys, is think like, okay, while root, or Walker, excuse me, Walker does not equal to null, because if that's true, then we can just skip all this and return 1 anyway, right? Pretty easy. Okay, so now let's go through all these cases. So we have to check, okay, hey, if root left is equal to null, so basically if it doesn't have any children, return 2. So how would I check that? How would I check if it has 2 children and return 2? Anybody? Yeah, exactly. Just check, hey, is the Walker null? If Walker arrow left is equal to null and Walker arrow right is equal to null, well, all you got to do is just return 2. Okay? Now, else, if, well, what's the third case? The third case, you basically check if it's a left child, or I'm sorry, if it only is a right child, and then if it does, return 3 and the traversal to the right child. So how do you think you would do that? Ideas? Well, first, how would you check if if it only has a right child? Exactly. If Walker left is equal to null. Now, remember, this isn't recursive. We can't do any recursive calls here. You can return because it's a loop. You can always do that. Oh, no, wait. I see what you're saying. No, wait. Yeah, we can just return, couldn't we? For the first, this with two? I don't see what's wrong with that. Because you're basically done traversing. Oh, no, wait. Yeah, I see what you're saying because you have to get all the extra stuff. So, yeah, this is wrong. You can't just return two. Okay, how do we fix this? How could we basically count not equals to? Be careful. Think about what was happening in all the other ones with recursive calls. We're not adding, we're multiplying. Good. Count times equals to. And then how would we stop the traversal? Well, the loop has to stop. I mean, you could return count here, sure. Break, that also works. You could, the thing I was going for was just make the walker null. But yeah, you could break, you could return the count there. Any of those work. I'm just gonna write this. They all work because this just terminates the loop. Okay, so now we're back to this case. So we checked if it has a rat child only. So then how would I get update the count for three? Good. Count times equals three. Now here's the question. Now what would I do based on the original problem? Exactly. Walker goes to the right. Good. Okay. Well, case four is literally the same thing, just the opposite with the number four. So I'm just going to copy this. This just becomes right. This becomes a four. This becomes a left. Okay, great. That's case four. Case five. Very similar. How would I write case five? You have to do an else if because there's two more cases. You have to do else if too because if this one fails, you don't want to just jump straight to this one. You might want to get down here. Yeah, you got it exactly. Else if Walker, you're just checking the data like before. If Walker writes data is greater than Walker left data, well, then you multiply the counter by 5, and Walker goes to the right. Otherwise, another page. Otherwise, else count times equals 6, and then it goes left. And then finally, once you get out of the loop, return the count. That one was more tricky than I thought it would be. But there you go, that's it. Does that all make sense, what we did there? Any questions or anything? FE is always 12 questions. No, this is iteratively. The whole point was to do this iteratively. Iterative means no recursive calls and using loops instead. Yes, it would result in the same as recursive. Yep, yeah. We're not overwriting Walker, we're just updating its pointer where to traverse. That's like making the recursive call. Yes, it doesn't need to go back here necessarily because we're just updating a counter the whole way. We're not having it to like have to check other things and update other things along the way. Yeah, the only thing getting overridden is the count. It can go left and right, no problem, because it's like, you're just going through. It's like, okay, go right, now go left, go right, go left. It doesn't need to go back up like the recursive tree at all here. Basically, this function is just going straight down and not going back up. It is kind of weird. And then now most of this stuff is recursive. But like in this scenario, it's just like it's going whoop, 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 whoop. And it's not going back up. But that's not needed for the original function anyway. Does that make sense, Jesse? Right. It doesn't go back up. It can't. But it doesn't need to because we're updating the counter along the way. You're good. All right. I'm getting tired. Here's the next question. The last question for this. AVL should be pretty quick after. I'm just going to get right into this one for time. Write a recursive function. This one's actually not too bad. Write a recursive function named sum at depth that takes a pointer to the root of a binary tree, root, and a non-negative integer, depth, and returns the sum of all the values in the nodes that are at a level depth below the root. For example, if you pass the root of the following binary tree and depth equals 2, the function should return 61 because everything at that level, 3 plus 8 plus 20 plus 30 is 61. And all those nodes are 2 levels below the root node of the tree. You may assume that depth is non-negative. You must write your solution in a single function and cannot write any helper functions. Okay, how do you think we can do this? Don't overthink this one. It's recursive. So what do you think our base case or base cases will be? Exactly. Always, if the root's null, then you can't, there's nothing in the tree. It just returns 0. Okay, so now how do you think we're gonna do this? We're given a non-negative integer, so like you're passed in the root and the number two. Yes, that's another good start, Ethan. Because if the depth is equal to zero, well then the only thing is just the root. So you got to return the root. This also works because you'll see in a second. You guys getting a little ahead of me. That's okay. This is the main base case here. Why? Because basically all you have to do, you just traverse through the whole tree and decrement the depth value each time on each recursive call. And if the depth equals zero, that means you're at the depth you want. So just return that data and you just add them all together. That's literally all it is. Does that make sense? Did that make sense what I just said? Okay. So how do we write this? Well, return sum. I'm just going to write SAD. Don't abbreviate on the exam. Root left. You just decrement the depth. Depth minus one plus sad. I'm run out of room. Root right depth minus one. That's it. That's literally the whole function. Because think about it, okay, the root's not null, and I want to get everything in index two. Go decrement the depth by one, decrement it again. Okay, now it must be at the one I want. Return it. Then add that with the other side. Then back up top, get this side and that side. Does that make sense to everybody how this works? I probably, I did go jump into that one a little faster, but I want to make sure we finish by 5 o'clock if we can. Any questions, confusion, or anything? It makes sense how you were able to come up with that. Like you'd be able to do that on your own on the exam. Okay, good. All right, let's finish this thing for today. AVL trees, last topic. I love AVL trees, one of my personal favorites. So, what is an AVL tree? It's a self-balancing binary search tree where the heights between the left and the right subtrees for any node cannot be more than one. It's known as the balance factor of the node. This is an AVL tree here because the heights of the left and right subtree for each node is less than one, or less than or equal to one, excuse me. Yeah, I agree. Binary search tree code is a lot easier than DMA and stuff. You find the balance factor of a node by taking the height of the left subtree minus the height of the right subtree, or vice versa. I just always do the first one, the height of the left minus the height of the right. It can only be between negative ones, or it can only be negative one, 0, or 1. If it's not any of those three numbers I just said, it is invalid and must be rebalanced at that node. Leaf nodes always have a balance of 0. Keep that in mind. Balance factor of 0 at a leaf node. You don't really need to worry about rotations because I'm going to gloss over this because you guys need to all know the ABC method, which you know here is here. No matter what, using ABC, any of the four scenarios results in this, which is exactly what you want. Here the ABC method. Once you have the three nodes you want to redo, the smallest of the three is A, the middle is B, the biggest is C, and then you rebalance it just like that. That's funny. I just realized that's my own handwriting. I don't know when this is from. So insertion and deletion are identical to binary search trees, but require two additional steps. No matter what, you always, no matter what, where you insert or delete up to the root, you have to delete, or you check, excuse me, wherever you insert or delete, you start it where you insert, you did the thing, go all the way up to the root, and every node you got to recalculate the balance factor. And if you need to do a rotation, do it. So really, it's just following the process. Let's just get right on into it. All right. Insert the following integers into an AVL tree in the given order. Whenever an insertion causes the tree to become imbalanced, rebalance it immediately before proceeding. Continue this process until all elements have been added. Put a box around the state of the tree after each of the bolded and underlined elements are inserted, which are each worth a point. All right, let's do it. Ready? Just following the process. You insert 50, there's nothing there. It's the root, and its balance factor would be 0 because it's a leaf, technically. Okay, great. 80, where would 80 go? To the right of 50 because it's like the binary search tree insertion. What's the height? What's 80's balance factor? 0 because it's a leaf. And what's 50's balance factor? Be careful. I guess 1 technically if you do right minus left, but -1, yeah. But it's fine. Regardless, it's fine. Okay? Now we had 70. Where's 70 going to go? Left of 80. Good. What's the height of, and remember, you always start from where you inserted and check all the balance factors all the way up to the root. What's the height of, what's the balance factor of 70? 0, because it's a leaf. What about 80? 1 or -1. It doesn't matter. You can do right minus left or left minus right. It doesn't matter. But yeah, it's fine. It's 1 or -1. Doesn't matter. And then what's the balance factor of 50? 2 or -2, which is a problem because it has to be between -1, 0, or 1. So remember with insertion, you mark the node, immediately mark the node that has the problem, and you take 2 steps towards the insertion point. So I'm going to mark 80 and then 70. And then remember, A is the smallest of the 3, then B is the one in between, and C is the biggest. And then you just rewrite it like this, B, A, C. So this would be rewritten as 70, 50, and 80. And now that we did that, we fully inserted 70, and that's our first box. Make sense to everybody? Just follow in the process. Yeah, A is always the smallest, and C is always the biggest. Did you not know that, I assume? Yeah, who'd you have? I'm just curious. Gotcha. Okay. So now we keep going. Well, it's nice to see people here that weren't in Ahmed's section. If these balance factor was 2 because the height of the left subtree is -1. Anything that's not there is -1. And the height of the right subtree is 0, 1. -1 minus 1 is -2. Or you did the other way around, you get 2. Does that make sense, Deborah? Cool. All right, so let's keep going. We're going to insert 99. So where's it going to go? Right of 80. Good. That balance factor you know is good already because it's a leaf. What's the balance factor of 80? -1. Good. Or 1 if you did it the other way around. It's fine. Then what's the balance factor of 70? -1. Because the height of the left subtree is 0. The height of the right subtree is 0, 1. 0 minus -1, or 0 minus 1 is -1. So you're good. Now, do I need to check the balance factor of 50? Not because it's a leaf. The answer is no, because you only have to insert, you only have to check from where you insert all the way up to the root. That's it. Nothing else. You just follow the path straight up to the root. Nothing else. All right, so let's keep going. 85. Where's it going to go? Left of 99. Good. We know 85 is good. So remember, we're just checking this path only. What's the is 99 good? '99's fine. Because the height of the left subtree is 0, height of the right subtree is -1. 0 minus -1 is 1. Now 80, the height of the left subtree is -1. The height of the right subtree is 0, 1, which is not good. We need to rebalance. So again, you follow the process. Mark the node that has the problem. Take 2 steps towards the insertion point. The smallest is A, the middle is B, the biggest is C, and then we restructure it as we did a minute ago. You get 7, you leave everything else alone here, and now you'll get 85, 80, 99. Now you can, thing I like, you can do a quick self-check, make sure you didn't mess up. What's the balance factor of 85 now? Well, it's 0, so you're good. Now we keep going. What's the balance factor of 70? Yeah, you got to go all the way to the root every time. The balance factor of 70 is -1, so we're good. And that's our second picture they asked for. We can keep going. We have 3 more to go. All right. Now we insert a hunt. Oh, let me actually, sorry, just label this for later. There we go. Okay. Now we want to insert 100. So where's it going to go? Good. Right at 99. 100 we know is good. 99, is it good? 70 is crying is crazy. 99 is fine. Its balance factor is -1. 85. -1, so it's good. Do we need to check 80? No, because it's not on the path to the root. Do that. Now 70, what's the balance factor for 70? Yeah, it's -2 because the height of the left subtree is 0. Height of the right subtree is -2. That's a problem. So you mark the node that has the problem. Take 2 steps towards the node you inserted. 85, 99. A is 70 because it's the smallest. B is 85 because it's in between. C is the biggest, so and that's 99. So first, this becomes 85, 70, 99. Now, there's that T0, T1, T2, T3 thing. I don't like that. I just kind of eyeball it. The way I like to think about it is, okay, if something's going to go to the left of 70, what does it mean? It has to be smaller than 70. So what needs to go to the left of 70 in this restructure? 50, exactly. Now, if something goes to the right of 70, that must mean it's bigger than 70, but smaller than 85. So what should go there? Anything? 80, exactly. Good. Now, what about to the left of 99? That must be bigger than 85, but smaller than 99. Anything go there? Nothing. Good. To the right of 99 must be bigger than 99, so 100 goes there. So now we can do a quick recheck. The balance factor of 85 is now 0, so we're perfect. Good job there. Makes sense so far? We're just following the process. Now we keep going. We have 2 left. What was the next number? 95. Okay. Where's 95 going to go? Left of 99. Good. Just normal binary search tree insertion. Okay. We know that balance factor is good. 99, A-okay. 85, how's 85? Well, you can immediately see that both trees are same height, so it's good. Great. Last up. Oh, whoops. There we go. Okay, we need to insert 84. Where's it going to go? Right of 80. Good. Just normal binary search tree insertion. 84's balance factor. A-okay, because it's a leaf. How's 80? Good, because it's -1. How's 70? Also -1. Good. How's 85? It's 1, because height of the left subtree is 0, 1, 2. Height of the right subtree is 0, 1. So we didn't need to do another rotation. And there we go. We did it. Did that all make sense to everybody? Any questions or confusion? Just follow in that process. Yeah, I told you it's game changing once I get the hang of it. Questions, comments? All right, let's do the next one. Deletion. Very similar, except should be shorter. Show the result of deleting the value 8. The first. What do you mean the first children at 0? Yeah, because if there's one node in the tree, the height of the left subtree is -1, and height of the right subtree is -1. -1 minus -1 is 0. Oh. Yeah. That's just how it is. Yeah. The first link is 0. That's just how it is. I don't know why. It goes to like 0. What is happening with my pen? Oh, my pen just died. Not now. Crap. Hold on. It takes like 30. I think it always says like if you charge it for 30 seconds, that gives you like 30 minutes of battery, which is kind of wild to think about. Right, hold on one second. I am not finger painting. I'm so bad at it. You sound like Ahmed. That's what he would say. Okay. Yeah, it's yelling at me. Okay. So yeah, like this is 0, and then that's 1, and so on. That's just how it is. Okay. Deletion. Show the result of deleting 8. In this process, there are 2 rebalances. Show the state after each. Okay, so what's the first step in deletion? Follow the process. You kill the node that needs to go away. It's gone. All right, so now you do the same thing. You just work your way up to the root, checking the balance factor along the way of each node. So, how's 15? Is it good? Correct. It's sad because the height of the left subtree is now -1, and height of the right subtree is 1. -1 minus 1 is -2, which is a problem. Now, this is slightly different than insertion. You still mark the node you're at, but then you take 2 steps away from the deletion point. So basically, you would rebalance. You would have to just basically get these 2. You go down. You don't go up. You basically go down, like you go down its mirror copy side. So if it was 46, for example, you would do this. So same thing though. A, B, C. 15 is the A because it's smallest. B and C, and then the restructuring is the exact same. So everything else gets left alone. 49, 46, 35, 60, 53, 58, 70. Now we can do what we just did. 18 is B, and 15 and 23. Cool. Makes sense what I just did there? Now we can just do a quick recheck to make sure we did it right. You can already tell they're both the same height, so 18 should be good. Okay, but we're not done. We have to go all the way to the root, remember. You have to keep going. Now 27, what's the balance factor of 27? -2, because the height of the left subtree is 1, but the height of the right subtree is 0, 1, 2, 3. So mark the node that has the problem. Now you take 2 steps away from the deletion. So which way would I go? 18 or 49? 49. Good. Because you're going away, the opposite. That was going the opposite direction. Now do I go to 46 or 60? You go to 60. You go to 60 because it has the longer subtree. You always go to the one that has the longer subtree. If they both have the same subtree height, well, pretend 58 wasn't here for a quick second, then you go in the direction you came from. So you'd still go to 60 anyway in this case. Here's your A, B, C. Now we get to do the fun guess and check again. 49, 27, 60. So what goes to the left of 27? Everything smaller than it, and you keep the rest the same. 18, 15, 23. To the right of 27 is everything bigger than 27 and smaller than 49. So you have 46 and then 35. You keep the structure the same. To the left of 60 is everything bigger than 49 but smaller than 60. So you have 53 and 58. To the right of 60 is everything bigger than 60, which is just 70. And do a quick self-check. The balance factor of 49 is now 0, 1, 2, minus 0, 1, 2, which is 0. So we're set. And there you go. That's it. Questions? Make sense? Cool. All right, last question of the night. Let's see if we can do this by 5 o'clock. There is a unique AVL tree with the height of 4 with 12 nodes. And so remember, height of 4, that means 5 technically, because there's the extra. The first level is 0. With 12 nodes storing the integers 1 through 12 inclusive, such that for every non-leaf node, the left subtree is strictly shorter than the right subtree. Part A is just draw this tree. Now, how do you think we would do this? This one's a bit of a doozy. Correct. The height means 4, so that means it's 5 levels. Yes. So that's one thing to keep in mind. Let's write that down. So really, it's just one of the big things. We have to have 5 levels. And obviously the numbers 1 through 12. Now, but every non-leaf node has to have the left subtree strictly shorter than the right. So let's think about this. What number, give me like a few numbers you think might be the root. Could be 8. What else could it be? Could be 5, 7. Basically, what I'm getting at is like 1 or 12 is not going to be the root. Because remember, we have to satisfy the binary search tree property. Did you do 6 or 7 on purpose? So, honestly, the best thing to do here might just be kind of some trial and error. I like the way you think. Yeah, that's a good point. 5 should be the root because if you think about it, after 5, from 5 to 12, that is crazy to say it's fatter. Everything to the right, there's more numbers from 5 to 12 than there is from like 6 to 12 or 7 to 12 to 8 to 12 or whatever. And then, so 5 should be the root. Yes. Okay, so now let's do the left first. Okay, what number do you think should go on the left? Do that same logic again. 2, exactly. Because from 2 to 5, there's 2 numbers, and that could still satisfy the property. Because if you did 3, there'd only be 1, so it's too small. So if you did 2, then what would have to go to the left of 2? Well, then just 1, because we're still doing the binary search tree property. Then no matter what, 3 would have to go here, and 4 would have to go here. Does that make sense? Okay, so now let's just do the other side. What would be to the right of 5? Be careful. This is so sad to say, but I like the way that you kind of did the analogy of like that the right side of the tree is fatter. Can I use that analogy again? Okay, you said 7. So if we did 7, let's think. If we did 7, there's 8, 9, 10, 11, 12. There's 5 numbers to the right. So let's try it. A lot of you said 7. So if we did 7, that means 6 would have to go to the left. And then 8 would go over here. Anything else could go over here. So you'd have to put 9 and then 8. And then 10. You'd have to do 11. No, this wouldn't work. See? Because here, this wouldn't work down here. Because the trees here are the same height. Okay, so let's try 8. A couple of people said 8. We did 8. But then to the left. Well, so what would go to the right, you think? 10, because you got to have 9 go to the left afterwards. Okay, so then what would go to the left of. You think 7 or 6 would go to the left of 8? It's kind of just plug and chug, honestly, in my opinion. Yeah, the left would be 6, so we can make sure that the right is bigger. So you'd have 7. Otherwise, it wouldn't work. Then after 10, well, you can only do 11. We could do 12. But actually, you can't do 12 because then the left would be smaller than the right, which is not what you want. You'd have 11 and then 12. And this, my friends, is that special binary search tree. Basically, you'd have to explain it, basically what your thought process was. It says right on it, give full credit for general logic in the direction of figuring it out. So if you could eventually come up with this, you should be good. Any other questions, comments, concerns? Yeah, that's a good way to think about it too. All right. Well, long 4 hours again. Thank you to the 11 of you who stuck through it all. That is day 2 of the Spring 2026 Foundation Exam Crash Course. All right, so welcome back. This is day 3 of the Spring 2026 Foundation Exam Crash Course. We're almost done. I'm hoping today won't be as long as the other 2 days. I think today's topics will go by a little faster. I'll throw the slides in the chat for you all. There you go. If you want to follow along with me. Anyone have any quick questions or anything before we get started? All right. Well, let's get into it. Day 3, the final day. Today's going to mainly involve base conversion, bitwise operators, binary search. There's no questions. I'll just briefly go over it again. Then heaps, tries, and hash tables. Hashing and base conversion, I can imagine, will go pretty quick. I think bitwise will take the longest, and then heaps and tries will kind of be like somewhere in between. I think heaps will go faster than tries. But we'll see how we do. I'd like to be done by 1 o'clock, hopefully 3 hours instead of 4 today. But if it is 4, I mean, it's not the end of the world. So we'll just see how we do. Let's get right on into it. If nobody has anything else to say or any questions or anything, let's just do this thing. So start off with good old base conversion, probably one of the easiest topics on the foundation exam. Everybody says this is always free points, and for good reason. It's pretty easy once you get the hang of it. Basically, a quick recap. Your day-to-day life, you use the decimal number system, base 10, digits through 0 to 9. Well, computers and there's other number systems in existence. The most common ones you'll see that are mainly used in computers, binary, base 2. Basically, if there's a base, whatever number it is, it's just all the digits before that base. So if I had base 100, it'd be base 0 to 99, for example. But binary, base 2 is very common. It goes between 0 and 1. I think you've heard that term before, zeros and ones. That's how computers work. Another one you'll see is octal, base 8, 0 to 7. And then hexadecimal is base 16. Those are digits So it's 0 to 15, but once you get above 9, you start using letters instead of digits. So 10 is A, and you can see this in this chart here. I should have pointed that out. You know, oops, wrong thing. There we go. 10 is A. Come on, Styles. There we go. 10 is A, 11 is B, 12 is C, and so on all the way up to 15. Does that make sense? So really the whole point of base conversion is you're given a number in a certain number base, and you need to convert it to another number base. It's not too intuitive or not too difficult once you get the hang of it. So, any questions on this? All right. So, if you're converting, um, is that even what this is? I remember. No, this is just saying base x. It's basically what I said already. You for each index in the number. So basically, if you know what base it is, right? So like if you're given a number in base, I'm gonna make up a different number just to start from scratch. So if we have the number 358 in base, I don't know. Let's do base 4, and the this subscript here means this is what base it's in. So it's in base 4. If you know it's in base 4, well, what you can do is if you want to, you don't have to do this labeling part I'm about to do, but it's good practice. You label the indices from right to left, starting at 0. And if you want to figure out what this number is in decimal, well, basically it's just you basically just take this number, the number in orange here, and then multiply it by the base to that power. Does that make sense? So this would be, for example, 3 times 4 squared. Then, if you keep going, 5, the number in orange, times the base to the index. Then 4 to the first, plus 8 times 4 to the 0, which is basically 3 times 16, plus 5 times 4, plus 8, which is 48, plus 28, which I believe is 76. Don't quote me on that. I think that's 76 off the top of my head. That's why you can figure out exactly what a number in any other base is in decimal. And basically, there's 3 types of problems you'll get here. Really, you either have to go from a base that's not base 10 to a number that's in base 10, because base 10 is the usual. You might have to go from base 10 to a number that's not base 10, or you might have to go from a number that's not in base 10 to a number that's not in base 10. And there's some shortcuts for doing that last one. Basically, base 10 is involved or it's not involved. But if you want to convert a number to base 10, you basically do exactly what I just showed you above. You label the indices from right to left, and for each number, you take the number itself and multiply it by the base to that index. Does that make sense? And of course, starting at the rightmost is 0. So you label from right to left, and then you can evaluate it anyway. I just like going then from left to right, kind of, like you go one way, then you go back the other way. Does that make sense? All right, cool. So if you want to then go the opposite way and convert a number from decimal, so base 10 to a different number, so I'll do a quick example. Let's say we want to, I'll squeeze it in down here. Let's say you want to convert the number 53 in base, I don't know, how about base 6 to, you want to figure out what is that in base 10? Well, what you do is you basically keep dividing the number. So 53, it's not 53, but I'm calling it 53. You divide 53 by 6 every time until you get, and while you're doing this, you write down the remainders, and you keep doing this over and over again with each quotient you get until you have a quotient of 0. Does that make sense? So as an example, you'd start off by doing, this is how I like to do, you can write this slightly differently. 53 divided by 6 is, well, that would be 8, and then you have a remainder of, well, let's think about this. 6 times 8 is 48. That's the closest thing. And then 53 minus 48 would be 5. Then you keep going. Now you just basically bring this number over here. 8 divided by, let me move that up a little. 8 divided by 6 is just 1 with the remainder of 2. And then 1 divided by 6 is 0 with a remainder of 1. So now that you have a 0 here in this column, you know you're done. And to get the final answer, you read the remainders from the bottom up like this. So really the final answer is 53 in base 6 is the same thing as 125 in base 10. So that's how you would go between a number that's not in base 10, or yeah, a number that's not in base 10 to it. Actually, I just realized, you know what I did? I completely did that backwards. Well, what I meant to say is I apologize. I wrote this backwards. This should be saying 53 in base 10 is what in base 6. That's the correct. I did the math right. I didn't do the labeling right at the beginning. I apologize for that. I was like, something seems fishy here. That's how you go from a number that is decimal to a number that's not in decimal. So I basically converted 53 to whatever its equivalent is in base 6, which is 125. And then this again up here is how you go from. And then if you want to go back to base 10, you basically do what you did up here. Does that make sense? Sorry about that error there. All right, cool. So hopefully this is all review. Then basically, if there's a shortcut methods, this is a great example. If you wanted to go between two numbers that are perfect powers of 2, so 2, 4, 8, 16, 32, 64, etc., there's a shortcut method. Because if you didn't, if you're going, I mean, you still can do this if you have two bases that are powers of 2. But if you don't, or one of them isn't, you basically have to do both of these combined. You have to first convert it to decimal and then convert it to the other base from decimal. But the shortcut method here, this is a great example. You think to yourself, okay, hey, well, the first step is you want to convert the number you have into binary, base 2. But this number is already in binary, so that's skipped. So this is a great example. If you want to go from base 2 to base 8, these are perfect powers of 2. So you got to think to yourself, okay, 2 to the what power is equal to 8? Can somebody tell me? What I'm essentially asking you here is log base 2 of 8. What does that equal to? 3, exactly. 2 cubed is equal to 8. So now this number here is what I like to call the magic number. So what you want to do is using this number, you want to go from right to left and group the original number in that amount of bits. So we start here. So I group the first 3 numbers from right to left in 3 bits. So now I say to myself, okay, then you just basically going through each of these numbers, you say to yourself, what is whatever you just grouped, what is that number as a decimal number? So what is 111 as a decimal number? Can somebody tell me? Like, I'm basically converting 111 in base 2 to decimal. So like, what is that as a decimal? 7. Exactly. Good. Because then if you don't understand that, as a quick side note, 111 in base 2, well, you do the same thing as the first thing. Basically doing this in your head. Label the indices from right to left. Now you have 1 times 2 squared plus 1 times 2 to the first plus 1, which is the same thing as 4 plus 2 plus 1, which is 7. Does that make sense? So this is 7. Now I do the next 3. Whoops, what happened? There we go. How about these 3 guys? What's 0 on 1 as a decimal digit from binary? 3. Good. And then how about this guy? 4. Exactly. 4. Good. And again, if you mess up the conversion, if you need to for at first, write it out like I did over here. Now, as a quick side note, if there was I'm making this up, if there's a 1 here, do I still keep going? Exactly. Yes. What you would do is you would pad however many zeros you would need because that doesn't change the number technically. But anyway, there you go. So then basically all you have to do is you just take these numbers you wrote up here and that's your answer. So 437 in base 8 is the answer. Pretty cool shortcut, right? So that's the shortcut method. But again, you can only do that between where both bases are powers of 2. So, any quick questions on that? All right, so there's 2 problems. One of them's a little longer. Do you want me to give you guys a minute to try it, or should we just go into it? Sure, I'll give you guys a minute to try it. So this one's kind of a 4-in-1. I'll give you guys like 4 minutes, a minute for each. Because I think that's like pretty much what you should be able to. If you can do that on the exam, you should be really good if you can solve these in like at most a minute. There'll be a minute for each. And we'll come back together. All right. Well, let's go through this thing. Let's go one at a time. So let's look at the first one, performing to these base conversions. We want to go from base 347 in decimal to its equivalent in base 5. So which of the three approaches am I going to do here? Am I going to do the multiplication, the division, or the shortcut? The division, exactly. You basically have to keep dividing the original number in decimal by the new base until you get a quotient of 0. So, and remember, you don't get a calculator in the exam, so you got to be able to do long division by hand if you don't know if you don't know it off the top of your head. So 347 divided by 5. Well, I don't know what that is off the top of my head, so I'm going to go over to the side here and figure that out with long division. All right, dividing by 5. Well, 5 doesn't go into 3 at all, but it goes into 34. Good old 6 times. That's 30. You'd get 4. Bring down the 7. Then you would get 5 goes into 47 9 times. Oh my god, that's funny. It's 69. That's random. Anyway, that would be 45. Track that. You would get 2. So you get 69 with the remainder of 2. So you get 69 with the remainder of 2. And now you basically remember, you bring the quotient you got and bring it over and keep going. So 69 divided by 5. Well, 12 times 5 is 60, I believe. Yeah, 12 times 5 is 60. So this should be 13 then. 13 with the remainder of 4. And we do this again. 13 with the remainder, 13 divided by 5. Well, that's just going to be 2 because 5 and then 10 with the remainder of 3. And then lastly, 2 divided by 5 is 0 with the remainder of 1. Or not 1, excuse me, 2. 0 with the remainder of 2. And since we got a 0 as a quotient, we're done. So, do I read this from the bottom up or the top down? And what am I reading? You read the remainders from the bottom up, exactly. So I'm going to read the remainders like this to get the answer. So from the bottom up, we can see that it's 2, 3, 4, 2. So that's the answer. Does that make sense? Hopefully you're all able to get that answer. Also, wow, whoa, a lot of thumbs up just appeared on my screen. That was funny. All right, part B. This one. We want to go from 361 in base 7 to its equivalent in decimal. So am I going to do the multiplication, the division, or the shortcut? I have one person saying multiplication. Anybody else? Exactly. You're going to do the multiplication since your destination is base 10. So what I like to do, write out the number, then label the indices from right to left. So, and remember, this is in base 7. So, oh, whoops, why did I write a 7 here? This should be a 1. There we go. Sorry about that. So, you go from left to right. You multiply with the original base. You start with the 7. That's a good question, Stephen. You do it with the original base. So, then you go from left to right, and you multiply each number at the index, so 3, by the original base to that index, so 7 squared. Then you repeat for the rest of them from left to right. So you have 6 times 7 to the first plus 1 times 7 to the 0. So you get 3 times 49 plus 6 times 7 plus 1, since 7 to the 0 is just 1. Now, I don't know what 3 times 49 is off the top of my head, so let's do that on the side real quick. And choose 27, carry the 2. It should be 147. So we'll get 147. 6 times 7 is just 42. And plus 1. So basically, what is 147 plus 43? Well, that should be 190. So that's the answer. 361 is in base 7. Its equivalent in decimal is 190. Does that all make sense what I did there? Any confusion or questions? Awesome. Okay, part 3. We want to go from 3AD in base 16 to its equivalent in base 2, binary. So which of the 3 techniques would I apply here? Yes, you can do the shortcut method here because 16 is a power of 2 and 2 is a power of 2. Now, let me just ask you, if this was going, for example, to base 6 instead of 2, could I do the shortcut then? Good, you can't, because 6 is not a power of 2. It's a multiple of 2, but it's not a power of 2. Just want to make sure you got that. So now what I like to do, especially with hexadecimal, remember the first step is, well, this one, the destination is binary anyway. But the first step is you have to convert the leftmost number to binary. Now, the way I like to do this is, especially with numbers with letters, I first write out the letter. So I'm like, okay, what is A? Well, that's just 10. What is D? That is 13, I believe. Yeah, that's 13. So then I like to substitute that in for each number, just because I think it's a lot easier to read a number than a letter. I don't know about you guys, but that's how I feel. Now we have to figure out the quote unquote magic numbers, I like to call it. So we have to think to ourselves, okay, log base 2 of 16, what's that equal to? Basically, 2 to the what equals 16. The same thing as this. 4, exactly. So we need to group each of these numbers in 4 bits in binary. So we got to do this from right to left. Always go right to left here. So 13, what would that be in binary? 1101. Perfect. It's not 11. I just say that. And remember, if you're not sure, write down what you think it is, and then you can do the multiplication technique to check. I like that you can self-check here. But yes, it's 1101, because this is basically saying 8. This is 2 to the first, 2 to the, or excuse me, 2 to the 0, 2 to the first, 2 squared, 2 cubed. That's basically saying 0, or no, 1 plus 4 plus 8, which is indeed 13. Does that make sense? Now let's keep going. What's 10 represented in 4 bits? One zero one zero, exactly. Good. Then what's 3 in 4 bits? 0011, exactly. So now, and then remember, if you have trailing zeros, don't cut them off because otherwise they'll be marked points. So the final answer would be, since we wanted to get to binary originally, 0011, 1010, 1101. And there you go. Does that make sense? Not too bad. Any questions on that? All right. Oh, you guys made my computer explode with thumbs again. Now this one, last one. Which of the 3 techniques should I apply here? Actually, before I do this one, remember on this one, part 3, you could convert this to base 10 first and then convert it to base 2, but shortcut's a lot faster. Anyway, which of the 3 techniques should I apply to this one if we're going from base 8 to base 4? Shortcut, exactly. Let's do the shortcut method because these are both powers of 2. But this one, we can see our destination is not a power of 2. It's not binary. So what you have to do in a situation like this, where there are 2 powers of 2, where one of them isn't binary, you convert this one to binary using the shortcut, and then use the shortcut to convert it to this guy. So we first have to ask ourselves, okay, log base 2 of 8 is what? What's the magic number for the first conversion? 3, exactly. 2 cubed is 8. So now that means we have to group each of these numbers in 3 bits from right to left. So let's go one at a time. What is 1 represented in binary as 3 bits? 001. Good. How about 2? 010. Good. How about 3? 011. Good. How about 7? 111. Good. How about 4? 100. And then we already have 2 again, which is 010. So now I would put all these together because it's a lot easier this way for the next part. So now we basically have the binary representation of the original number. But that's not what we want. Our end goal is we want it in base 4. So I'll switch to another color here. Now we have to basically do the opposite with the shortcut. So now we have to find a magic number again. Log base 2 of 4, what does that equal to? 2 to the what power is 4? 2, exactly. So now we have to go from right to left, always go from right to left here, and group all these numbers in 2 bits, and then basically figure out the decimal representation, and we'll have the answer. So the first number, what would that be? What is 0, 1 as a decimal? 1. Good. How about 0, 0? 0. Good. We already have 0, 1. How about 1, 1? Yeah, 3. Good. Now we keep going. This is 2. This is 3. This is 0. This is 1. And this is 1. Now you just write these from left to right, back up top. 1, 1, 0, 3, 2, 3, 1, 0, 1. And that's the answer. Does that make sense? I used the shortcut technique twice. Any questions on that or anything? Hopefully you're all able to get those answers. If you didn't, just keep practicing it. That's all. This is just kind of got to get used to the process. All right, I figured that was pretty straightforward. Here's one more. You want to try it or should we just do it? Okay, sure. I'll give you like 90 seconds. Whoops, I did not mean to do 4 minutes. Okay, that should be enough. Yeah, I can go back. What's up? What'd you need? Did you get what you needed, Guillermo? Okay, cool. No problem. Okay, give you guys like 90 seconds here. All right, hopefully you got an answer. If you didn't, that's okay. Let's go through this. So we're going from base 10 to base 16. So which technique would I want to use here? Want to use the division technique. Good. Because that's just what you do when it's in this scenario. So this is going to be fun. 32,456 divided by 16. I do not know what the heck that is off the top of my head, so I'm going to go to the side here and do some long division. Because remember, no calculators. Okay, we're dividing by 16. Well, it doesn't go into 3. 16 goes into 32, though, twice. That's nice. So that minus 32. 16 times 2 is 32 is 0. Bring down the 4. 16 doesn't go into 4 at all, but it does go into 45 though, so bring that down. 16 goes into 45. Let's think about this 2 times again. This will be 0, 2. 16 times 2 is 32. That's the closest you can get. So that minus 32 would be, let's see, one to be 13. And you bring down the 6. Okay, I don't know what 16 goes into 32. Okay, someone said 8. Let's just double check that just to make sure. If you're not sure, just try try plugging in some numbers. 16 times 8, you get 8, bring it to 4. Yeah, that's as close as you're going to get, 128. So it goes in there 4 times, or excuse me, 8 times, sorry, 8 times. It's annoying, you kind of got to just kind of guess with these sometimes, but that's just how it is. So it's minus 128, which is just 0. This will just result in 8. So basically, the answer would be 2028 here with a remainder of 8. Did that all make sense what I did there? Just long division. That was just a sub problem of this problem. Cool. Okay. Now just keep going. Bring the quotient you just got over here and do it again. 2028 divided by 16. Again, I have no idea what that is, so let's figure it out. 16 goes into 20 once. That minus that would be just good old 4. Bring down the 2. 16 goes into 42 twice. That's 32. So that minus that would be 10. Then bring down the 8. 16 goes into 108. Well, I don't know. We knew 16 times 8 was 128, so I'm going to guess it's 6. Let's give it a try. 16 times 6 is 36. Yeah, that's as close as you're going to get. So it would be 6, 96. So then you'd have a remainder of 12. So that is equal to 126 with a remainder of 12. Did that all make sense there, what I just did? Now be careful. We can't write 12 here because we're going to base 16. So what should I write instead? What letter? I'm just going to put it in parentheses. C, exactly, because C represents 12. I like to write the number and then put the letter afterwards. But we're not done. Let's keep going. 126 divided by 16. Well, I don't know what that is either. But based on what we've done, I can already tell it's going to be 7. So it's 7. But I don't know what the remainder would be because I don't know what 7 times 16 is. So let's figure that out real quick. It'd be 2. Bring up the 4. 7 times 1 is 7. It'd be 112. So then 126 minus 112 would be 14. But then what letter am I going to write instead of 14? E. Okay, now it's pretty much easy rolling. Keep going. 7 divided by 16. Well, that's 0 with the remainder of 7. Now that we did this, again, read from the bottom up. So the final answer, 32,456 in base 10 is the same thing as 7EC8 in base 16. Does that all make sense? A bit of a tedious one, but once you get the hang of it, you should be pretty good. Questions, comments, or anything? Again, these just take some practice, but just make sure you were able to do these side computations on the side. I hope you understand why I did the side computations. It's kind of hard to solve this without them. Questions or anything? All right, so let's keep going then. Moving on is probably my least favorite topic in the whole course, Bitwise Operators. I know a lot of you don't like Bitwise. The stat emoji. I'll be honest, I'm a little shaky on the Bitwise coding questions, so my explanations on those might not be perfect. I'll do my best. But let's just get right into the preliminary information. Why use Bitwise Operators? Well, there's a lot of problems that can be... Why the angry face, Eric? There are a lot of problems that can be represented in binary and clever ways, of course. And bitwise operators allow you to exploit those bit patterns to make simple and efficient memory-efficient algorithms. So there's 3 things you need to know: bitwise and, or XOR. It's and and or sounds like, a Boolean and or, but remember those are written by 2 of them. So like this is saying, is like, I'm making this up, is 5 and it's 5. Basically checking, are 2 variables the same or something, or bitwise or Boolean OR would be with 2. But bitwise is just you only write it once, as you can see here. So with and, the only way it's true is using the 2 bits. Because remember, since it's bitwise, it's only zeros and ones, which is kind of handy. And is only true when they're both 1, no matter what. Otherwise, it's 0. The combination doesn't matter. For or, that's always true unless they're both 0, because one or the other has to be true. And then XOR, they're called the exclusive OR. That's basically when, and this is written with the little caret. That's basically written, or that's basically true. Excuse me, when both the numbers are different. So 1 and 0 are different. 0 and 1 are different. So those are true. But 1 and 1 are the same. So that's not true. Does that make sense? How these work? Cool. Okay. Then a few other things. There's the not, left shift, and right shift variables, or variables, operations. The not basically is just you flip the bits around. It's called one's complement. So if I had a 1001 here and I applied the not operation, you just flip the bits to their other value to get 0110. Hopefully that's pretty self-intuitive. Left shifting, you shift all the bits to the left and multiply the original number. This basically essentially multiplies the number by 2 to the k times. So, here we have 2 and we're left shifting it once. So basically, first in the binary representation, you shift the 1 to the left once to get this. So this is the same thing as basically multiplying the original number 2, because remember, these are equivalent, 2 by 2 to the k. So this column here, this is your k here. So then you basically multiply it by 2 to the first, which in this case would be 4. As another example, if I did 5 and I left shifted it 3 times, well, that's basically saying you multiply 5 by 2 cubed, which is the same thing as 5 times 8, which is 40. Does that make sense? All right, cool. Now the opposite to that is right shifting. If left shifting is multiplication, you can probably guess that right shifting is division. Literally the opposite. The binary bits go to the right. This is I'm shifting it to the right one. And otherwise, you divide. It basically is the same thing as dividing by 2 to the k times. So now let's do a different example. If I had 50 and I right shifted it, and by the way, I should point out, you do right shift with 2 greater than signs, left shift with 2 less than signs. Sorry, I forgot to point that out. But if we did 50 right shift by 4, that's basically saying 50 divided by whatever 2 to the 4th is, which is just 50 over 16, which is, and then remember, since this is integer division, you don't do any decimal, you just round to the nearest whole number. So that would be 3, because 16 times 3 is 48, and that's the closest you're going to get to 50. Does that make sense? And then, this is also the same thing as writing out 50 in binary and shifting all the ones 4 times. We're shifting everything to the right, technically. But any questions on this? All right. So all these data types are encoded in binary, and they don't require casting the binary for bitwise operations, which is handy, because basically everything's stored in binary anyway. The most common cases in the FE concern integers, since they're the simplest to represent. So I think we have 1 conceptual, 2 coding. I'm probably going to struggle a teeny bit on the coding. I admit it right now. I am not the best at coding here with Bitwise, but we're going to do our best. The first one, though, the conceptual, is basically just doing some base conversion and then applying what we just did. So, you guys want to give these a try? First? Sure. All right. I'll give you guys 5 minutes I'll give you a minute for each. There's 5 of them. Give this a try, and we'll come back together in about 5 minutes and see how we can do. All right, I know you probably didn't finish all of them. I mean, these are a little tedious and probably take a little more time than 5 minutes, but I just want to keep moving for time's sake. So, the first step to approaching any question like this, well, the last two are easier. It's these three mainly. The only way to really figure out the right answer is you have to convert the two numbers to binary, since that's the whole point of bitwise. You have to convert the two numbers to binary, then do the operation on them, and then convert it back to decimal. So basically, you have to do two base conversions, and actually three base conversions rather, per each problem, and then also do the bitwise part. Does that make sense? All right, so let's do the first one. We want to figure out our goal is what 56 implying bitwise or with that 17 is. Well, first we got to figure out, okay, what is 56 as in decimal? What is that represented in binary? Well, you can do the division technique, or you can probably just figure it out in your head if you really tried. But let's just do the division technique to be thorough. 56 divided by 2. Well, that would be 20. What is that? 28? 28, I think. I think it's 28. 28 with a remainder of 0. Yeah, it's 28. Then we keep going. 28 divided by 2 is would be 14 with a remainder of 0. 14 divided by 2 is 7 with the remainder of 1. 7 divided by 2 is 3 with the remainder of 1. 3 divided by 2 is 1 with the remainder of 1. 1 divided by 2 is 0 with the remainder of 1. Now they got a 0 in the quotient, you're done. Does that make sense? Just base conversion again. Just what we did before. You following? Okay, cool. Now let's do the other one. That was what number? 17. This one should be easier. 17 in base 10. What is that in binary? Well, 17 divided by 2. That would be 8 with the remainder of 1. 8 divided by 2 is 4 with the remainder of 1. Or 0, excuse me. 4 divided by 2 is 2 with the remainder of 0. 2 divided by 2 is 1 with the remainder of 0. 1 divided by 2 is 0 with the remainder of 1. Now that we have them both, the best way to do this is write what the first number on top of the second. I guess it doesn't actually matter, but I just do the first on top of the second. So again, we read these from the bottom up like this. So the first one, 56, we have, that would be 1, 1, 1, 1. So 4 ones, 0, 0. And again, if you're ever unsure if you did it right, you can just, actually, I see an error. This should be a 0. 14 divided by 2 is 7 with the remainder of 0, not 1. But if you're ever unsure if you did it right, just convert your binary result back to decimal and see if you got the same number. Because if you didn't, then you must have messed up. So anyway, 3 1s and 3 zeros. Great. Now the second one, they both actually have, well, this one only has 5 numbers. So the second one I would write from right to left. So we have 1, 0, 0, 0, 1. And then since there's an extra space, you want to pad that with the 0. Does that make sense? Okay, cool. And now the way you write this, we're going to do the OR operation. So I'm just writing the bar. And now remember how OR works. If at least one of them is a 1, representing true, then the result is true, or a 1, otherwise it's false. So what would 1 with 0 be? Someone tell me what number, 1 or 0? 1, good. What about 1 and 1? 1 again. How about 1 or 0? 1, good. 0 or 0? 0. And with the same thing. And then 0 or 1? 1. Good. Okay. So there's your bitwise result. But now we have to convert that back to decimal because they want the answers in decimal. So we have to figure out, okay, what is 111,001 from binary? What is that in base 10? So now we have to do the multiplication technique, right? So 0, 1, I'm labeling the indices from right to left. And now it's just doing the same thing as before. Now, you don't have to, for this one, for any time you're doing base 2, I'm just going to write the 2 to the whatever part because, 1 times that is the same thing. But you could still write 1 times 2 for each one, but it's kind of irrelevant. So basically you have 2 to the 5th plus 2 to the 4th plus 2 cubed plus 2 to the 0. Well, that's the same thing as 32 plus 16 plus 8 plus 1. So that is, let me think, 48 plus 9, which should be 57, and base 10, which is the correct answer. So there's your final answer, and I'm going to write it up here in the blank, 57. So did all that make sense how we did that one part? Any questions or anything? A little tedious, but that's just how it is. All right, so let's do the second one. The second, we are applying the bitwise and to 47 and 83. So we have to do the exact same thing as we did. We first have to convert the two numbers to binary, so division technique. Starting with 47, well, we don't know what that is in binary, so do division. 47 divided by 2, that should be 23 with the remainder of 1. 23 divided by 2. Oh, so one thing I should point out here, if you're getting a remainder that's bigger than or equal to the base you're trying to go to, then you did the math wrong. You should always get a number that's less than the base you're trying to go to as your remainder. It's a nice self-check that you can kind of do in your head as you're doing this. 23 divided by 2, keep going. Oh my god, whatever. 23 divided by 2, that should be 11 with a remainder of 1. 11 divided by 2 is 5 with the remainder of 1. 5 divided by 2 is 2 with the remainder of 1. And 2 divided by 2 is 1 with the remainder of 0. 1 divided by 2 is 0 with the remainder of 1. Okay, we got that. Great. That was 47. That looks right. Just checking my work. Now let's do the other one, 83. What is that in base 2? So, same process, 83 divided by 2. It's going to be 40 something. 40 times 2 is 80. 41 times 2 would be 82. I think it's 41. Yeah, it's 41. 41 with a remainder of 1. 41 divided by 2 is that would be, Jesus Christ, my brain just shut down for a second. That would be 20 with a remainder of 1. 20 divided by 2 is 10 with a remainder of 0. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1 with a remainder of 0. And 0, or 1 divided by 2, excuse me, is 0 with a remainder of 1. And there we go. Now, of course, normally you read these from the bottom up. Let me just double check our work. Yep, that looks correct. Does that make sense what we did so far? Just the two base conversions? Cool. Glad you're following along. Now, let's write the two numbers. Now, here I know this is kind of against what you're supposed to do normally in base conversion, but for bitwise, it's honestly better to write the numbers from right to left. So basically, if I'm going from the right, do the top down approach. That way, you don't mess up any of the math. So I'm going to do the first number, which was 111,101, just like that. Going from right to left from the top down. I mean, you could just go also from the left to right from the bottom up as well. But the thing is, it's handy for when they don't have the same amount of bits, which you're about to see. So now if we do that on this side, from the top down, we'd have 1100101. So now I'm just saying, if you didn't do what I just did and you instead roll from left to right, from the bottom up with the second number, you have to be really careful because you have to be like, okay, would I start it here? Do I start it over here? Do I start it like one of them in? So if you don't do it this way, if you do it the other way, what I just did the first time, it's a lot easier not to mess up. Does that make sense? What I just said there? Did any of that make sense? Okay, just making sure. Um, Stephen, I'm not sure if you'd get points deducted. Oh, it says right on. It actually says right on it. No work necessary. Only the answers are graded. So no, you would not lose points for that. If you could just do this in your head and don't do the division, you can absolutely just do that. No problem. Okay, so now we're applying the AND operation, the bitwise AND rather, to this. So now, first off, what number am I going to put here to fill in this space? 0. Good. So now you go from left to right. Now remember, when is bitwise AND true? When they're both ones, exactly. So the first one would be 0, the second one would be 0, the third one would be 0, the fourth one would be 0, the fifth one would be 0, and these two would be 1. Does that make sense? So basically, now you have to ask yourself, what is 1, 1 in binary? What is that in decimal to get your final answer? Well, this one I think you could probably just do in your head. But for those who can't, I'll just write it out really quick. Label the indices. That's just basically saying 2 to the first plus 2 to the 0, which is just 2 plus 1, which is 3. So that's your final answer, 3. Did that make sense? Any questions on this question? All right, let's keep going. Let's do the third one. The third one, we're going to do 79 and apply the XOR to 36. So, same process. First, let's figure out what 79 in binary is. 79 divided by 2. I actually don't know what that is off the top of my head. Let's think about that. Oh, actually, I just realized what it is. It'd be 39. 39 with a remainder of 1. 39 divided by 2. That would be 18. No, not 18. That would be 19 with a remainder of 1. 19 divided by 2 is that'd be 9 with a remainder of 1. 9 divided by 2, that would be 4 with the remainder of 1. 4 divided by 2 is 2 with the remainder of 0. 2 divided by 2 is 1 with the remainder of 0. And 1 divided by 2 is 0 with the remainder of 1. Double check that was correct. 1, 0, 0. Yep, that was correct. Great. Now we can do the other one. Let's use pink. 36 in base 10. What is that in base 2? This one should be pretty easy since I think pretty much everything is even. 36 divided by 2 is 18 with the remainder of 0. 18 divided by 2 is 9 with the remainder of 0. 9 divided by 2 is 4 with the remainder of 1. 4 divided by 2 is 2 with the remainder of 0. 2 divided by 2 is 1 with the remainder of 0. And 1 divided by 2 is 0 with the remainder of 1. Great. Now we have the 2. Double check the work. Yep, that's correct. So we just did the base conversions. Makes sense? Now you can see here, there's going to be one number has more bits than the other. So I'm going to read them from right to left in the bottom down approach again. Excuse me, I always do that. The top down approach again. Excuse me, top down. So I'm writing them from right to left. So I do the top one first, second one, the third, the fourth, and then the 0, 0, 1. Now the other one, you have 0, 0, 1, 0, 0, 1. Now this just makes sure you don't have a mismatch with the padding. And then we would fill this guy in here with a 0. And we're applying XOR. So when is XOR true? Can someone tell me? Correct. When it's both 1 and 0 together. Or they both basically, it's you have to have two different unique numbers. They shouldn't be the same. So the first one would be a 1, the second one would be a 1, the third one would be a 0, the fourth one would be a 1, the second or the fifth one would be a 0, and then the last two would be a 1. All the ones are because you have two different numbers, and the zeros are because they have two of the same. Okay, great. We have a number. So our last step is, well, what is 1, 1, 0, 1, 0, 1, 1? What is that number in from binary? What is that in decimal to get our final answer? Well, label the indices from right to left, and then just do the math. 2 to the 6th plus 2 to the 5th plus 2 cubed plus 2 to the 1st plus 2 to the 0. That's the same thing as saying 64 plus 32 plus 8 plus 2 plus 1. Well, let's think about this. 64 plus 32, that is 96. And then 8 plus 2 plus 1, that's 11. So basically 96 plus 11, which is 107, which is indeed the correct answer. So that was that question. Did that all make sense? Awesome. Now for the last two, these are a lot easier. 13, and we're left shifting it 3 times. Well, what does that mean? Did someone tell me? Exactly. We're multiplying the original number, the number on the left, by 2 to the k, and this is your k. The k is always the number on the right. So this is basically saying, what is 13 times 2 cubed? Or what is 13 times 8? And we can quickly figure that out on the side. 8 times 3 is 24. Bring up the 2. 8 times 1 is 8, and you should get 104. Look at that. Done already. Does that make sense what I just did? Just applying the left shift. Remember, the left shift means you take the number on the left and multiply it by 2 to the number on the right. Any questions or confusion on that? Is this making sense, I hope? All right, cool. Now the last one, right shift, very similar, except now you're just dividing instead of adding. So now we're basically being asked, okay, hey, what is 187 divided by 2 to the 4th? Which is the same thing as 187 divided by 16. Well, I don't know what that is. Let's figure it out. 187 divided by 16. We're going to do long division. 16 goes into 18 once. You'll get 2. Bring down the 7. 16 also goes into 27 once. I did not give myself enough room. Hold on a second. Sure. Squeeze it in there. There we go. There we go. So then you get 16, and that minus that would be 11. So you basically get 11 with the remainder of 11. But now what would I put the answer as? Do I need the remainder, do you think? Remember, this is basically integer division, not float division. You always assume with this it's integer division. You don't need it. Exactly. The remainder is completely irrelevant. So the final answer would just be 11, whatever the quotient is. So that's how you do that. And now that took longer than I thought it would. There's your 5 answers to this one question. Any other questions about how we did all of this? All right, so we're good to move on. All right. right, coding question. This is where I'm going to be shaky. Should we just do this right away? I have a feeling most of you are just want to do this right away. Okay, this is going to be fun. Not. Complete the function below using the appropriate bitwise operators when necessary so that it returns 1 if the array numbers, first parameter of the function, contains a subset of values that adds up exactly to target, the third parameter of the function. Note that the second parameter n represents the length of the array numbers. If no subset exists, the function should return 0. Okay, so we need to be really careful here, try to figure out what the hell were we being asked to do. Well, basically, we're being passed in an array of numbers. Let's do a simple example. We are given, let's say we have 3 numbers. Let's do 3, 8, and 15. And let's see if there's a subset of those numbers that adds up to, and by the way, a subset I believe means like any combination. So like with 3 and 15 add to, and let's say our target is, let me call it T. Let's say our target is 18. So really, you would just have to go through and see, like, hey, is this combination equal to 18? Is this combination? Is that combination? And is this or is you get the idea. So really, from what I understand, it's just you're being asked, can you use this using bitwise? Now, we have to be really careful here. How do you think we can do this? Actually, I just completely read the question wrong. Oh, no, I didn't. Well, sort of. You need to go through and see if there's a subset of like, you start at each number and say like, hey, is there anything afterwards that adds up to it? Basically. Does that make sense? It's basically you're trying to figure this out by using bitwise. Now, can someone tell me before we get into it, what does this mean here? Like, why are they doing this? Why are we doing 1 left shift n times? Exactly. This is saying I is less than 2 to the n, which in this example, there's 3 things. So this is basically saying I is less than 8, since n was 3. And because of that, if you think about it, there are pretty much 8 different combinations that you could initially start with. So that's why they're doing that. Now, we have to be careful here. How do you think we can do this? Well, if we're trying to determine a sum, what do you think we need? What do you think we need if we are going to track a sum? Think of that last word I just said. You need a tracker variable, exactly. And so we have to do this for every iteration of the loop. So int, I'm going to call it sum, and initialize that to 0 since we're adding. Okay, now here's the fun part. Not. So now we have the sum, and on each iteration, basically at each number, we have to basically go through all of the numbers again and basically say, okay, hey. So like as an example, our goal is like, okay, hey, we're currently on 3. Is 3 plus 8 plus 15, is that equal to our target of 18? No. So then you do it again. You're basically just doing this 2 to the n times, if that makes sense. That's why they're doing 2 to the n for some reason. I'm not honestly fully sure why it's 2 to the n. But then you basically have to do that another time. So then now at 8, our goal is to pick, okay, hey, I is here. Would this be, is this plus this equal to this? No. You get the idea, kind of, I guess. I'm sorry, I'm not really good at explaining these. We're basically trying to figure out, if there's a subset of values that adds up exactly to the target. So really, basically, essentially what we're doing is we're just checking all the combinations. That's really all that's happening here. That's why I think this is I is less than 8 and not 3. So you have to check all the possible combinations of numbers. So if we have to basically do something more than once again, what do we need? A loop, exactly. So we can do another for loop, and j equals 0. Now I think here I'm going to want to loop through, what's j going to be less than? If for each time I just want to go through and check, add up all the numbers, basically. Possibly. If I want to just go through the array again with each of the possible numbers, j would be less than n, exactly. Because you're just going through it once. There's no shifting or anything needed here. Because for each iteration, you basically want to just go through the loop 8 times. Well, like 8 on each of the outer loop 8 times, you want to go through the entire inside of the array once. Does that make sense? That's probably a better way of putting it. Okay, so now this is the tricky part. How do you think we can check if we want to add the number to our sum? This is the really tricky part here. Does anybody have any ideas? This is where we want to use the bitwise. Anybody? Okay, no idea. That's fine. Okay, why are you saying and? I like the way you're thinking. It's not that and is addition per se. Really, so what you can do is we can do an if statement here. And while we're going through, we can basically see if the current index of I, so like, 1, 2, 3, whatever, if that, and we bitwise and it, so basically if it's the same, if that is the same thing as 1 being left shifted by j. So this is, it's basically saying if I and 2 to the j are the same. Now, why would we do this? Well, let's just do a quick example. On the first iteration here, if I is 0 and 2 to the 0 and 1's left shifted j, like the first iteration of both loops, 0 and 0 are the same. So that makes me think, okay, hey, we should probably add this to the sum. Then this would keep going. Is 0 and 2 the same? No. Is 0 and 8 the same? No. Is 0 and 4 the same? No. Like those second numbers are getting from this. Is 0 and 16 the same? No. 32 and whatever. But this one's only 3. So then on the second iteration, I would be 1. So none of those would add up at all. Then what about the second one? Basically, what this is doing is it's essentially, this is a way to only add up when the two I and j, 2 to the j match. And when that's true, yes, this is a bit mask. When I and 2 to the j match each other, that means there's a possibility of a combination you want to, that basically means you want to add it to your sum. That's a way to go through it. Does that make sense? Kind of, I guess. I mean, I really don't know how else to explain this. I told you I struggle with bitwise coding. Happens to all of us. Did that kind of make sense? I guess. So we can go through this example at the ends, but basically what we want to do is just add up the array at the j variable, and at the end we just check, hey, once we're out of the for loop, the inner for, actually once we're out of both for loops, no, once we're out of the inner for loop, we just want to see, hey, is our current subset sum equal to the target? If it is, return 1, because that means we found it already. We don't need to keep going. I hope this part makes sense here. This should make a lot of sense. Okay, so now let's just go through how this works. Let's use this example. This might be a little tedious, but I think it'd be really easy. I think it's better to see how this works. So let me copy the array. Our target is 18. And we're initially starting, okay, here's I and here's J. And here, let me do this. 0, 1, 2. Actually, hold on. 0, 1, 2. This is I and this is J. So now we're starting here. And we have our sum variable. Our sum is 0. So now, okay, it's like, okay, hey, is 0, so is I the same thing as 2 to the J? Basically, is 0 equal to 2 to the J? Well, what is 2 to the J in this case? 1. So is 0 equal to 1? No. So don't add it to the sum. Then you increment J. Is J is now is 0 equal to 2 to the first? No, there's no way. Is 0 equal to 2 squared? No, there's no way. So don't add anything to your sum. Did that make sense what I just did? Why we didn't add anything? Okay, cool. So now we keep going. Let me just erase that. So now I gets incremented and J gets reset. So now is 1 equal to 2 to the 0? Yes, indeed it is. So we want to then add whatever is at the bit mask index. So we want to add 3 to our sum. Now we keep going. Is 1 equal to 2 to the first? No. Is 2, no, I'm sorry, is 1 equal to 2 squared? No. So don't do that. And now we would check, hey, did this current combination, is our sum equal to our target of 18? No. So reset this and just keep going. So now, oops. Now this gets incremented again. And we start over. So now is 2 to the 0 equal to 2? No, don't add anything. Is 2 to the first equal to what's it called? Jesus Christ, my brain just shut down. Is 2 to the first equal, is 2 equal to 2? Yes. Add 8. Then is 2 to the is 2 squared 4 equal to 2? No. So that's that iteration done. Now basically we check our sum again. Is that equal to 18? No. Reset it. So now I is going to keep going because I is not dependent on any of, there's no operation we're doing that's dependent on I in the array. So this can technically go, I guess if you want to call it, out of bounds. So now basically I'm going to go a little faster here. Is there any combination of 2 to the power that equals 3? No, because 2 to the 0 isn't 3, 2 to the first isn't 3, and 2 squared isn't 3. So that iteration doesn't have anything. 2 to the fourth, or excuse me, I equals 4. Is there any value of J that would make that true? Yes. When J is 2. 2 squared is equal to 4, so we'd add that to our sum of 15. But that's the end of that iteration. So is 15 equal to 18 our target? No. So this gets reset and we do it all again. So now I is 5. Well, there's no combination of 2 that would get to there based on what we have, nor 6, nor 7, nor 8. So no matter what, basically, this doesn't work ever after this. And so basically, we can already tell there's no subset of numbers that would add up to our target of 18. So the function itself would return 0. So really, I guess now looking back, the way you'd want to approach this question is like, how can I go through all possible combinations, but also make sure I don't miss any extraneous ones while also only adding up all the possible combinations. Does that make sense? Does that make sense how this works, basically? I know this is a little confusing. Really, honestly, I will say if you struggle with this kind of question, if you could get the sum initialized, the for loop, adding this up, and this if statement here, that would get you 7 out of 10 points on this question, which is pretty good. I feel like most of you could probably do those four things. This, and this. If you could do that, that's 7 out of 10, which is plenty for this kind of question. Does that make sense? So I know that probably wasn't the best explanation again, but that was the best I could do. Honestly, if you want a good explanation on this, probably go to a professor. I don't really know a student who understands bitwise coding questions that well, I'm being honest. So any other questions on this, or should we give it the other one another lackluster attempt? The other one I think is going to be even harder. All right, let's keep going. This one's not fun. Do you guys even want to do this one, or should I just skip it, honestly? Yeah, that's a good way of putting it, Russell. The outer loop creates all combinations, and the inner loop checks each index to see if it's part of the current combination. That's a much better way of putting it. Do you guys want to do this one, or should we skip it? Or because would you rather me spend more time on the other topics, or do you want to go through this? I don't care. Take a poll here. Okay, we have a skip. Can you put a poll in the chat? Oh, shoot. Oh my god, where'd you all go? I just minimized Zoom. What is happening? Okay, there we go. Yeah, let's do that. If there's time at the end, we can skip. So I'll write that this was skipped. I'm sorry again. I apologize. I'm just not really good at these. So there's probably better YouTube explanations for Bitwise. I apologize. You know, when I took the class, Bitwise was in a recorded lecture in the last week. It was very rushed, so I didn't get really full chance to understand it. I think that was the case for a lot of you as well. So, all right, let's move on then. Binary search. This is just going to be a review. No questions. Remember how binary search works? It works only on sorted arrays. Basically, you start at the middle of the array. You check, hey, you're trying to find a value while searching. That's the whole point of a search. You check, hey, is the value I'm at bigger or smaller than where I am? Based on that, you update where the left and the right of the quote-unquote array is. And then you recursively call the binary search algorithm again, find the middle. You're basically kind of, eliminating half each time. Which it's a really cool algorithm. You should know how this works. It kind of like, bounces back and forth until it finds a spot if it's there. If it's not there, it'll eventually return 0. And this gives you a big O of logarithmic end time. So pretty quick. Log end time is very good. So basically, you start with the left and right at the and representing the beginning and the end of the array. If the middle value is greater than the current value, or the value you're looking for, discard the right half of the array and decrement the right, and then recursively call. Otherwise, if the middle value is less than the target, do the opposite and discard the left half of the array and increment the left. Don't decrement it. Then recursively call it again. It's a very cool algorithm. Hopefully it's not new to you. Any quick questions on how it works? There's not really a binary search question on the FE per se, but it's good to know the general idea. All right, cool. Let's move on then. Heaps. We got 3 things to go. Heaps and tries, and hopefully we'll go much faster than we just did with Bitwise. So there's 2 types of heaps. A heap is another type of data structure. It's represented in an array where basically it's like a binary search tree, except I'm pretty sure you usually use a binary heap in this class for the FE. So Each node can, again, only have up to 2 children. But basically, instead of like the binary search tree property, a binary tree or binary heap, there's 2 types. At a mini binary heap, it's a binary tree where both the children are greater than their parent rather, and the root is the minimum. So you could see in this example, this node is smaller than its 2 children. Same with this node, it's smaller than its 2 children, and etc. Now, a max heap, you can imagine, is the opposite. This node is bigger than its 2 children, and then the other node's bigger than its 2 children. Now, usually, a heap is represented in an array. Now, this heap is wrong. This array is wrong because for FE purposes, always assume that the index starts at 1, because otherwise that makes the percolating stuff a little harder. So really, this should be indices 1 through 6. And then index 0 over here is just not used at all. Does that make sense? That works. That applies to any kind of binary heap in this class. Did you understand what the difference between a max and a min heap is? Hopefully this isn't new. Really, there's 3 types of operations. Inserting, what you do there, quick refresher, you basically place the new value in the first open child from left to right. So basically it should be how do I say this? It should be the first open spot that's furthest to the bottom and furthest to the right, because the heaps, this wasn't mentioned here, also have to satisfy the shape property, where it's I always get this mixed up. I think it's a complete tree, technically. Someone correct me on that if it's wrong. I'm pretty sure a heap to be valid has to be correct, or a complete binary tree, excuse me. It's the same, yeah, a complete binary tree has to validate the sheet. Jesus Christ, I cannot talk. For a heap to be valid, it has to not only satisfy the heap property with the numbers, but it must also be a complete binary tree. So that's why insertion, you go furthest to the bottom and furthest to the right. So you insert the value there where it should go, in that spot furthest to the bottom and furthest to the right. And then you just percolate it up until you get to the heap property satisfaction. And that runs in logarithmic time. Now the delete, basically, you always delete the root. You replace it with the last value. So again, furthest to the bottom, furthest to the right. You delete that value and basically bring it up to the root, and then you percolate it down to where it needs to go based on the heap property. And that is also logarithmic time. Does that make sense? Cool. And then making a heap. Well, does anyone remember what this is usually called? Heapify, exactly. Heapify, you're just given a random binary tree. It can be anything. And it makes a heap out of all the values. Basically, what you do is you start at the first non-leaf node and percolate it down if necessary until basically trying to validate the heap property. And then you just keep doing that from backwards all the way up to the root, starting from the first non-leaf node. This takes linear time, O of n. Now, doing this, can someone tell me what index, if you have n elements in a heap, or in an array rather, because a heap's an array, what index would you want to start doing heapify on? Basically, what index is the first non-leaf node at? Not 1. Remember, you want to start at the first non-leaf node. I guess I should say starting from the bottom. The first non-leaf node from the bottom. Yes, it is whatever the size is over 2. It's half of the size. Because think about it, in this heap here, there's 6 things. Well, I know these numbers are wrong. If this is 1, 2, 3, 4, 5, 6, you always want to start on the first non-leaf node that's furthest to the bottom and furthest to the right. So this guy. And since there's 6 things, it's n over 2, 6 divided by 2, which is index 3. Does that make sense? The only one where you just touch the root immediately of all the operations is delete. Otherwise, don't think of the root at all. That's a good rule of thumb. So the cool thing, this should say heap, that's a typo. An array. What what kind of thing can a heap be used to represent? Does anyone remember? Like what kind of data structure? Priority queue. Exactly. That's what I was going for. A heap represents a priority queue. A good analogy to that is the emergency room at a hospital. If you're there for a broken leg and someone comes in with a stroke, well, the stroke patient has more priority because it's higher likely they could die first. So you basically can represent people in a priority queue. That's what a priority queue is. So I just want to make sure you guys knew that. But anyway, in a one-based index system, which you're usually using, you can go to the right, left, and parent, the right child, left child, and the parent using the respective indice jumps. The parent is always at whatever index you're at over two, just cut it in half. The left child is two times the current index you're at if they exist. The right child is at two times the index plus one if it exists. Does that all make sense? Just keep that in the back of your head. Cool. Now, time complexities. The average insertion, um, there's a bunch of them, but there's a few more important ones. Deleting and inserting is always logarithmic time. The average time for insertion, average, is constant, but the worst time could be logarithmic as well. And we already said heapifies logarithmic time, or excuse me, is constant time. It uses the average case of insertion. No, that was not right what I just said. Sorry. Heapify is linear time. That's the word I was looking for. But on average, it uses constant time. On average, it could be constant. So look at that. There was that cheat sheet from the other day, basically showing all the runtimes and stuff. Oh, that was for sorting. Never mind. So really, just look at this and kind of memorize it, I guess. Now, does someone else remember what's the runtime for heap sort? Best, average, and worst. It's always the same. And log n. Good. Just wanted to make sure you understood that. Okay. Does all that make sense? Then heap sort, I explained it the other day, but again, basically what you do, you have a heap, then you just run delete on the heap n times and put the return values into an array. And since heapify, you have to make the heap first, of course. But since heapify is constant time, this honestly isn't the right explanation, in my opinion, since usually you have the heap already. Since you have the heap already, you have to loop through n times. And then since percolating is logarithmic time, the overall running time would be n log n. Does that make sense? I don't think this isn't really the right explanation here. These slides need to be updated a little. You understand why it's n log n? Not because of what it's on the slide, because of what I said. Again, just to repeat, you have to loop through the heap. If there's n things in the heap, well, you have to do deletion n times. And then through each deletion, you have to do percolating, and the percolating is logarithmic time. And since those are both nested with each other, you multiply the runtimes together to get n log n. Does that make sense? All right, cool. So there's a few questions here. These will be some good ones. One of these, I think, a lot of you from Dr. Ahmed's class especially will recognize. But let's do the first one. Consider a mint heap represented below in its array of representation. It's not the root stored in index 1 as usual. They will tell you when it's not. So basically, first is doing an insertion. Do you guys want to give this a try or should I just do it? Sure. Try these three. I'll give you 3 minutes, since a minute for each, and we'll come back together then. All right, let's come back together here. So we want to insert 32 into this heap and show its array representation. I definitely think it's more helpful to write out the tree first. So let's do that. So we have 6, 33, 9, 41, 36, 12. Oh, there's more? Oh, God. Okay, I'm going to write it over here to the left. 9, where are we? 36, 12, 100, and then we have 50 to the left of 41. You can see it satisfied the shape and the heap property. Great. Now we want to insert 32. So how does insertion work? Well, you insert it to the first spot that's furthest to the bottom and furthest to the right. So basically, what child is that going to be? Like the left or right child of what number? 41 to be the right child, exactly. So we'd insert 32 here. But now we have to think about, okay, hey, do we need to percolate up at all? So basically, by inserting 32 here, did that violate the heap property for 41, considering this appears to be a min heap because every node is smaller than its two children. So did this violate the heap property at all? Yes. So we need to percolate 32 up, swap 41 to 32. Are we still good now? Well, 32 is good with its two children. It's smaller than its two children. But what about 33? Is 33 less than 32 and 36? No. So we need to swap again and percolate it up. So now is 32 good? Yes. And is 6 good? Yes. So now there's our answer. So we'd have 6, 32, 9, 33, 36, 12, 100, 50, and 41. And if you're not sure of the indices ever, you just start at the root. That's 1, and you just go from left to right on each level. 2, 3, 4, 5, 6, 7, 8, 9. So there you go. Which that is the correct answer. Did that all make sense? Hopefully not that bad. Now we continue. Insert this value 3 into this heap after part A is done. So now I'll copy the heap. I'll leave this alone. Now we're basically inserting 3 into the heap. And then showing the array representation. So where am I going to insert 3? Left of 36. Good. Because that's the first spot that's furthest to the bottom and furthest to the right. So squeeze it in right here. Okay. Now this is a min heap again, as we figured out, because every node, it's smaller than its two children. So, okay. Does 3 need to percolate up with 36? Absolutely. Because that violates the heap property otherwise. Okay. Does 3 need to swap with 32? Absolutely. Does 3 need to swap with 6? Yes, absolutely. And now it's at the root, and since we're at the root, you basically, you're done, and you can verify. Yes, the heap property is still satisfied. Every node is smaller than its two children, since it's a min heap. So the answer would be 3, 6, 9, 33, 32, 12, 100, 50, 41, 36. It's definitely, see why it's much easier to write out the tree. I would not just try to do this with the array. Any other questions here? Does that make sense? How we got there? Cool. Now let's do the last one. Here, I'm going to scooch all this up. Let me label these. This is for A, B. Okay, for part C, Here's the heap. Now we want to delete the minimum value in the heap and represent it again after. So remember, how does delete work? You always delete the root, then bring up the value that's furthest to the bottom and all the way to the right, and then percolate it down. So first you delete the root, you kill 3. It's gone. Now, which value am I going to bring up to the root? Which one's furthest to the bottom and furthest on the right? The picture's not the best for this, I won't lie. But what number? 36. Good. Because remember, these 3 are technically on the same lowest level, and 36 is over to the right, the furthest. So you delete the number down there and you bring it up to the roots. Now we have 36 up here. Okay, and now you just percolate it down. So since this is a min heap, would 36 want to switch with 6 or 9? 6. Good. Because it's the smaller of the two. Now, would 36 need to swap with 32 or 33? And if so, which one? Swap with 32, exactly. 32, 36. And now it can't go anymore. It actually ended up nearly back where it was. And there you go. So now you just convert that back to the array. 6, 32, 9, 33, 36, 12, 100, 15, 41. So there you go. That's how you get through that question. Did all that make sense? Any questions or anything? All right, cool. Let's move on then. This one's kind of a triple in one. You guys want to try it on your own for a minute? I'll give you guys 3 minutes again. All right, sorry about that. I was multitasking. Let's go through this question. This is a good one. Some of you probably recognize this from Dr. Ahmed's class, a very similar type of question. So let's just go one part at a time. Part A, a heap is represented by the following array, where the root is stored at index 1, as imagined. Answer the following questions, and please answer the data and not the index where it's stored. Who is the left child of 13? Well, remember, what index is the left child at for any value? Can someone tell me? 2 times the index, exactly. So 2 times 3 is 6. So the value at 6 is 19. So that's the answer for the first one. Does that make sense? Now, what's the formula for the right child? 2i plus 1. So the right child of 16 at index 4, well, 2i is 8. 2 times 4 is 8. Plus 1 is 9. So the value at index 9 is 20. And again, we were being told to answer the data, not the index. Finally, what's the formula for the parent? And remember what the parent formula is? I over 2, exactly, the index over 2. So 24 is at index 7. 7 divided by 2, you're using integer division, so rounding down all the time, is 3. So 7 divided by 2 is 3.5. You just kill the decimal. So the parent of 7 would be 13. Did that all make sense? Any questions about how we did that? Awesome. All right. Consider the following tree. Is this a min heap? Justify your answer. You cannot just say yes or no. You have to say why. Okay. What do you guys think? Is this a valid min heap? Correct. It is not a valid min heap because the tree is not complete. So no, not a complete tree. If it were to be valid, basically 41 would have to have 2 numbers under it. So I'm just making up 2 random numbers. If it was like this, then it would be valid, absolutely. But the way as is, it is not valid at all because it verifies the shape property. It's not a complete tree. Make sense? I think that one's pretty self-explanatory. You just got to know the shape property. Lastly, this is the bulk of this question. Consider a min heap here, stored in an integer array with up to 100 elements, which is globally declared. Complete the following percolate up functions. Basically, can you write percolate up? That performs the full operation for percolating up at any value in the heap. So, while writing the code, you can also always assume that there's a swap function available that's described below. So this is kind of a little just memorization. So what do you think the first if statement's going to be? What do you need to check right away? Exactly. You need to check if the index is greater than 1. Because if you're at the root, you don't need to keep percolating. You're done. Does that make sense? So first you would check is the index, which is called IDX, is that greater than 1? Does that make sense? Cool. Now, how do you think we're going to check if we need to swap? Basically, what do we need to check for a min heap? What do we need to check what do we check if we know we need to swap? Correct. Is the current, no, be careful. It's actually not correct. Sorry. Correct. Well, wait, what do you mean the root, Noah? Sorry, I don't know why I keep saying correct right away. Can you clarify what you mean, Noah? I assume you're typing. Correct. That's right. That you have to check, hey, is the parent bigger than the current index you're at? Because think about it, if this was I'm just making this up, if this 51 was a 20, you have to check, hey, is the parent bigger than me? If it is, then you have to swap. You're good. Does that make sense, everybody? So how would I write that? Well, the heap array is called heap array. So I would just say if heap array at index over 2, the parent, because that's where the parent always is, if that's greater than the current value, well, then you swap the two. And then how would you swap the two? Well, this is just a function call to the swap function calling the two, like passing in the two. Now, the order doesn't matter because it'll swap them both regardless. But then how would I write this? But let's just do the parent first. How would I write the passing in the parent? Good. I just want to make sure you guys understood that this is passed by reference. You have to pass in the address because it's pointers. So it's the address of heap array. You know what? I'm just going to copy this. So it's the address of this guy and the address of this guy. Make sense? Because if you don't put the address, it won't swap them all. Then the last step, what do you think I'm going to do here? You need to keep going if you're not at the root. So then how would I write the recursive call? Who am I going to go to? Like what? Yeah, you go to the parent. You just move on up to the parent. So that's an index over 2. And there you go. That's the full answer to this question. Did all that make sense? Questions, comments, concerns? Awesome. Let's get a move on then. Okay, this one, before we do it, let's just jump straight into this. This one was actually from my foundation exam I took. Let's just fill in these blanks first. What is the big O runtime, the worst case big O runtime for the following operations? Building a binary heap from an unordered array of size n using Heapify. Someone tell me. O of n, perfect. Heapify is always Heapify is always linear time. It's not log n, it's always just n. How about inserting an item into a binary heap with n items? Log n, good. Inserting is always logarithmic. What about deleting the minimum item from a binary heap with n items? Log n, good. It's also log n. And then heap sort of n items. And log n, good. Those are just kind of memorization. Now, for the question itself, this was a good question. I remember liking this one. You guys want to try it, or should we just jump into it? I assume you guys want to give it a try, right? Question mark? Okay, sure. Let's do 2 minutes. This is not a very long function. I'm gonna give you guys 30 seconds because I'm finishing something up real quick. Give you guys another 30 seconds. All right, sorry about that. Let's do this thing. So this one is really just testing you. Do you know how heap sort works? So could someone quickly just reiterate the overall idea about heap sort? How's it work? Yeah, exactly. You basically create an array of sorted items by constantly removing items from the heap. Now, usually it's done with a min heap. But if you did a max heap, you could just do this and then just flip the array in half after. But basically, the overall idea is you have the array, you constantly call the heap or delete on the heap over and over again, and then you return the final array. So let's look at the question fully. Consider the following struct that represents a binary min heap. You have all the elements, the capacity, and the size. And then you have two functions, one of which called remove min removes the smallest item, and the other one called size, which returns the number of elements in the heap. We're at a function called heap sort that takes a pointer to the heap and returns those values in a sorted integer array. At the end of the function, the heap pointed to by the h will be empty. So really, it's just a matter of following the process. So first, we need to make the array. So if we want to look at the return type here, this is an int pointer. So what should that be jumping out to you as? We need a DMA, exactly. We need to use DMA here. So int, I'm just going to call it ARR. That's equal to, well, how do you do a malloc call? Malloc. We want int, so size of int. Then, how many of them do we need? Well, that's a good question. How many of them do we need? How would we get how many we need, you think? Heap arrow size, exactly. Heap arrow size. Good. Okay, so now we have the array ready to go. Now, what do we have to do? Well, we need to go through. We need to go through all of the. We have to go through how many items are in the heap, and each time just delete it and save it into the array. So if we're gonna do something more than once, what do you need? A loop, exactly. So for int I equals 0. Now this is the tricky part. What do you think I is going to be less than? Be careful here. No, it's not. There is. Oh, we do get the capacity. Um, I guess you could do that. I didn't think about that, but you did, the problem with that is you don't know how many. Um, you don't know if the heap is full to begin with. You don't know if the array is full. So that's why you shouldn't do capacity. You should do size because that's how many items are in the heap. Now, I like what Russell said. The initial size. The initial size. If you if you called the size function every time, or you kept doing h arrow size, there's a problem with that. The problem is every time you call remove min, it changes that value. It changes h arrow size, and thus will also change the value of returned by size, the size function. So if you do that, the problem is the loop won't run as many times as it needs to. So really what you have to do is you have to just write, you have to declare the number of elements beforehand. So int n is equal to h0 size. You have to do that beforehand. So if you did that, you could also just put n in here as well. But does that make sense? Why you have to do that? Okay, good. I is less than n, I plus plus. Now, every time you just save the element that was spit out into the array. So array at I equals removing the min, deleting, remove min with h. And then the last step is just return the result. The resultant array, which is error. Boom, done. Not too bad, right? Honestly, the biggest trick was this guy. Any questions on this? In that removal part, what about it? No, because it would be just the heap h. Because look at the function prototype; it just takes in the entire heap structure. It doesn't take in the array. It's not. It doesn't take in an int. You got to be careful what's being given to you. It takes in the pointer to a heap, which you're also being given already. Does that make sense? Cool, no problem. All right, it's gonna move on. Two to go. Tries. Why use a try? Can we just store strings? It's used for strings. Can we just store strings into a binary tree? Of course you can, but it's using the string functions are expensive. String length and string compare would be those are linear constant time, and it would require multiple computations for each comparison instead of being logarithmic time, which is the whole point of a binary search tree. So a trie is basically a tree that stores a dictionary of words, where each trie it's composed of trie nodes, where each node typically stores two things. It stores an array of trinodes where the index of the trinode represents what alphabetic character it is. So basically, each node has up to 26 children, which may or may not be initialized depending on if there's a longer word that's going through it. Otherwise, it also has a flag variable, so 0 or 1, which denotes whether that node marks the end of a word or not. Hopefully, this is not anything new. So trie operations, inserting. We don't really talk about deleting as much. I mean, deleting is really easy. You just update the flag at the end. That's all you really have to do with the flag at the end of the word. But inserting, you start at the root of the trie and see if the current character of the word you're inserting is a link to the node you're on. If it is, just move to that node and go do the same thing with the next character. Otherwise, create that node and move to that node itself. Searching is basically the same thing, except if you don't find the needed link, you just know it doesn't exist in the trie. Make sense? Awesome. All right, so we have 3 questions for this. This one is a conceptual question. We'll give you guys 2 minutes to try it, see if you can come up with an answer, and then we'll go from there. Actually, I'll give you 2.5 minutes. All right, let's go through this question. This one shouldn't be too bad. It's just, can you insert things and do it? Oops, there we go. Consider inserting the following words into an initially empty trie, where nodes are created only if they are necessary. Note that an empty trie is a null pointer and has 0 nodes. How many nodes will be created after all these words are inserted, including the root node? No need to include any drawing. Just give your final answer, but be very careful since your grading is completely based on the numeric answer and no work at all. So let's just start slowly. You first have to make the root because we're including it. Now, if we want to insert cat, well, okay, just do it like so. Great, that's done. Now, if we want to insert part, well, we have to start over here from the root again because there wasn't a P there. Do, well, there's nothing with a D from the root, so we got to insert that. Art, nothing with an A, so you got to do the whole thing. Now, cart, we have a C and an A from the root, so we can just expand from that. There's the R and the T. Car, we don't need to make anything because we already have CAR. Dog, we only need to make the G. Dart, oh, I probably should have written this better. Let me do this. There we go. We can expand out the D. There we go. Arc, we can expand from the R over here, from the A. Excuse me. And park, we have a P, we have an A, we have an R. Just put out the K. So now we just got to count how many nodes there are. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, which is the correct answer. So hopefully you got 21. If you didn't, no worries. Just try it again from scratch. See if you can follow along with me. Hopefully that made sense to everybody. Cool. No one has any questions. We can keep moving. See if we can't finish a little after 1 o'clock today. I don't think we'll go to 2 o'clock, which is good. All right, let's continue. Let's just jump into this coding question since there's a lot and fill in the blank. Okay, we are maintaining a trie for predicting the next letter for a given string. The trie node struct and its properties are discussed below. So there's the structure. You're given, it looks like every node has the 26 children, of course, but some other things. It has an integer called frequency, which is the frequency of this word represented by the node, i.e., how many times the word has been added to the dictionary. If this is 0, it means there's no word in the trie that ends at that node. Some prefix freq, that is the total frequency of all words in the dictionary that have a string that have the string as a prefix, including the string itself. So, prefix, for example, if you have the words par, part, park, park like this, the prefix for all these would be par. So that's what a prefix is if you're not sure. Does that make sense? Cool. Current max frequency, which is the highest sum frequency among all child nodes of the current. Basically, how many words are in all the children from this node. And then, of course, the 26 children. A pointer should be null along in this array if no words in the dictionary continue along the path. Typically, of course, only a subset will be active. Here's an example. The following trie is constructed after inserting the following list of words and their frequencies. The numbers inside a node represent its frequency, some prefix, and current max. So let's just start at the bottom for a simple example. So here, if we follow along, A, B, well, at this node, there's no word from the list that is just AB. But afterwards, we can see that there is, current max, we can see that there is a sum of current max of 10 of the max that's the highest sum that's basically the highest frequency from the rest of them. Sum frequency, excuse me, the highest sum frequency, so the one in the middle. And then back to this node, the total frequency of all words in the dictionary that have the string as a prefix, well, there's only one. It's able, since there's 10 here, so that is also 10. Does that make sense? As another example, if we go over to this node, there is no word that is just CA. So the frequency should be 0. But the sum, the sum of there are two words after it. There's cat and there's cap. Cat has a sum prefix of 20, and the cap has a sum prefix of 15. So the CA would have a total of 35 since it's its two children. Oh, that was actually, no, that was right. And then current max, that's just the highest sum frequency of the two children. So the biggest one of the two of the middle numbers of the two children in this case is 20. So that's why that is 20. Does all that make sense? I hope. Our goal is to complete the recursive function of the next page that receives the root of a trie t, a string str, and an integer k, the current position in the string, and returns the most likely letter that follows the input string. You must assume a unique letter. You may assume a unique letter appears most of the time in current max frequency. If there is no string in the trie that str is the proper prefix for, then return the question mark character. So basically, what are we asking to do? For example, if the string passed to the function is predict roots with the string a and 0, it should make a recursive call to its child because that would return C because C is the likely most letter since it has a higher current max frequency. I guess. Is that why? Just reading it again. This is why I got to reread these a couple times. I think if there's a tie, you're supposed to I'm just making sure I understand this. Basically, you have to check, hey, is the sum equal to the current max? And if it is, then you go to it. No, that's not true. I forgot what I just said. Basically, what you're doing is you're going through it. It looks like, yeah, you do an A, but then why? How does it determine the C? That's what I'm just trying to figure out. Well, I'm stupid because it's looking at this. There's a loop here, so it's going through them all anyway. Okay, that makes sense. So then basically you're going through and it'll check out the children, possibly it'll figure out a variable and then go from there. So looking back at the example, if you pass an A, it should return C because C is the most likely letter to follow A for the sample try. Then if you did AB, that would eventually return 1, the lowercase l, because that's the next thing that's likely to follow. AC would return the T because that has more stuff than the E. ACE would return question mark because after 3 recursive calls, ACE is not a proper prefix for anything. And then AP would return question mark as well because there's an A, but there's no P whatsoever. So really, it's just you have to check, is the prefix in there? And if it is, basically, which of the children, I guess, has the higher, well, not even that. Actually, all you really have to do is just, as you're going through the children, you find the first one that comes first that has the same sum. The children has the same sum as the current node's current max. Does that make sense? Because if you look through, for example, back at A, it's going through and it'll check, okay, hey, C's sum is the same as the current in A. So that means it would be the most likely to go. Does that make sense? How that works? So I need me to explain that again. Okay, we're good. Okay, so really, let's start with the first case. We have to check if there's no string in the prefix. How would we do that? This should be pretty self-explanatory because if there's no string with the prefix, then you know you're done. Any ideas? What attribute could tell you that the prefix has nothing? Anybody? Some prefix is a good idea, but let's think about that. If we did some prefix, it would do the total frequency of all words in the dictionary that have this string as a prefix, including the string itself. So the only problem with that is, for example, if you were trying to see if the prefix a has that, if you did some prefix, the middle number, well, it's kind of hard to tell because there's still other stuff that could. I guess you could, but it would be better, yes, to do if the current prefix equals 0, because or current max prefix, because if that is equal to 0, then you know immediately that because remember, this is a base case. I should have pointed out this is a base case. So if this is equal to 0, then you know the prefix doesn't already exist and you can immediately stop. I should have pointed that out. I apologize. Does that make sense? So you'd want to do current max frequency because this is your base case. If it doesn't exist, return the question mark. How would you write that? Well, T, you got to dereference it. Cur max freak, if that is equal to 0. Because then if it doesn't exist, there's no need to keep going. You're done. Okay, so now the next part, we see it looks through all possible next letters until it finds the one that has the most words that start with the prefix. So this is looping through all of the nodes. So what's the first thing you have to check always when you're looking through all the possible children? Anybody? Exactly. You have to check if the letter is null, because if the letter is not null and you go to it, you're going to have problems. Or if the letter is null and you go to it, you'll have problems, excuse me. So you check, hey, I'm looping through the children, which is called next. If the current try node's next child that I'm on, so T of next at I, if that is not equal to null, then we're good. So check that. Now we have to check how would we check if, so like if we're at this A here, how would we determine which one comes first? Do you think? Take a look at, like, compare A's values to B and C here. That should give it away. Anybody? Remember here, I'll do this. This is the that's freak, that's sum, and that's the current. Now see how those overlap on the two children in this case, as an example. Because remember, the value returned here was C. So how did it know, you think? Exactly, yes. That's basically the right idea. If the next child's sum frequency is equal to the current node's current frequency, then you know that's the one that has to come first. Does that make sense? Yes? No? Maybe so? Just think about it. The current is the current frequency here. We knew C has to come first, and the current frequency here, Matt, is the same as the sum frequency here. So that means it's more likely to have a prefix there. versus this guy because that one's smaller. So how do we write that? Well, we just do it in this if statement. Then we do if t arrow next at I got to dereference that node, sum prefix frequency. If that is equal to the current node's current max frequency, oops. If that is true, then you just return that character because you know that's the one that moves forward. Now, if that isn't true, then you would just have to keep going. So you do the recursive call as it says. So how would I make a recursive call? Well, first you rewrite the function name. Then what's the first parameter? Well, then we would have to go to the next child. How would I go to the next child? Basically, if these two fail, these two assignments fail, that means you need to keep going. And remember, we're given an index in the string with k. We haven't used that yet. Any ideas how I'd write this? Anybody? Well, all you have to do is just move forward to the next child based on the k plus one, yes, but I wasn't getting there yet. Basically, you have to figure out what node to go to. Well, you just go to the one at the next child based on the current index of the string you're in. So it would be t arrow next at the current string's letter minus the lowercase a, because that gets you the actual index in the alphabet. Then the string itself is not changing, and then you increment k by 1 since you're going to a new index. And that, my friends, is the whole thing. Did that make sense, I hope, how this works? This one's very wordy. Any questions or anything? Please don't hesitate to ask. All right, let's do the last one then. Just get right into it. Assume that a dictionary of words is already stored in a trie with the structs shown below. Complete the function below so that it prints out all words, lowercase letters, stored in the dictionary of length, big length, which is constant, in alphabetical order. Note, students often get tripped up about when to use the null character, so that code's been provided for you. A correct response won't ever require writing the terminator in the space you're given. Necessary support code is given below. Basically, they're just making the buffer string and putting in the terminator at the end, and they're initializing a trie. And now they're calling this function we need to write. So basically, all we have to do is just go through and print out all the letters in the trie in alphabetical order. And then we're doing this recursively. So how do you think we can do this? Let's make up a quick trie. We have the roots. I'll make up like 3 words. Cat, dog, um, fish. And then how about expand one of these? Finish. What do you think is the general idea? How could I print these in alphabetical order? Do you think? Any ideas? Like tell me the conceptual thing. How would you do this? Well, really, what you have to do, if you think about it, Yeah, it's almost like a pre-order recursive. Exactly. It's basically you're doing it almost like a pre-order traversive call. It's basically you have to go down here, see if there's anything to print, see if there's a word that matches. Do that, then you go back up to the root, go to its next, and basically, yeah, it's exactly just doing a pre-order traversal of the tree. And anywhere you hit, you find that the word flag is true, you can print the string. Does that make sense? So let's do the base case first. This should be easy. So if k is equal to n, that means that you're basically through all the indices in a word possibly. So how would I check if there actually is a word there? You can't just assume that there's a word there. You still have to check the flag variable, right? Because look at the structure. It has the flag variable. One if it's in the try, zero if it's not. So what would I do here first before I print? Any ideas? Think you through. So if k is equal to n, remember that means there's a possibility there's a word there, but you're not sure. How do you check? Not if a letter is null. Look at what we have. If we're at possibly the end of a word, what thing will tell me if a word is actually at this try node? And that means we need to print it. Exactly. If the current nodes is word flag is one, that means that's the end of a word, so you should print it out. Exactly. So if root arrow is word is equal to one, just print out. How do you think I print this out? Any ideas? What do you think I can just? Yeah, you can just do percent %s. It'll always work. Percent %s, new line, and then you print out the buffer, which is basically holding like all the combinations, like the combinations we built up to. Because basically along the way we're building like it has C, then it has CA, then it has CT, etc. So basically, once you hit a word, you know the buffer is at the word you want it to be at. I don't think you do. Well, actually, you probably do since you're trying to print all the separate words separately. I don't think that would really hurt you per se, but and then do I need to keep going once I'm here? Should I go down to where the recursive call would be? No. So how would I go back? Just a return statement. Return. Okay. So now basically we have the part at the end. Now, how do you think I can just go through at every node all of the children and then keep doing this pre-order traversal process? Remember, pre-order is root left right. Exactly. Loop through all the children. Good. That's a great start. Check all the characters. Yeah, that's pretty much exactly right. For int I equals 0. I is less than 26 since there's 26 letters in the alphabet. Plus plus. Okay. So what do you think the first, should I recursively call first or is there something else I should do? Remember, we're basically building up an array along the way. And we're building up this array with each character as we encounter it. And as we go back, it goes away. You actually wouldn't want to recurse first because we need to be, if you were just a straight recurse, you wouldn't be filling up the buffer with anything. Before you recursively go, like for example, you got to fill up the C. Like this is a better example over here. You got to fill up the F, you got to fill up the I, and then before you go left, the I has to be there. If it's not there, you wouldn't get anything. Well, we don't even need to actually check if it exists or not because that's already being done up here. It'll, if no matter what, when we do the recursive call, if it doesn't exist, this will just go back right away. Does that make sense, Steven? I mean, you could check it here, but it's kind of silly to, since this will already take care of it. Does that make sense? Okay, cool. So we have to fill in the string, the character first. So why did he? I don't know. So buffer, since they're building up this string, buffer at k, because that's the current index in the string you're at, equals, well, how do I get the current letter, you think? Based on what index I'm at. Like the letter I'm going to try and see if I can add it to the string. Any ideas? So that's usually if you want to traverse, but if you want to put in the actual character, I mean, this I don't think it's really said as much. You just do the letter A, and then you add it to whatever index you're at. So, like, you know, if it was 0, you get A, then it would fill B if it was 1, C if it was 2, etc. Does that make sense? Then lastly, you just make your recursive call. So I'm going to abbreviate it, but make sure to print it out on the actual exam. Print words length n. Then you just, I should indent this a little better. Oops. There we go, that's better. Then you just move on to the current child you're trying to do. Root children. I'm using the structure here, basically what's given. Add I. Then you increment k since you're at a new index in the buffer. The buffer doesn't change though since we already changed it. And n. And that's the whole thing. Because no matter what, if you did I minus A, that just gives you, that itself gives you an index, Loretta. So like if you were trying to do the letter C, for example, C is 2, you would basically be doing, well, could you do that? I'm trying to think. No, see, that would be a problem. If you did C minus A, because remember, these characters are stored in ASCII. So if you did C minus A, like pretend, I don't remember what A is exactly, but pretend A is stored at 50, and C, so C would then be 52. You're basically saying, hey, give me the ASCII value of 2, which is not a letter. Does that make sense? If you did the letter A, 50 plus I, that basically be saying, give me 50 plus 2, which is 52, which corresponds to C in ASCII. Does that make sense? No, you're good. But yeah, basically, the buffer, it will add each, it will try to add each letter into the buffer as it traverses, but then if it doesn't exist, it'll go back and be automatically removed and rewritten with the next one. So that's it. This is how this works. Pretty cool, right? Any questions on that? Just take some practice. You know, drawing it out is helpful. That's why I guess I apologize. I probably should have drawn the buffer a little better, the idea of the buffer, since you know you're slowly building it up. If that wasn't clear, so I apologize for that. But I'm hoping the general idea makes sense. Because basically, once this thing is a word, you print it out, and that's how you eventually print everything out. So, any other questions about that? All right, we have 3 questions left. Let's see if we can't finish in half an hour. Our last thing is hash tables. Hashing hash tables. These should all be pretty easy year questions. A hash table is basically, you know, eventually it would be amazing if we could access an array in constant time, but basically you can't do that physically the best. You can't just, if you want, you know, to have social security numbers for everybody and have a unique row for each person, well, then your array would be billions of rows long, which is just stupid with space and searching and whatnot. So hashing is you use a key or basically the data that you put through a function called the hash function, which spits out a random row to basically insert the key into. Does that make sense? Hopefully this is review for you. Basically like, hey, hash function, I have something I want to insert. Where should I put it? The hash function will tell you where to put it. The hash function basically knows the constraints of how big the table is you're working with. So if you had a table array basically of 10, it would know, okay, hey, I'm only working with 10 things. Does that make sense? Cool. So good hash functions are, no problem, Lorena, take care. Good hash functions are deterministic, the same input will always produce the same output, efficient, they basically do it constantly, and they're distributed. They maximize the chance to output many different hash values. See, like this one's not good since it loops through everything. You shouldn't have a loop in a hash function. Problem with hash tables always are collisions, aka two inputs or more can map to the same bucket, and this is known as a collision. There's two types. Open hashing means you can store multiple items in the same row in like a quote unquote bucket, or closed hashing is you better find somewhere else to go. There's two types of open hashing, bucketing and separate chaining. Bucketing is each bucket is basically another array. So, if this was a row, it would then, you have all the rows here. If this was the row that you were going to use bucketing on, well, then basically you have more of the array. It basically, you turn it into a 2D array sense. It's like it has columns now, basically. Whereas separate chaining is a very similar idea, except if this was the row that had the collisions, well, then this would be pointing to the head of a linked list. And so on for each value that maps there. Does that make sense? The differences between those two? So this is typically called bucket hashing. This is typically called separate chaining, or just chaining. Make sense? Hopefully that's pretty new, or not new. Excuse me. So chaining is a lot more memory efficient as opposed to bucketing, since only allocating memory is needed. But the problem is, if the chain gets too long, the poor search of a linked list having to go through the whole thing starts to take over. But because you have to search through the whole thing if you're trying to find something, and it relies on a good hash function, because without one, you have linear access time, which is not good. So closed hashing, there's two types. Again, this is basically you're going to find somewhere else to go instead. There's linear probing and quadratic probing. Quadratic probing is usually better since linear kind of has clustering. But linear probing, remember, you just go, if this is if one is where the collision is, linear, you just go one by one by, let me do, there we go. One by one by one by one by one until you get a spot that's open. Otherwise, once you get a spot that's open, you're good. Otherwise, you just keep going until you find a spot that's open, basically. Quadratic probing, though, it basically does the same thing, except you're going in groups of squares. So it checks the one squared position away, so one away. Then it checks, if that's full, then it checks the two squared position away, so four away. Then if that's full, you check the three squared position away, so nine away. And mind you, this loops around. It's like modulus. And so on. It keeps doing that over and over again until it finds an open spot. Does that make sense? Quadratic probing is typically better, but it can be terrible with largely full hashes. Make sense? I hope. All right, so 3 questions, I think. Is it 3? I think it's 3. Yeah, it's 3. Oh, wait. Oh, it's 4. Okay, wow, we got 4 questions. All right, so let's just jump right into these. I think this just for time. All right. Consider the following hash function and then the questions that follow. Here's the hash function. Basically, it gets the index of the last letter in the string, since it takes the string length of the string and minuses 1, get the last index. And then basically it converts the letter at the last index to lowercase and then gets its index of that letter in the alphabet. So, first part is give the hash code produced for each of the following strings. Well, to begin, we have to first it's getting the index of t. Oh, actually, I said that wrong. It's getting the index of where the last letter is in the string, but then it's getting that letter and basically subtracting it from. It's basically finding where is that last letter in the alphabet. That's really all it's doing. Where's the last letter in the alphabet? So, first for not, the letter not, it takes in the letter T and it gets its index in the string. So then it's converting that letter to lowercase, which it already is, and then subtracting it from lowercase a. So basically, what index is T in the alphabet? Now, if you don't know, you probably wouldn't hurt to do this: A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, U, V, W, X, Y, Z. So then just label them 0, 1, 2, 3, 4. I think it's easy to have this chart here. It makes it a lot easier. Twenty goes to U. Okay, so we can see right away T is the 19th letter in the alphabet. So that's 19. The next one, last letter is W. W is at 22. The next one is T again in bright. Moon, the last letter is N. That's at 13. And then the last one is now. That's at, or it'd have W, 22 again. Make sense? So that's where the hash function is telling them to go. Then, using the hash values above, insert the strings one by one in the order given above, into the following hash table. Use quadratic probing to resolve any collisions. And there's a special technique for values that exceed the length of a table, which we'll get to. So, 19. So the length of the hash table is 10. So is 19 even in the table? No. So what you do, since it's 10, this is really nice. All you have to do is you basically just mod it by the length of the hash table size, 10. And when you mod something by 10, it just spits out the last digit. So not would go to index 9. Hopefully that makes sense. Then no, same thing. Last digit is 2. And since you're 22 mod by 10 would be 22. So now no would go in index 2. Bright. Now we have a collision. Since that would go to index 9, since 19 mod 10 is 9. But we're going to use quadratic probing since there's a collision. So first, I'm going to check the 1 squared spot away. So just 1 away. Is the first spot after 9 open? Mind you, this loops? Absolutely. So bright's going to go into index 0. Great. Moon, that can go into 3, no problem. Subtracting that last digit. And then now, that would go to 2 normally, but that has a collision. So I'm going to first check the 1 squared spot away. That's taken. How about the 1, 2, 3, 4 squared, the 2 squared spot away? 4. That is not taken. So again, that's the 2 squared spot away right there. It's 6. So that is where now would go. And there you go. That's that whole question. That makes sense? Hopefully. I'm going to actually skip the next one for now just because of time. And this one's just really, can you mod these numbers by 12 and differentiate between the 3 techniques? That's all it is. I want to do something like this one. Suppose we insert, here, let me just say this was skipped. Let's do this one and the next one. Suppose we insert 9 strings into a hash table and end up with the following. Bunch of fruits. Furthermore, suppose we no longer know the order in which these strings was inserted or what their hash values were. In solving this problem, you may assume quadratic probing was used for the collisions. You should also assume that no strings may have been deleted from the table and that each of these strings were inserted exactly once, no more, no less. You may also assume that the table length was 13 for all insertions. None of the insertions triggered an expansion of the table. Fill in the 10 blanks below to indicate whether the hash value for banana, when modded by the table length 13, might have been the value indicated. For example, it's impossible that hash banana mod 13 could have been 1, because if it were, the banana would have been in position 1, which is empty now, and not in position 12. but it is possible that hash banana mod 13 equals 12 because that's where it ended up. Fill in each of these blanks with yes or no. Do not leave any blank. So do you understand what we're being asked to do here? One of the four people tell me. If you want to unmute, that's fine too. Anybody? Anybody have any idea what we should do here? Basically, what you need to do, you basically just have to go to each index that's not empty. If they are empty, you immediately know it couldn't, that's not an answer. So I'm going to fill those in right away. Those are no, because there's no way it could have gone in there. So we have 4, 1, 7, and 11. Because if it did, if that is where it was, it would have just gone into there. Basically, what we have to do is, for all the non-empty indices, see if there's eventually a way quadratic probing could have gotten us to index 12. Because that's where banana went. Make sense? So let's do that, starting with index 0. Well, the 1 squared spot's open, so no, there's no way it would have gone there because it would have gone straight into index 1. Let's try index 2. Well, banana, it couldn't go to the 1 squared spot because that's taken. How about the 1, 2, 3, 4? That's taken. How about the 1, 2, 3, 4, 5, 6, 7, 8, 9? No, there's no way. It would have gone to 11. How about 3 if it hashed to 3? Well, the 1 squared spot's open, so there's no way. Index 5. The 1 squared spot is taken, but the 1, 2, 3, 4 spot is taken. How about the 1, 2, 3, 4, 5, 6, 7, 8, 9 spot is open? So no, there's no way it would have gone to index 12 then. Index 6, the 1 squared spot is open, so no way. Index 8, the 1 squared spot is taken, but the 1, 2, 3, 4 is 12, and that's where it ended up. So yes, it possibly could have hashed to index 8. Index 9, well, if it banana hashed there, the 1 squared spot is taken. The 1, 2, 3, 4 is taken. Let's try the 3 squared. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's taken. Try the 4 squared. The 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It does end up at banana. So yes. And then index 10, the 1 squared spot is taken. The 1, 2, 3, 4 is open. So there's no way it would have gone to 10. Basically, it only could have passed to either 12, 8, or 9. Does that make sense? That's how you get that answer. All right, let's do the last question. This one's a bit tedious. That's why I'd rather do this one than the other one. This one also involves some math. The other one, though, is just mod. This one involves more than mod, so that's why I want to do this one. Use the following hash functions use the following hash function. Insert the following elements into the table below. Use quadratic probing to resolve any collisions. You may assume that the correct table size, in this case 10, is always passed to the function. So basically, we have it calculates two numbers. The first one, key mod 100, means get rid of the right two most digits, and then divide it by 10. Then the second one takes the key, mod it by 10 to get rid of the last digit, and then return the sum of those two, mod the table size. Let's do this step by step. First off, with 2055, I'm going to do this in like colors here. 2555 mod 100, that is 25, because you just get rid of the last two digits. And 25 divided by 10 is just 2. So A would be 2. And again, that's using integer division. And the other one takes 2555 and mods it by 10, so it gets out the last digit, which is 5. Then lastly, it returns a plus b. So 2 plus 5 is 7. Mod the table size, 7 mod 10 is 7. So that is not correct. Okay, I did something wrong. Let's figure out where I went wrong here.
I think
P mod 100 is, go ahead.
it's mod the mod 2555 mod 100 is 55.
You're right. Thank you.
Yeah.
Yeah,
So that gets to 5.
right. It would get, yeah. Because, yeah, that gets the, 10 gets the last most two digits. So, yeah, 100 would get the right most two digits. Sorry about that. So, yeah, you're right. It is 55, Dylan. So then, yeah, you would get a 5 here instead, because 55 divided by 10 with integer division is 5. So 5 plus 5 is 10, and 10 mod the table size is 0. That's where that would go. Next up is 1523. That gets the rightmost two digits, 23. Divides it by 10, you would get 2. Then it gets 1523 mod 10, that's a 3, as that's just the last digit. 3 plus 5, 5, or sorry, 3 plus 2, 5, mod 10 is 5. That's where 1523 goes. And green, we have 58, 9, come on, I want green, please. There we go, 5893. Okay, well, the last two digits is 93, since that's what mod 100 is. Dividing by 10 gives you 9. The original number, 5893 mod 10, is the last digit, 3. The 9 plus 3 is 12. 12 mod 10 is 2. So that's where this will go. Then we have 800. 800, that gives you the last two digits, 0. 0 divided by 10 is just 0. The other one's 0 as well, since 0 mod 10 is 0. Then 0 plus 0 mod 10 is also 0. But we have a collision, so we're using quadratic probing, since 0 is taken. So first we check the 1 squared spot away, which is just 1. 1 away, and that's index 1, and that is open. So that's where 800 will go. And then last but not least, we have 956. The last two digits is 56. 56 divided by 10 is 5. 6, or B would be 6, since 956 mod 10 is 6. Then 5 plus 6 is 11. 11 mod 10 is 1. We have another collision. Check the 1 squared spot away. That's open. Check the 1, 2, 3, 4. Or I'm sorry. Let me say that all again. The 1 squared spot away is closed. It's taken. Check the 1, 2, 3, 4 away. That's also taken. So let's check the 1, 2, 3, 4, 5, 6, 7, 8, 9. That's also taken. So let's check the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's open. So that is going to go into index 7, 956. And there you go. That's the answer to this question. Really, the trick here is knowing that modding anything by 100 gives you the last two digits. Modding anything by 10 gets you the last digit. Any questions? All right, I think that'll be a good stopping point, since this one again is really just, can you do the mod? It's tedious because you got to do it by hand, but you could do it, I'm sure. Just for time's sake, and it's already long enough. You basically just do that. Can you differentiate between the three probing techniques? So really, all in all, if there's no questions, that is all of the foundation exam crash course for day 3 and the entire thing itself for spring of 2026. I thank you all for being here. If you attended any of the meetings, thank you to the 4 of you right now who stood around the whole time. If you're watching this, thank you for watching the whole thing or whatever you watched. I know 11 hours is going to be very long of a recording in total. I wish you all an amazing spring. Best of luck, of course, taking the foundation exam. You all got this. I hope you liked my teaching and the way this went. Sorry if I made some mistakes. I'm only human, of course. There's a feedback form here, which you can fill out in the slides. There's a permutation section down here as well, which I'm not going to go over, but just can you memorize the permutation stuff mainly. But These slides and then recordings will be posted not only in that OneDrive folder, but the recording of everything should be posted on will be posted on my YouTube channel and the Night Hacks YouTube channel at some point soon. Best of luck for studying. I really wish you all the best of luck on this exam. You all got this. You should get some details about it soon, probably hopefully today or tomorrow. Make sure you registered. If you didn't register, do that. Again, thank you all for being here. Have a great rest of your day and your week, and I wish you all the best in the semester ahead.